is working. Good morning, everyone. I hope you all had a great banquet last night. I'm glad that some of you actually made it here this morning. I'm Nicholas, and this is Georgia. Together, we'll be hosting the session, and I think it's going to be a really interesting session on foundation models for robot learning. So without further ado, let's get started. And we'll start with, Masha, presenting Explore Until Confident, Efficient Exploration for Embodied Question Answering.
Good morning, my name is Masha. I'll be presenting for Alan Wren. We're interested in the setting of embodied question answering, or EQA. So imagine you have a robot that's plopped into a home without prior knowledge. In order to answer a question, for example, which item is left on the armchair next to the bedroom dresser, it needs to first explore the scene and then stop when it is confident enough to answer this question. We call this efficient exploration. Our paper presents Explore Until Confident, which achieves efficient exploration both in simulated and real scenes. We use the rich prior knowledge of VLMs, which can answer complex questions about 2D images. We also hypothesize that these VLMs can actually reason about the relevant regions in the scene. One issue with the VLMs is that they don't have an internal memory to keep track of the semantic mapping information or that information from prior views. So what we do is we build a map online which keeps track of the semantics. So for example, we have this image that the robot sees, and we label A, B, and C as free regions that it could explore. So for instance, it might be asked, is the outdoor grill covered? So what we can ask is, which direction would you explore next? This prompt and the image can be passed into the VLM and output likelihoods for the options. This is the local semantic value, or LSV. Similarly, we can ask, is this image relevant at all? Is it worth exploring? This is our global semantic value, or GSV. We can combine the two to build a 2D semantic map, which is filled with these semantic values. We explore the region using a frontier, which is the space between explored and unexplored regions, and we choose the next point by weighted sampling using the semantic values. We found our method to be more efficient than the baselines, such as just frontier-based exploration or CLIP and frontier-based exploration. We also found that both GSV and LSV are critical to achieving this efficient exploration. The robot also needs to decide when to stop the exploration and to answer the question. In order to do this, we once again prompt the VLM. We ask it, are you confident about answering the question given the current view? Once again, we pass the prompt and the image into the VLM, and we get out a probability. This is our question image relevance score that the robot could use to know when to stop. Unfortunately, VLMs are often miscalibrated. They can be over or underconfident. In this case, it's underconfident in both examples. And so to solve this, we use multi-step conformal prediction to rigorously quantify the uncertainty. It outputs a prediction set using this relevancy score. And what happens over time steps is we take the intersection of these prediction sets over time. Once we have a singleton set, or one option, the robot stops exploring and can answer the question. We have a coverage guarantee that with high probability, the correct answer is achieved with high likelihood. In our experimentation, we curate a simulated data set with 500 questions and 267 simulated scenes. In this simulated example, the question is the lamp next to the sofa turned on? The robot explores the home and eventually sees the lamp and notices that it is turned on, in fact, and answers correctly. This approach is more efficient than those that don't employ VLM-based exploration. In our hardware experiments, we ask, what kind of stools are under the whiteboard? And as you can see in the prediction set, it reduces from 4 to 2 until the robot can see the stools and notice that they are actually lime green and answer appropriately. Please check out our website. Thank you very much. Happy to take questions.
Okay, so we have time for a few questions. First question over there.
That's really cool. I was wondering if you could explain, do you draw the letters on the image? And is that kind of you're mapping from 3D into your 2D space, is that right?
Yeah, basically you can map out the free space and then cluster and put the letters there.
That's cool. And then you're literally just saying which letter to go to.
Yeah, and weirdly, that's a really important thing for VLMs to do.
Yeah, that's really clever. Thank you.
Mm-hmm.
Any other question?
So the VLM operates over 2D images, right? And you're also building this 2D semantic map. Do you see any direction here that perhaps 3D reasoning would help?
So there's actually an intermediate step where Alan, the first author, he builds a 3D voxel grid, and then that gets projected down to a 2D map. You could totally keep track of 3D points. We didn't find it super useful in this work, but there are definitely situations where that would be helpful.
The question here, please.
Hi, I'm wondering about a case where background knowledge can result in inferences which mean that you don't actually have to drive around. So I'm thinking of a scenario where you say something like, the professor is either in her office or she's in the lab. And the question is the professor in her lab? But the office is much closer, so you drive to the office and you make an observation and you realize she's not there, and you therefore conclude that you can answer the question confidently that she's in the lab. Can you do this sort of thing? Do you think a large language model could allow you to do that sort of inference?
I don't think I fully follow the nuance of the question. Would you mind?
Sure. So imagine you have an XOR condition, and rather than you're asked about one of the branches, and rather than answer.
So to figure out once you see it, I think this is not a nice answer, but if you prompt it in such a way to say that, hey, this is one of the categories of questions that might happen, that you have an XOR condition, I bet it could, yeah. But unfortunately, a lot of these things, they highly depend on these little tricks like prompt engineering or putting the ABC in the images, which allow them to work really nicely, but are not scientifically really happy, yeah.
Okay, let's thank the speaker. And let's move to the next speaker, Homer, that will present Octo, an open source generalist robot policy.
Hey guys, my name is Dibbo, and I'm presenting Octo with Homer, an open source generalist robot policy. This is joint work with collaborators from CMU, Stanford, Google, and Berkeley. I'd especially like to mention Carl, Kevin, and Oyer, who are the other visionaries behind this work. So the big lesson that we've learned in machine learning is that large models trained on larger data sets just work. They generalize well, they perform better in outer distribution situations, and they're more robust. And the same situation seems to be coming to robotics, where instead of training my model on my single robot in my single task, I can leverage all of these large data sets to really improve the policy. But this is easier said than done. Robots have different types of task specification, different numbers of sensors, different types of cameras, different types of action spaces, and in general, getting one model that can share information and learn across all of these different modalities is very, very difficult. So I'd like to tell you about Octo, our version at making such a model, how we trained it, how you can use it, and some lessons we learned along the way. So the core idea in Octo is to say, let's take all of these diverse robot data sets and convert them into a sequence of tokens. Pretty simple, pretty vogue. So what does that mean? It means we take our tasks and our observations and we use small input adapters to convert them into sequences. It gets passed through a massive transformer, and then the transformer embedding gets decoded into a robot action at the very end by a small adapter. Now, a few decisions were important here. The first is that robot datasets are very diverse, and using multimodal action prediction is really important. We found diffusion policies to work best over MSE and discrete actions. The second important lesson is that you want to let the transformer do all the work. Rather than having large ResNets to process the images before, we found that letting the transformer do all the work in processing the visual observations allowed us to attend to previous tokens, different tasks to learn better semantic features. And this plays another role too. Let's say I want to take this model and fine-tune it. When I fine-tune it, I can just change the input and output adapters and keep the majority of parameters which are in the transformer and retain a lot of the pre-training. Homer's going to talk about the data and how we train the model.
Yeah, so let's talk a little bit about the data that Octo is trained on. So we use the Open Cross-embodiment dataset, which is a collection of robot datasets submitted by research labs around the world. So our subset of the Open Cross-embodiment dataset contains 800,000 episodes across 11 different robot embodiments. However, training a policy on this large and diverse data is challenging for a couple reasons. First, just loading the data is hard. So we designed a super fast data loader that makes it so that anyone can use the Open Cross-embodiment dataset and release this for everyone to use. The second issue is that not all the data is very good. The quality varies widely, and so we found that we had to remove datasets that had a low image resolution, that were overly repetitive or contained excessively niche tasks. And so we found that our mix, the Octo mix, outperforms prior mixes of the Open Cross-embodiment dataset and enables positive transfer across robots and tasks. And so there are a couple ways that we can use Octo. The first way is to use it just out of the box and evaluate on robots that were seen during pre-training. So in this zero-shot evaluation, we found that Octo outperforms the prior best openly available generalist robot policy, RC1X. And interestingly, Octo also performs comparably to a much larger 55 billion parameter policy fine-tuned from a VLM. So that's RT2X here. Notably, Octo also has favorable scaling qualities. So we can see that larger Octo models perform better than smaller models. And one thing I want to really stress here is that unlike prior generalist robot policies, Octo allows for flexible task and observation inputs. So whereas prior policies might have only been able to use a single camera or language instructions, Octo can use both goal images, language instructions, third-person cameras, or wrist-person cameras. So the second way to use Octo is to fine-tune it on your own small robot demonstration data set. And yeah, so Octo supports fine-tuning to both observation and action spaces that were not seen during pre-training. In our fine-tuning experiments, we found that Octo outperforms policies trained from scratch, as well as policies trained from pre-trained visual features. So we tried to make Octo really easy for everyone to use. So we released good open source code on this website, as well as pre-trained checkpoints. So we hope you check it out. Thank you.
Are there questions? Here there is one, please.
Hi, nice work. So I'm wondering, have you tested in a zero-shot manner on like some new tasks and new setup? And what's the success rate you observe? And if that's not high enough, what do you think is the like how many data or what kind of data we needed to really scale this up? Yeah, thank you.
So I guess generalization comes in different types of forms, right? There's generalization to new robots. There's generalization to new tasks that you can put on robots. So we did a test like that kind of breaks this kind of thing down. The truth is we can't control completely new robots. It's difficult, there's different action spaces. And it's also sometimes very difficult if you change let's say like, I don't know, you knocked over the camera, right? And then you put it back, but it's like kind of off. Doesn't quite work zero shot yet. I think there's a data coverage problem, and we use the most diverse data we have right now, but there's a lot more to be collected, and I think we need to make a lot more headway there. Also, like kind of a core principle here was like we kind of wanted to keep it simple, keep it from scratch. There's a lot of work that you can do to like improve on top of this, and I think a lot of the newer works have been kind of getting better about using, let's say, like internet pre-trained knowledge and other types of things to improve zero-shot performance. I think for fine-tuning, it matters less, and like the kind of features you learn visually from these other robots are just as good. But for zero-shot things, there's a lot of work to be done.
Okay, for the interest of time, we will thank now the speakers.
And the next paper is going to be demonstrating OK Robot, what really matters in integrating open knowledge models for robotics. And Mahi is going to be presenting.
Imagine taking a new robot, putting it in your home, unboxing it, and just giving it some command. Like, take the cooking bottle from the kitchen counter and put it to a different marble surface. Imagine, without any demonstration, any training, any fine-tuning, the robot just working and doing the task that you tell it to do. That's what we try to build in our project, OK Robot. And we do it by using large, pre-trained models that has been trained on a lot more data, and we stitch it together in clever and careful ways. And we can deploy it in 10 different New York home environments, and we can get it to do interesting things just by giving it a language query. And that's what you see in the video here. So the question is, how does it work? So you take a robot, you put it in a home, you give it a query, like, OK Robot, move the takis from the desk to the nightstand. This is a complex task, and we try to break it down into 3 little pieces. So the pieces are, how do I get to the takis? How do I pick up the takis? And how do I drop the takis on the nightstand? So let's take the first one, which is, how do I go to the takis? So for this, the robot scans the environment, gets a lot of RGBD images. We process this with LVIT and clip, and we get a voxel map, which maps every point in space to a semantic representation. And once you have this map, you can actually query with language. So for example, you can ask where the plants are, or you can ask for where the red body spray is, and you can give it many other language queries. But more than just point queries, you can also ask it for direction. You can give it like, hey, how do I get to the plants or the takis on the table? And it gives you a plan. So we use that to navigate to the takis on the table. Then the question becomes, how do I pick up the takis on the table now that I'm in front of the table? So here's a robot looking at the table. There's some takis on the table. The robot doesn't know what it is, right? So first what we use is AnyGrasp, which is a grasp perception model, and it proposes all the possible grasps on the scene, as you can see here. Very cluttered, so we have to clean it up a little bit. So what we use is this model called LangSam, which takes a query, like takis, and once you give it the query, it just maps out, segments out where the takis are on the table. So you can combine both of those together, and you can get just some segmented grasp proposals on the takis themselves. Once you have those, you can use a heuristic to pick the best possible grasps on the takis, and then our robot just open loop executes it. So once it executes, hopefully the takis are in the robot's hand, and then the next problem becomes, how do I go to the nightstand and drop the takis? Going to the nightstand is very similar to step 1, so I'm not going to talk too much about it, but the problem is, how do I drop the takis on the nightstand, right? So again, the robot has gone to the nightstand, it's looking at the scene, it's thinking like, okay, where do I drop? Once again, we use a LangSam model to figure out which part of the scene is a nightstand, right? So here's the LangSam output, it's telling like, okay, this is where the nightstand is. We have the depth image as well, so we can figure out the 3D structure, and we figure out a central point using a heuristic on where to drop the takis. So our robot just kind of moves the arm right on top of the dropping location, it opens its gripper, and hopefully that drops the takis at the target location. And then you can give it further queries, so it can do a few things in a row. We have some videos where it's doing 5 things in a row, and so on and so forth. And you know, like once this completes, then the question becomes, what can you do with it? And that's what I'm going to be talking about here. So we took it to 10 different home environments, we just put it there, we just run the robot, and then we get some data, right? Like the robot's doing something, it's picking up, placing things. So we ran 375 trials in total in 10 different home environments. And a lot of them succeeds, some of them don't, and so we wanted to understand how things fail, right? Because that gives us pointer on what research to do next. So here's the failure analysis of all the different ways this method can fail. You can see there are different categories, like navigation failure, there's manipulation failure, and even within those categories, there are subcategories, like sometimes the model fails, and within the models, any grasp may fail, or langsam may fail, right? This is for us to better understand how we can do better next time. And one of the examples is, for example, this case of VLM incantations. Sometimes you have to ask for things in a very specific way. Like you can't ask for an orange soda can. The model's like, I don't know what an orange soda can is. You ask for a metallic golden beverage can. All of a sudden it's like, okay, I know where it is, I'm gonna go get it, right? This is problematic if you want to just zero-shot deploy it in your home because you don't want to ask for things in this magical way. You want to understand what's going on, and right now we don't really understand how VLMs work that well. So as we understand this, this will get better. And there are more failure cases on our paper, on our website, so you should be able to check those out as well. We try to do as detailed of an analysis as possible. Here's our paper and code. Everything is on our website. You can also see more videos. And we love open source. We open source everything. We want you to just be able to download and run it. So we hope you do that. And I want to thank my collaborators on this. Mahi, thank you so much. And we also planned a demo. The robot didn't get here on time, unfortunately. So I apologize, but we still have videos, so please look at those. And we're going to try to do a remote demo. I don't know if it's going to work out. Thank you so much.
Great, thank you. And we have time for a couple of questions.
Yeah, thanks a lot for the talk. I have one question. So you put the robot in very human-built environments, but then oftentimes you said, well, then the robot just execute that in open loop. For example, it just navigates to the nightstand and then it just picks it up where it's expected to be. What if there are obstructions, if something goes wrong? How will you react? Will you even detect that something went wrong?
That's a very good question, and that's something that we're looking on right now. So for the failure analysis case that we did, we kind of run it so that if something fails, we just put it on the failure cases and move on. But I think this is something that is very important that we want to do. We want to detect if something fails, we want to retry it many times, if possible, ask for help. There are other papers here which talks about it, and I am very interested in looking at those and improving the method in the future. Thank you.
Any more questions?
Oh, thank you so much for the work. I really appreciate the approach. I'm just wondering, just a simple question. Your environment seems a bit unpopulated. I mean, there should be humans there. Did you think about how to involve them in the interaction with the robot?
That is also a very good question, and I really, really enjoy the question, because if we're thinking about homes, then definitely thinking about humans is pretty much high priority. Right now, our model assumes that the environment is static and not much is changing around it. So you can imagine that, you leave the robot in your home, you go to sleep, you wake up, the home is cleaned up. That's kind of our mental model right now. But this is something that we want to look at next. How do we deal with dynamic environments? If there are humans, and you have to think about it as well, just that humans are changing the environment right underneath the robot. So it's not a simple problem, and that's something that we want to tackle next. Thank you so much.
Okay, let's thank the speaker again, and then move on to the next talk.
Okay, so next we have Xingyu presenting any-point trajectory modeling for policy learning.
Hi everyone, I'm Xingyu, and I'm excited to present our paper, Any-Point Trajectory Modeling for Policy Learning. Humans can learn new skills by watching videos. Even the child here can imitate Bruce Lee by watching TV. Can we enable robots to learn by watching videos as well? This would allow robots to learn from the large body of video datasets, paving the way for a robotic foundation model. But what should we learn from the videos? One approach is to learn everything by training a video prediction model. During policy execution, the video model can generate future images as sub-goals to guide the policy. However, just like the flying chairs that you see here, video models can hallucinate and generate unrealistic videos as they focus on modeling the visual appearances. The other extreme is to learn very specific human affordances, such as contact points. But this drops a lot of the information from the videos and can be limited to simple tasks. In this paper, we propose an any-point trajectory model that can instead model the 2D trajectories of all the points within the video frame. Each of these 2D trajectories corresponds to the movement of a point in the 3D space. By treating the videos as point trajectories, we focus on modeling the motions in these videos, which are the most important part for robotics. It also naturally incorporates inductive biases such as object permanence and continuous motion. Specifically, we propose to predict future point trajectories as a way of video pre-training. During the pre-training stage, given a video dataset without actions, we can use an off-the-shelf tracker to track through the videos and get point trajectories. Each trajectory is simply a sequence of 2D coordinates. We then learn a transformer network that takes input the visual features of the initial frame, a language instruction, and the initial positions of a set of query points. The transformer network is then trained to predict the future trajectories of the query points. As the transformer is permutation invariant, we can query any subset of the points in the image frame. Then in the second stage, we learn a trajectory following policy using just a small set of action label demonstrations. Given the current observation, the policy first predicts the future trajectories of the query points and then predict the actions conditioned on that. We conduct our first experiment in simulation for reproducibility. We treat a set of expert demonstrations as a video by masking out the actions. After testing all 130 language condition manipulation tasks, we show that our approach significantly improves over various video pre-training methods and a very strong learning from scratch BC baseline. Furthermore, our trajectory model can be easily incorporated into different policy classes, such as diffusion policies, to further improve the performance. When learning the policies, we can simply query points from fixed grid locations in the image frame and predict their future trajectories. Here you can see that these predicted trajectories model rotation and translation of the robot arm, providing the fine-grid sub-goals to the policy. We also verify that the same setup works pretty well on the real robots and give us consistent conclusions. A really exciting result from our framework is the ability to learn from cross-embodiment videos. For this cross manipulation task, we collect a small number of action-labeled robot demonstrations and a large number of human videos, and we can learn a single trajectory model from both the video sources. The policy learning experiments show us that if we train a BC agent only on the robot data, it doesn't work very well due to the lack of data. However, by utilizing the human videos, we see significant positive transfer and is able to improve the policy performance a lot. We further investigate this learning from cross-embodiment videos with more tasks, including long-horizon multi-stage tasks and two-use tasks, and we see positive transfer from all of them. Furthermore, we can even transfer from videos of a different robot. I'll conclude this presentation with two current limitations of our method. One is that the model is trained only on in-domain videos, and the second is that it still requires some action-labeled demonstrations for learning the policy. I'm super excited to see future works in this direction. Finally, this is joint work with my amazing collaborators at UC Berkeley, Tsinghua, and Chinese University of Hong Kong. If you're interested, come talk to us at the poster session, and our code is also released. Thank you for listening.
So there's time for questions.
Hey, sorry, here. Nice work. One question. If I want to try this in my lab and fine-tune on my in-domain data, how long would it take me, and what resources do I need?
So if you want to try this on your own task, because right now it's not really trained on a lot of diverse data, you need to collect your own human videos and collect a small set of human teleoperation demonstration data. In our case, we find that it can learn with just 10 demonstrations, but if you want the policy to have more generalization, maybe you collect a bit more videos, but not necessarily teleoperation data.
Okay, and what resources do I need in form of GPUs and so on?
I see. So for our real-world experiments, we only train on a single GPU for a few hours. For the simulation experiments with 100 tasks, it takes A100 and a few hours.
Okay, thank you so much.
Next question here.
Can you tell us what's the horizon of the prediction for the point trajectories and how, and the accuracy? I presume accuracy drops over time.
Yeah, good question. So there's actually an ablation in our paper where we show that if the prediction horizon goes to 0, then the method reduces to the naive behavior cloning, and you would basically see the baseline performance. If the horizon is too long, you also see a degradation of the performance because now you're predicting too far into the future. The prediction task becomes harder, and this long-term prediction don't actually help with the current decision making. And in our case, we find there's a sweet spot, maybe around 2 seconds into the future.
We have time for, oh no, we don't have time actually. We thank the speaker, please.
Right. Let's move on to the next paper. Maybe before, we're still looking for our last session speaker. Norman, if you're here, maybe wave at us. Okay, so the next paper is pushing the limits of cross-embodiment learning for manipulation and navigation, and Jonathan's presenting.
Yeah. My name is Jonathan, and I'm presenting our cross-embodiment work. So recent years of research in robotics have shown remarkable progress in training large-scale foundation models for navigation, manipulation, and autonomous driving. And the success of such policies might lead us to wonder a question. Can each of these embodiments actually benefit from this data used to train from other embodiments? And just how diverse can these embodiments be? In this work, we study the extreme end of this question, the transfer of knowledge between real-world heterogeneous robotic embodiments. Specifically, we focus on transfer between manipulators and navigators. While these domains were previously considered as separate, there are many commonalities in their structure. So why might we hope for any form of positive transfer across navigation and manipulation? These domains actually contain many similar sensory motor principles. For example, both domains require the learned robot policy to have an understanding of high-level semantic concepts, collision avoidance, and geometry. For example, consider a navigator and manipulator approaching a strawberry. Both embodiments have to have the same equivariance between pose changes and camera observations. Moving forward, left, and right on the manipulator will transform the observations in a similar manner as the navigator. We use this insight to unify navigation and manipulation into a single goal-reaching task. So we train a goal-conditioned generalist policy that is capable of controlling robotic arms, quadrupeds, mobile bases, drones, and mobile manipulators. And our policy has a transformer backbone and a diffusion policy action head. Our policy is actually trained with a diverse mixture of data. So we get our manipulation data from the OpenX embodiment dataset and navigation data from the GNM dataset, and as well as the BDD 100K driving dataset. So the following depicts our policy performing various manipulation tasks. In each of these tasks, the robot is given a goal image containing a specific object to manipulate. So actually, one of these images in the first-person view is given to the robot. Then the robot predicts n actions into the future to try to achieve that image. The task is considered a failure if the robot manipulates a different object, as you can see in the cluttered grass task. As shown with these egocentric viewpoints, the robot must actually avoid some obstacles in some of these tasks. For example, it must avoid kitchen countertops or shelf panels while moving toward the goal image. In two of these tasks, actually, toy kitchen and novel cluttered grass, the robot is asked to manipulate new objects or act in a new environment. So, for example, in the novel cluttered grass task, the robot does not see the battery in its training set. Our policy actually achieves an average success rate of 71% success over these 5 tasks. We demonstrate the same policy's ability to control navigation embodiments. Given a set of images in the topological map, the robot must actually predict how close it is to each image, as well as a set of waypoints to move to that image. The actions to execute are chosen based on a heuristic on the distances predicted by the robot. We further test the ability of our policy to control more challenging embodiments. For example, this is our policy controlling a unit tree Go 1 and a DJI Cello drone, which was an embodiment not containing the training set. Our policy actually averages over 85% success on all navigation embodiments. So we evaluate over 1,000 rollouts to empirically characterize the effects of data size, model size, and architecture choices. We find that a policy trained jointly on navigation and manipulation has a 20% higher success on manipulation and 5 to 7% higher success on navigation than single domain policies. And we actually have further experiments that try to characterize what type of data leads to better transfer and ablation on goal conditioning, which can be viewed in the paper. Finally, this is a very interesting experiment we did where we showed that our policy can control a mobile manipulator without any data specific to the embodiment. So we actually query actions separately on each of the embodiments. So the mobile base has a separate set of observations as a robot arm, and we get the action separately from these two embodiments, and we can control a mobile base or a mobile manipulator without any data. We believe our work represents a step toward achieving greater synergy between robot embodiments, and we hope that this can actually pave the road to achieving a true cross-embodiment foundation model that can leverage data from all robots and control any robot out of the box in the future. Thank you.
Great. Thanks for the nice talk. We have time for a couple of questions.
Oh, thank you for the talk. I'm here.
Yeah.
So, very interesting, but I wonder, cannot be dissolved with control, knowing the geometry of the robots and say, okay, I know the mapping between the camera direction I need to move and the actions. So what do you think about that different solution? I know that this is about learning, but a classical control approach, will not that work in that case?
Yeah, so this like goal condition policy, I mean, this is just like one set of experiments to investigate this sort of transfer. There are many other sensory motor principles that these like policies need to have. For example, like knowledge about these like, different geometries of the robots need to be implicitly part of the model. If you give the robot actually two goal images where you have like an object that the robot needs to avoid in between the object, in between the like goal image and the current like state, the robot actually learns to avoid the object and get to that place. And I don't think that type of task can be solved with classical control without some sort of like ground truth knowledge about the environment.
Okay, thank you.
We have the next question over there.
Hear me? So, very cool work. I wanted to ask you how much is it depending on the placement of the camera? So I noticed that on all these data sets, and also including the end effector, the camera was always pointing down at maybe an angle of 45 degrees. So I would say maybe it's quite expected that they should generalize. So can you comment on that?
Yeah, that's actually a very good question. And there are works that are trying to investigate different camera viewpoints in the future. But one limitation I would say is that the OpenX embodiment dataset doesn't actually contain a lot of camera extrinsics data. And if we have more datasets in the future that contain camera extrinsics, this mapping would be a lot easier to do and would be more explicit. So there is a bit of a limitation in the type of dataset we're using, but I foresee that in the future we can actually like overcome these assumptions.
But you could actually render new views because you can reconstruct the geometry, and then in principle you can then generalize also to different camera placements, right?
Yeah.
All the information is there actually, I think.
Yeah.
Okay, thank you.
Great. Thank you very much. Let's thank the speaker again and move on to the next paper.
So next we have DrEureka, Language Model Guided Sim-to-Real Transfer by Will.
Hi everyone, I'm Will. I'm a student at UPenn and I'll be presenting DrEureka. So our project investigates how we can use sim-to-real reinforcement learning to learn difficult robot skills with minimal human effort. And specifically, we use large language models to automate reward and domain randomization design, which allows us to learn complex skills like globe walking, where the quadruped must balance on the yoga ball, as well as quadruped locomotion and dexterous cube rotation. These policies were zero-shot deployed in the real world, and we find their behavior is both safe and effective. Now, before we start looking at the method, let's take a look at where sim-to-real stands today. In the past, we've seen numerous impressive tasks achieved by training and simulation, from a dexterous hand solving a Rubik's Cube to extremely robust quadruped locomotion across diverse terrains. But while this framework allows us to train policies in environments faster than real time and with no danger to the hardware, each task must be carefully designed and tuned in simulation. For example, this is a reward function from a past established work, and while each term makes sense, it's difficult to come up with an entire reward along with coefficients without several iterations of reward engineering. And similarly, this is a set of domain randomization parameters from prior work, and again, it's hard to create this without some domain expertise. So given the impressive results in the past, Sim2Real can be potentially applied to numerous robotics tasks. However, it remains limited by the human effort necessary to tune it, and thus we ask the question, can we somehow automate Sim2Real? Specifically, we've seen large language models applied to many parts of robotics and machine learning, from planning to optimization. Here we hypothesize that they can design the reward function and domain randomization components of a Sim2Real system. On a high level, we generate the reward function via evolutionary search, and the domain randomization with a query that grounds the value physics values. We then train multiple Sim2Real policies and evaluate them in the real world. Now I'll go into our methods step by step. First, we give the LLM a task and safety instruction. The safety instruction is actually crucial, and among the different ideas we tried, it's actually the most effective way to guide the LLM to generate a reward that learns safe and deployable behavior. We then use these instructions to run DrEureka, which performs iterations of evolutionary search to find a promising reward function for the given task. DrEureka also gives us a policy trained on this reward. And next, we need the LLM to also generate domain randomization parameters. But we often see that the scale of reasonable values is different across physics parameters, making it difficult for the LLM to generate without additional information. So we compute what we call the reward-aware physics prior, which is essentially a range of reasonable values for each physics parameter constructed by testing the DrEureka policy on different values and measuring success. And now with this prior, we can then query the LLM to output subranges that it deems relevant to the task and likely to occur in real. An example of our query is on the right, where the prompt is in blue and the prior is in green. And finally, with the reward function and domain randomization generated, we can train policies with reinforcement learning and then deploy zero-shot to the real world. We validate our approach on 4 quadruped locomotion and dexterous cube rotation, 2 platforms that have established Sim2Real works. We find that our best policies outperform the human-designed ones, which suggests that the LLMs can indeed generate useful rewards and domain randomization for real-world robotics. And moreover, we evaluate the 4 locomotion policies on 4 different terrains, and our policy is performant across all 4, highlighting its robustness and the effectiveness of its domain randomization. And finally, our globe walking policy can balance for an average of around 15 seconds. In these videos, we tied it to a pole to keep it safe and prevent the robot from going too far. Note that the uneven ground and wind outside also makes this task particularly difficult, and our policy can stay on longer under lab conditions. If we also bring in a human who applies minimal assistance just by holding the leash, the quadruped can stay on the ball for around 5 minutes, traversing an entire city block. Please see our project website for the full video.
Okay.
And next, this is a video demonstrating our policy's robustness as it goes over a curb, walks sideways, and survives the ball being kicked. Note that the yoga ball is also bouncing deformable in the real world, whereas the simulated ball is rigid. These results suggest that the generated reward and domain randomizations has helped the policy successfully transfer to situations unseen during training. And finally, we tried deflating the ball while the policy is still balancing on top of it. And despite the ball becoming more deformable and bouncy over time, we see that the policy still does a pretty good job of staying on. The full video on our website is a bit longer than the one here, and the policy balances for around 40 seconds in total. So in conclusion, we present a framework for automating components of Sim2Real for robotics. Our method is effective across 3 diverse tasks, including the challenging and novel globe walking. Please come to our poster for more details and visit our website linked here. Thank you.
Okay, questions here in the center?
Hi, thank you for an awesome talk. Curious, so the safety seems to come from the prompt and the reward, right?
Yeah.
Constraining what it can do. Do you think that's sufficient, or do you have plans to expand on that?
Yeah, so we actually experimented with a few different methods. The safe behavior most often comes from reward functions that are regularized with like action rate or torque penalties. And we found that if we just ask the LLM nicely, it can generate some terms like that.
Thanks.
Next question. Yeah. It's not. Yeah.
Thanks for a great talk. So first question, I saw you have a benchmark or baseline compared to human tuning. You show like your method outperform the human performance. So my question is, what kind of human? Is kind of robot expert, or you just find a normal human? Because from your performance, look like locomotion is maybe not a state-of-the-art performance.
Yeah, this is a prior work. So for locomotion, it was rapid locomotion, and for dexterous cube rotation, it was cube rotation for the leap hand.
So you mean you follow maybe some previous papers?
Yeah, previous papers.
Okay, yeah, okay. And second question is like, so looks like maybe your LLM, you do not input any robot physics related information. So how, I mean, how about its generability to some other task?
Sorry, could you repeat the
My question is like, so for your input, looks like many of the physics-related, for example, the robot, like motor limits and torque limits, and also size, such kind of information looks maybe not explicitly inside the input. So how, I mean, what do you think the generability of this method to many different types of robots?
Yeah, so in our prompt, we don't actually give that many robot details. The robots we use here, I think, are pretty common, so we hope that the LLM has, some general idea of like the Go one and the leap hand. But I think the tasks also don't really push the torque limits of the robot, and the reward function that it generates doesn't really rely on those specifications either.
Yeah. Okay. Thank you. Great work.
Thank you.
Yeah.
Okay. We thank the speaker, please.
Great, and our next paper is Set It Up, Functional Object Arrangement with Compositional Generative Models. And I think Yiking is presenting.
Yes, thank you. Let's recall how we humans instruct others to set up dining tables. So rather than specifying the precise pose of the chopsticks or the plates, we focus on the overall functionality of the arrangement, such as a Chinese dining table for two. So in this work, we study how to ground this under specified instructions to object poses, such that the arrangement aligns with the overall purpose of the instruction. And we term this as the problem of functional object arrangement. Can we learn this from data? Unfortunately, no, primarily due to the issue of data scarcity. Think about the huge space of free-form instructions and open set objects to the possible object arrangement. The annotated data for our scenario is quite limited, and gathering such data actively is expensive. So the real challenge is, can we learn this mapping from a limited amount of data, but generalize to a wide range of objects and instructions? Our insight is that, instead of directly predicting the object poses, let's predict an intermediate graph of abstract spatial relationships. This graph abstracts away the object geometries and only predict a simple compact set of abstract relationships. The beauty of this intermediate prediction task is that now it naturally breaks down the task into two phases. First, we predict the graph using semantic inference based on the instructions and object types. And then we ground the predicted graph into the precise object poses by considering their geometries. So specifically, we use a large language model to induce a Python program to generate the abstract graph. Guided by human-crafted high-level task routing on only 5 examples, the program induced can generalize well to new instructions and object sets. And we then employ compositional diffusion models to ground the predicted graph. We pre-train individual models on each relationships using only synthetic data and compose them flexibly during the inference time to ground any abstract graphs. And via this decomposition, our Set It Up is both data efficient and generalizable. And now we are ready to define our problem formally. Given an underspecified instruction and set of available objects, we aim to generate object poses such that the arrangement aligns with the intended purpose of the instruction. But instead of using lots of annotated data, Set It Up only needs 2 pieces of information. First, it's a human-specified high-level task routine written in Python code, the skeleton, and 5 instruction arrangement pair examples. And let's now talk about the first component. How do we predict the abstract graph using large language model? The semantic inference, in fact, involves multiple steps if you think about it. On a super high level, we need to first interpret the instruction and ground it onto the current object, and finally generate the graph. To improve the reliability of this generative process, instead of directly prompting large language model, we utilize it to generate a Python program that follows these reasoning steps sequentially. And to achieve this, we ask human to offer a high-level task routine guidance and only 5 examples. The large language model uses code commands and the contextual examples to implement these functions. This procedure guidance enables a large language model to generate a program that generalizes well to novel instructions and objects from only 5 examples. Next, let's talk about how to ground this graph using compositional diffusion models. Given a graph consists of multiple relationships, we retrieve and compose the corresponding diffusion models trained to propose the poses for individual relationships only. Then we perform MC-MC sampling on the aggregator score of these models to jointly propose the object poses. Each diffusion model, the diffusion model for each abstract relationships are learned independently from synthetic data, and we trained a library of 24 types of such abstract spatial relationships to cover a wide range of object layouts. We assess arrangement based on functionality and physical feasibility. As an example, let's consider Chinese dining table setup. Without any decomposition, end-to-end diffusion, and direct large model predictions do poorly on both counts. A naive decomposition with no program guidance improves functionality slightly, but still falls short. And our setup excels in both axes due to the strategic decomposition, guided program induction, and compositional diffusion models. And we show we can generalize the novel instructions and object sets over a study table, coffee table, and dining table setup. So in summary, we propose an important task called functional object arrangement, which enables the human users to instruct the robots more naturally. And we also propose set it up to solve this task. And the key idea is to use an intermediate abstract graph to decompose the task into 2 simpler problems, which we can more effectively inject priors and more efficiently use the existing sources of information, be it a pre-trained large language model, a small amount of contextual data, and a lot of synthetic data. Thank you.
Thanks for the nice talk. And are there any questions? No questions? Oh, there in the center.
Thank you very much for a very interesting talk. I'm wondering about the application, because I would probably set up my table differently, but I see, do you plan to extend this, for example, for assembly operations or things where there are important, precise relationships on the positions of parts to be mounted, for example? Have you tested on settings in which the geometric relationships need to be very precise?
Right. Are you talking about now, if we talk about left off, whether it's like 2 centimeter or 5 centimeter, we have no control over that? Oh, that's a really good question. So if we can do that, we get closer to what human really wants. And currently, we decompose that into semantic reasoning and geometric reasoning. And currently, the pipeline is not able to do that. But there's a simple trick. So when you're predicting the abstract graph, then you try to give some additives to the symbolic relations you predict. Then you train diffusion model to do that. To predict like a little bit or further. And what is nice about diffusion models is that because this is just like simple affine transformations to the object poses. So it's fairly easy to train these diffusion models together with left off or right off. The only caveat is that you can't train this independent from any other symbolic relations. You need to train these additive like models together with left off, right off, but you can do that.
Thank you very much.
Right.
Okay, for the interest of time, we will continue. And thank you very much. And we now have the last talk of the session, Keypoint Action Tokens Enabling Context Imitation Learning in Robotics by Norman DePaul.
Hi everyone. I'll present Keypoint Action Tokens, a method to enable robots with in-context learning. And I'll show what I mean by this. This work was done in the Robot Learning Lab at Imperial College. So CAT can learn everyday tasks with as few as 10 demonstrations. Up to now, nothing unusual, right? The way it learns, although it's quite unusual. So thanks to in-context learning, we can provide the demonstration to the robot that can be then be deployed immediately without any weight updates. And to do so, we use off-the-shelf language models. So the goal is to use this LLM's pattern completion power for low-level in-context imitation learning. And I'll give more details now. This is justified by two observations. The first one is that language models can be general pattern machines. This paper from Google DeepMind demonstrated that language models can understand more than just language, and also relatively arbitrary numerical patterns, or in particular, patterns of tokens. So completing trajectories, doing some simple reinforcement learning, and things like that. Quite surprising. The second observation is that vision foundation models compute strongly transferable and general representations of the world. Here, I'm showing from the Dino V2 paper some PCA representations of very different objects, and you can see how they share the semantics by similar color being put on similar parts of the objects. Why is this interesting? Because it means that we can represent an observation with a few key points that are both semantically and geometrically interesting, having a very strong information bottleneck. So we know which part of an object are interesting. We therefore create a language of observations and actions that an LLM can ingest and understand, and we call it Keypoint action tokens. I'll show now how the framework works. This is how we give a demo. So the first step is that the robot extracts visual key points using Dino features. Their coordinates expressed as text become key point tokens and added to the prompt as input. This is all text in the prompt. After this, the user moves the robot to give a demonstration also with teleoperation. And so the robot poses are represented as a triplet of 3D points fixed in the end effector space. These triplets are the action tokens. These triplets are in the same Euclidean space of the key point tokens. A demonstration is therefore a trajectory, a list of these poses of this triplet that are, again, just numbers. And we put these numbers into the prompt as output. So each demonstration in the prompt is simply the key point tokens and the action tokens. The language model should then find the pattern that relates these inputs to these outputs, and at test time, generate trajectories that follow the behavior. At test time, indeed, we start again by finding new key point tokens that are put again as 3D coordinates in the prompt that now has all these demonstrations. The difference is that now the language model auto-regressively generates a trajectory of action tokens, so of poses. This is what the LLM is proposing the robot to do. These action tokens can be then represented as poses and simply executed by the robot. This is another example of another task. So it's also non-prehensile, so it's also not entirely trivial. We find these key points, we put it into the prompt, the language model proposes a trajectory of poses for the robot, and then it executes it. So the interesting idea here is that all the models we use were off the shelf. We use Dino, which is off the shelf, and then we use GPT in this case, but any large language model can be used. So it enables you to do imitation learning, and as you saw, low-level imitation learning without any weight update. Please check out our website for the paper, the videos, and more visualizations. Thank you very much.
Okay, we can take a couple of questions.
Thank you very much. Nice talk. One question: you have a very dark background, and you pretty much made that probably to make sure that you see these features. So what happens if during the demonstration you lose track of one of the things you need on your object? So then only, like, let's say 3 out of the 6 points on the object are being tracked.
Yeah, so the way we represent the imitation learning problem in this case, it's more similar to what they do, for example, in diffusion policy, where you have an initial observation, and then you come up with a plan, and you execute it, and then if you want, you can replan. So there are, let's say, 1 observation and then 10 actions. So you basically don't lose track of the object because you first execute like several actions. In that case, you always find the K key points you want. So the worst thing that can happen is that one of the key points is not exactly where you want it to be. So if the object is partially visible, one of these key points will be in a different part of it, that it's geometrically similar but not exactly that. I'm happy to talk more about this at the poster because it's an interesting question.
Okay, next question there.
Thanks for the talk. So when we look at the key points that are being evaluated, do you actually take into account the robot kinematics or singularity in actually tracking them at execution time?
No. So basically, we just assume that there's a low-level controller that handles the robot following all these poses. It's a very interesting problem, but as we know, robotics is a large vertical stack of modules that have to collaborate. So we just assume that if I ask the robot to follow a pose, there's a low-level controller that tries to avoid singularities by, I don't know, working in the null space of the robot. So long story short, we don't tackle that, otherwise we'll have to tackle too many problems at the same time.
Okay, and last question there. We don't have time, only one question, so sorry.
I'm happy to chat also the poster, which is right now, so you can find me there, unfortunately.
So let's take this last question there. And
Okay, yeah, I noticed that most of your tasks have like rigid body manipulation tasks, but I'm wondering what happens when it's a lot harder to predict key points into the future when like stuff like deformable objects or like, you know, precise tasks where like it's not only the robot moving in free space. Like, how would you deal with those cases?
So you said the first part, deformable object, the second part?
Or just like more complex tasks where the robot is not just moving in free space. They might be hard to like predict these like key points into the future.
Yeah, there are basically two different questions. Deformable objects are not really a problem for these key points. Like you can also use plushes or clothes. We tried and it generally works quite well. Obviously, it's not optimized for deformable objects, but it kind of works. We always assume the robot moves in free space. So in this case, yeah, if you mean like obstacles and stuff, for the moment we ignore that. But yeah, we can talk about this later.
Okay, thank you very much, everyone, for attending the session, and now we can go for the coffee break.
Okay, hi everyone, welcome back from coffee. I was told we have to be on time because we have a long and packed afternoon program today, so I'm going to do my best to keep us on time. I'm Jordan Boyle from Industrial Design here at Delft. I'm chairing this session along with my new friend Abdullah Mustafa from AIST in Japan. And so this is the session on robot design. Very much looking forward to it. And do we have our first paper is called Contact, Continuum Emulated Soft-Skinned Arm with Vision-Based Shape Sensing and Contact-Aware Manipulation, which is being presented by Tuan Nguyen. Thank you very much. Take it away.
Thank you. Okay, can I start? Okay, hello everyone. My name is Tuan Nguyen, and today I'll be talking about our work, which is on the contact system. So onto the motivation, we all know that continuum robots and soft robotics in general are very dexterous. They are flexible, so they are perfect for tasks requiring movement in narrow space and there are a lot of obstacles. However, integrating sensing into these robots can be quite challenging because they can form complex morphology with a lot of bendings and curves. So in our group, we're recently working on this skin-based, vision-based tactile sensor that can, so the question here is, can we combine this technology with continuum robots to provide them with both the shape and the touch sensing? Yeah. So our objective is to realize a vision-based tactile sensing solution for continuums and redundant robots, which we call the contact framework. And here's a briefly flow work of this. And about the hardware design, we use a soft silicone skin which has markers inside, so we can track its movement, and this skin can bend accordingly to an articulated robot arm. So in this recent work, we are using this just a simple robot arm for evaluation, but ultimately we will apply our method to like continuum and soft robots. And here's when everything is put together. You can see there's a camera that can observe the movement of the skin and the markers also. And we can also attach several of this modular unit into a robot arm. Here's the sensing model design. the camera captures the image, and we use 2 neural networks to provide the according tactile information, which are the shape of the robot and also the contact location and magnitude. And to train these models, we use this simulation platform. So we use the SOFA framework to provide the mechanical properties, which is like the deformation of the skin, and then we use Unity to capture the images. And to minimize the sim-to-real gap, we use the randomized transformation, which we shift and rescale the image. And after that, we zero-shot deployed our models on the real robot. And here you can see the result for a single unit and for like a robot arm. Here we just use the same models for several different units. And we didn't really need any fine-tuning. And so we also made this admittance-based controller. Using the tactile information, we can control a robot so that when it hits some obstacle, it can move back, and so there will be no further damage. And we can also tune this controller so to make the behavior of the robots better. And here's when we put together an arm. You can see that when I push into the robot, it changes its trajectory, so it can still complete the task. And after that, we test our models on this soft tendon-driven robot. So the result is quite promising. This is just an early test, so our model can tell the shape of the robot. And I would like to thank our team and our sponsor. And thank you, everyone. If you have any comments or questions, please come to our poster.
Thank you very much. Do we have any questions from the audience? Please wave vigorously. Okay, yeah, there's one over there and then one over there as well. We'll start on this side. If you could take a mic down there.
So if I understood, the camera is on the top looking down through the soft tube. Do you have occlusion issues as you rotate?
Yes, thank you. So there is actually occlusion, like quite a lot of occlusion. So that's why we also include the occlusion into the simulation. Like in the simulation, we also have like the robot arm itself inside. So we also capture the simulated image with that robot in mind.
So if the contact happens at the point of occlusion, you may still be able to detect it because there's deformation elsewhere?
Yes, so actually, even if the actual contact point is occluded, the neighbor section will have some deformation, so we can still use that information for the detection.
Great, thanks.
Thank you.
One more question there.
Yes.
Yes.
Thank you so much for the talk. So I'm more curious about the material side. So as I know, this is kind of a little bit similar to the previous gel site. So I'm wondering whether you have to make special accommodation, modification on the gels or the reflective layer in order to handle this curves situation.
Thank you. So actually, we just use like normal silicone. This is Dragon Skin 30. So there isn't anything special about it, actually. So, so to make it bendable, we just design it so it has this bellow shape as you see in the design. Yeah. Thank you.
Okay, thanks very much. Let's thank our speaker one more time and find him at his poster if you have more questions.
The next presenter is Jinjong Tian, presenting his paper, Function-Based Sim-to-Real Learning for Shape Control of Deformable Freeform Surfaces.
Hello. Can I start? Okay. Hello, everyone. My name is Jinjong Tian from the University of Manchester. Today, we'd like to present the function-based sim-to-real learning for deformable freeform surfaces. So sim-to-real is actually a very critical in recent robotics area for rigid robot, for tactile sensing, and also for soft robots. Especially this kind of difficulties come to several reasons. For example, the reduced simulation model, the manufacturing accuracy, and actuation and control. Okay, so reality gap exists for soft surface deformations. So in simulation, we establish the simulation, and also we construct the physical setup, and we apply the same actuation, and we find that we scan the physical models, and we find there's a scene-to-real gap exists, and we plot a color map. And also, scene-to-real learning is challenging for soft surface morphing. Actually, the core of scene-to-real is to learn a mapping that is from a simulation surface, which is a high degree of freedom, to a real surface, which can be calibrated by a sparse degree of freedom of motion capture markers. And the difficulty is we need to somehow using the sparse marker to calibrate the dense degree of freedom. And during capturing, it's actually usually the incomplete frame usually happens. So the second challenging is we need to incomplete the frame with the missed markers. And also, we are not calibrating a single surface. We are actually calibrating a set of surfaces, which is different mapping for different surfaces. And our scene-to-real approach, actually in the previous method, they usually learn a full set of surfaces, the degree of freedoms. We can know that from the left is all set of all points on the surface, and right is all set points on the surface. It's directly learn shape-to-shape mapping, and the input and output, they are fixed degree of freedoms, and this training needs full set of markers. And in the right-hand side, in our method, we actually decompose all the points into a single point enriched by a global surface feature, and this mapping is actually parameterized by the RBF coefficients. And the input is a single point enriched by a global surface feature. And you can see here, every time we only input a single point on the parametric domain, the UV parameter, and we enrich by a control point of the surface and the UV sets of the markers. These serve as a global surface features. And we send into a B-spline base shape decoder to be a point on the 3D space and the kernel centers on the 3D space. And then we're using an RBF network to learn a coefficient of the RBF space, and we send into a differentiable RBF space wrapping to output a new point on the space. And this is actually our whole pipeline. And the keynote is the first, we don't directly learn the mapping from the shape to shape. Instead, we learn the RBF function space, which is actually the Gaussian kernels, their width and height. And also, this is analytical differentiable and the better training result with less data. And how to encode different shapes, because we want to learn a set of shapes, we're using global surface feature as a Latin code. And this kind of architecture enables us to learn all frames, including those with marker missing issues. You can see clearly here, we somehow using this architecture. Yeah. And our scene-to-real learning can be used in the gradient can be computed end-to-end, and this gradient can be used in an inverse kinematics solver, and we have verified this on a physical setup. And you can see here, we show 3 target models we want to approximate. The red one is the deformable, the simulation one, and we approximate the target model. And we then scan the real physical models and compare with the target model. And we also plot the error color map. And this one, we also test up to 10 target models, their performance. And we can also see the efficiency is speed about 3,000 times compared to our last work. Because we are learning actually a model inside. Because previously we using a model-free method. Thanks for your listening, and welcome to our poster. And also, we bring our physical setup into the poster session. You can come and see our demo. Thank you.
Thank you for the presentation. Any questions?
Middle back.
Hi, thank you. I was curious if you could provide some motivation behind the mannequin itself. What is that used for?
Yeah, it's actually when we are like calibrating the surface deformation, there are two ways. We are using the marker. One way is using the marker. Actually, there's during occultation other issues, we cannot guarantee every time we have a full set of markers. So if in this case, we usually like abandon some frames, which is like not very efficient. So we like, this is the motivation. We want to use all frames.
Sorry, that's great.
Yeah.
Your method's awesome. I was wondering what the mannequin was for, right? It's not for manipulation. It's not a robot that can go up the stairs. So what is that used for? I'm just curious.
Yeah, so we have a like collaboration with a startup company called MikoTax. And actually before the presentation, I have been their company, and we're using our deformed mannequin to deform to different human body shapes, and we fabricate some sustainable material on top of it. And after like 3 hours, we can directly peel off the garment from our deformed mannequins. And our recent research will somehow release like some months later. Yeah.
Okay, top secret, got it.
To stay on time, let's thank our presenter. And
Cool, so next up we have Simon Gwist, who's going to tell us about safe and speedy tendon arms. And maybe you want to use the handheld mic if you want to be able to move around. But yeah, over to you.
Hi, so yes, I'm presenting safe and accurate at speed with tendons, a robot arm for exploring dynamic motions. Humans are very good at learning to perform highly dynamic and precise motions. Replicating the same performance with real robots still continues to be very challenging. So our question here is, how can we better build robotic hardware that facilitate learning these precise and dynamic motions? Commercially available robots usually fall in two categories. They're either fast and rigid, or they are slow and safe, like collaborative robots with collision avoidance and mitigation that can work alongside humans. But can we find a middle ground? Build robotic hardware that is more dynamic while still being safe. One such system that tries to find this middle ground is our pump-driven robot arm. It is actuated by pneumatic artificial muscles that can generate high forces and offer robustness and impact resilience. Because it is tendon-driven, the muscles are on the base, and the arm itself is lightweight, making it more safe, both robot safe and also safer to be around humans. But this kind of system also has some limitations. First of all, there is high friction and stiction, in a large part due to the tendon drives, and some other problems are time-dependent changes, for example, due to temperature, breaking parts, and unstable pressure supply. All of this makes learning of control quite difficult. And this is why we decided to design and build a completely new system. We focused on simple kinematics and design to make it easy for us and for other researchers to adapt and replicate the system. And while we use muscle actuators, the arm itself could also be combined with different actuators like motors. To make control easier, especially with the tendon drives, we focused a lot on reducing friction. And two of the biggest changes here was using ball bearings and our newly self-designed Bowden tubes. Here you can see our design. While for the old system, the arm itself was a purchase component, here we designed the arm completely by ourselves, and most of the parts are off the shelf or 3D printed, making it cheaper than many other systems. And here on the top, you can see our redesigned Bowden tubes with an inner tube and custom 3D printed outer support elements. Besides open sourcing hardware and software, we have also published a data set of about 25 days of uninterrupted movement. To validate our design, we performed several experiments. Here is the first experiment. So to compare the friction in the Bowden tubes with the old system, both types are actuated by rapid switching muscles, and then the image of the thermal camera, and also in the temperature evolution over time, the new Bowden tubes show significantly lower temperature, which is a good indicator of less friction. Another way to evaluate our design choices, including friction, is to look at nonlinearities. Here we employ system identification in the frequency domain. The first row is the amplitude response. The second row is nonlinearities, and to make them comparable, we can look at the signal-to-noise ratio, and here we can see that the new system is significantly more linear, especially at lower frequencies. Then here on the right, you can see measures from the long-term experiment. Here at frequency intervals, we look at the position that the arm reaches with a fixed set of target pressures, and both the relatively stable mean and the standard deviation indicate consistent performance throughout this experiment. One big motivation for this arm was being fast and dynamic while also being safer. So here we are crushing the arm into a PILS robot measurement system, and compared to traditional robots, we have much less force for the same impact velocity. Let's look into how we can solve an actual dynamic task with this system using reinforcement learning. The task here is table tennis smashing, and during training, the robot is real, but the ball is simulated. And our reward function takes precision at maximum ball velocity into account, and compared to the old system, with the same hyperparameters and everything, we achieve significantly higher speed while also being more accurate, which demonstrates well the benefits of the design for these dynamic motions. And then after training, we can use this policy also with field balls, and we reach ball velocities of up to 20 meters per second. This was very much a big group project. Thank you to all my co-authors. Here you can find the website, and happy to take questions.
Thank you very much. We've got one question over there.
Yeah, thank you very much for interesting work, Simon. So I have two questions. First, you said it's safe. Do you have any theoretical justification for that? Why is it safe? And second, from practical perspective, how reliable tendons are? Do they break often, or when you do experiments, if you elaborate on them? Thank you.
Regarding the first question, our main argument for it being safe is that it's much lighter than other arms that can do the same dynamic motions. So in case of impact, there is less bad things that can happen. But still, for the high velocities, it's still not. You still have to probably add some other safety measures. But then it's similar to also a human arm hitting something with high velocities. Regarding the second question, in terms of reliability, I think in general, building a tendon-driven arm, also for these dynamic motions is very challenging. So our argument is that we are more reliable than other systems. And we also showed this in a long-term experiment, but there's still some challenges in making it completely reliable.
One more quick question over there.
Hi, it seems really impressive. I have one question that is, in one of your plots, I see the accuracy of angles being around 2 degrees. Is that correct?
Yeah.
Wouldn't that cause almost 10 centimeter error at the end effector? Is that the case sometimes? And how to fix it?
In terms, that it will definitely be larger at the end effector. But in that case, it was also an open loop motion. So if you put a controller on top, then probably you can reach higher accuracies. This was just to evaluate that the performance that the system doesn't change over time too much.
Okay. Just a quick follow-up. Are there any sensors on there right now, or is there a plan in the future?
The main sensors are just joint position measurements.
Okay, that's good enough. Yeah, thanks.
Okay, thanks very much. We'd better move on. Let's thank our speaker again. And do we have anyone from paper 4 here? Yes, okay. And are you Luke? Yes. Yes, okay, great. Thank you, Luke. Step right up. Luke's going to be telling us about evolution and learning in differentiable robots.
That's right. I'm Luke. I'm going to talk about evolution and learning in differentiable robots. So I think many of us here are inspired by the forms and functions that we see in the natural world. For example, on the slide you see several different diverse and sophisticated biological machines, all of which came about through a large-scale evolution and learning process. And we applied a similar idea to robot design. These are some of the robots that we discovered. Our methodology joins morphological evolution with massive scale gradient-based learning and we find that we're able to increase the scale of robot design search by orders of magnitude. These are some of the bodies in motion. Each of these is modeled using a mass spring system, and the bodies operate with a fully closed loop controller, which I'll discuss in detail later. As I said, the body is evolved and the controller is learned. So let's take a look at how the algorithm works in detail. The first component is the evolution of morphology. We start by randomly sampling a population of robots, and each of these produce offspring through morphological mutation. The second component is learning. Each robot undergoes a period of learning in a massively parallel differentiable physics simulator. Zooming in, we can see that there's a neural network that controls actuation through simulation, producing behavior, and the simulator differentiates a loss function to produce gradients for improving future behavior. After learning is complete, the best robots are selected to move on, and they form the new population. Then this process is repeated 1,000 times over, evaluating around 10 million robots within a single run. Ultimately, we selected one design from simulation and we manufactured it, demonstrated an effective sim-to-real transfer, and I'll discuss this in some detail later. So returning to the mass spring system, each of these purple masses corresponds to a proprioceptive sensor that's measuring velocities and component displacements. The gray links are passive springs, the light green links are active and expanding, and the dark green are active and contracting. Like I said, this is a closed loop system, unlike most evolved robots. So each spring in the body receives motor control signals. Each mass in the body is a proprioceptive sensor. There's a set of sinusoidal waves that serve as a central pattern generator, and these both provide input to a neural network, which then produces motor output in order to close the loop. What we found is that evolution produces what we're calling increasingly differentiable robots. So the y-axis of this plot is measuring the performance of robots in terms of their body displacement, and the x-axis is measuring evolutionary time in terms of the number of morphologies seen so far. The light green line shows the initial performance of robots with a random neural network controller, and the dark green shows optimized performance after learning. The increasing discrepancy between the initial and the optimized performance indicates that evolution is discovering body plans that are more and more amenable to gradient-based optimal control. Well, control, not necessarily optimal, but learned control. Hence the phrase increasingly differentiable robots. Now this is one body that we would say is not differentiable. The robot undergoes 35 iterations of learning. Each of these green lines corresponds to a center of mass trace, measuring how far the robot moved. And you can see from the beginning to the end, it cannot locomote very far. These next set of robots that you'll see here are increasingly good learners, but relative to the population at large, we would not say they're particularly high performers. On the bottom row, we see some very high performers. These robots all begin with very, very low behavior scores and improve dramatically through learning. We would call these robots very differentiable. Unlike most work in differentiable simulation, which has been restricted to flat terrain, we also investigate rugged environments. So here, the mass, when a mass contacts the ground, the friction force is computed dynamically. However, the simulator remains fully differentiable, allowing these robots' control policies to be optimized end-to-end with gradients that propagate through ground contact. And finally, coming back to the sim-to-real, the 2D simulated robot was extruded into a third dimension for manufacturing. We used shape memory alloy springs for the active components, and the learned actuation pattern was manually transferred to the physical machine. We found that under a fixed number of actuation cycles, the simulated and the physical robot traversed a similar distance, and that in a control experiment where we removed one spring, the physical robot this time locomoted in the opposite direction. Thanks for your time, and I'm happy to take any questions.
Any questions?
Thanks for your talk. It's quite impressive. I'm wondering, have you included self-collision into your evolution?
Sorry.
Okay. So do you think we will have some influence on your performance?
By modeling self-collision, you mean?
Yeah.
Yeah, so we currently don't model self-collision, but it's something that we're exploring in future work. Okay. I suspect that it's essentially just a trade-off in computational overhead. So we're certainly working on prototyping physical systems that we can create a tighter coupling for sim-to-real transfer with. Of course, in the physical world, self-contacts are implicitly modeled. So it's definitely of interest to us, but currently we don't have that supported in this system.
Thanks for your answer. Yeah.
One more question over there.
Very cool idea, thank you. Quick question, is there any energy involved into the selection? So I mean, like an evolution, we have locomotion, which is energy efficient. Is it something you are taking care of?
In terms of the selection force?
Yes.
No, the selection is strictly in terms of the learned locomotive performance.
Thank you.
Let's thank the speaker again. The next paper is construction of a multiple degree of freedom underactuated gripper with force sensing via deep learning. Yes, presented by Hushu Dong.
Good morning, everyone. Today, I would like to introduce a gripper with force sensing by deep learning. The content includes motivation, methodology, evaluation, and conclusion. A fast-growing embodied AI allows this humanoid robot to perform dexterous manipulation, which is extremely possible. From these videos, we are thinking, can we use an actuated gripper to replace the humanoid robot hand? However, the existing unactuated grippers emerge with a few issues, such as low payload and insufficient force sensing. To solve these issues, we present a novel gripper to realize force sensing by deep learning without any force sensor, which is named GR-Robot1. This gripper has 2 3-joint fingers to offer peripheral grasping stability. The novelty is that we present a mechanism stacked by double 4-bar mechanisms to do the coupling and discoupling motions. The theoretical model of kinematics and power transmission is established to calculate the position and the contact force. Achieving the Jacobian matrix and the transmission matrix, we can guide the torques and the contact forces. Actually, we provide the first solution by deep learning model integrated with mathematical statistics to realize force sensing without any force sensor. According to the remarkable current changes of the actuator, we can predict the transition status of the parallel grasping and enveloping grasping. The LSTM model is adopted to predict the first joint angle during the grasping mode switching. And then the deviation between the actual value and the predicted value is made up by a fitting method. Also, we conduct a lot of experiments to evaluate the performance of a proposed force sensing methodology and the payload of this gripper. The average deviation rate of force sensing is around 2%. The payload of this gripper is around 350 Newton. Moreover, we enable this gripper to grasp some objects with force feedback control. After building the relationship between the elastic ring deformation and the grasping force, we allow this gripper to grip an object and then measure its deformation. The deformation is within the standard range. From this video, we can see there are 4 kinds of experiments. Parallel grasping, enveloping grasping, grasping regular shaped objects, grasping irregular shaped objects, such as mouse and glasses, grasping fragile objects, such as paper cup and potato chip, using tools to do some works. Actually, this gripper is superior to robotic cube on payload and force sensing capability. So, a very promising strategy is to use artificial intelligence to enhance the capability of robotic grippers. Thank you very much.
Thank you. Question in the front?
Hi. Great work. That seems really impressive, gripper. There's a question that you are trying to use AI for force estimation, right? And with the input being the current and the derivative of current versus time. Is that correct?
Yes, correct.
But then I also see the graphs like, are there any advantages of using AI versus conventional techniques? Have you compared them? Like just linear interpolation, for example.
Yeah, good point. Actually, you know, without any force sensor or tactile sensor, this method has solved a few issues brought by tactile sensor. This is a principle, right? Yeah. I mean, if you use this AI method to solve this issue, you don't need to put any force sensor or tactile sensor on the gripper. So this is the big advantages.
Okay, thank you.
Any second quick question? In that case, let's thank our speaker again and post a session later. And yeah, next up we have our question asker, Xing Xian Wang, who's going to tell us about a single actuator micro aerial vehicle.
Can I use this? Okay, hi. Hi, I'm Jingxian Wang, and on behalf of my co-authors, I will be presenting our work on single-motor nano-area vehicle with novel peer-to-peer communication and sensing. For swarm robots to collaborate, they usually need to communicate with their neighbors and sense their neighbor's position. However, this task can be hard for nano drones. People typically use external tracking systems to track robots' position. However, these systems are complicated and are inherently centralized. There has been recent work that tries to use onboard systems, such as depth cameras or Lidars, for these tasks. However, they're usually bulky and heavy and requires a lot of computational power to work, which is usually not available for nano drones. So in this work, we create a communication and sensing system that is fully decentralized, simple, small, and lightweight, and also computationally inexpensive. So here's our drone, the MP3. It's small enough to be held in my hand and weighs merely 20 grams. Our drone has a single motor, so as it spins, it spins around its geometric axis at around 25 rotations per second. And we'll soon see how we can take advantage of this behavior to achieve omnidirectional sensing and communication. So here's our drone flying. Okay, we'll start with the 2D case. Here's our MP3 drone, and we put a sensor on it that has a linear field of view. As our drone spins, the field of view will scan through the transmitters at T0 to T2. Assuming everything is fixed, we can compute the angular velocity of the drone as well as the angle between the two transmitters using the shown equation. Now, if we put 2 sensors on the drone at different positions, then these 2 sensors will see the same transmitter at 2 different times. Then we can determine the distance between the transmitter and our drone using parallax. In reality, our drone is operating in 3D space. So instead of the linear field of view we talked about before, we'll need to use a planar field of view instead. We can accomplish this by adding an aperture in front of our photodiode sensor that can block its view. Now, imagine that we have a second sensor at the same position but with tilted field of view. Then, if there is a transmitter that's not on the same horizontal plane as our drone, these two sensors will see this transmitter at two different times. And we can similarly use this time difference to determine the elevation angle. In reality, this is our drone, and we use two sets of IR LEDs as transmitters. They can transmit encoded IR pulses to facilitate communication. If we switch to the exploded view, we will be able to see the photodiodes that are used as sensors. They're hidden behind apertures to mimic the planar field of view we've talked about before. We use the left and right sensor for distance, angle, and angular velocity sensing. And if we take the average of their readings, we basically emulate a sensor at the center, but with vertical field of view. That virtual sensor, combined with this sensor in the middle with tilted field of view, can give us the elevation angle reading. So with peer-to-peer distance, bearing, and elevation angle reading, a drone can determine its own global position by referencing to neighboring transmitters with known global position, and then further use that position information for control. Here's a position holding experiment, where the purple circle shows the beacon's position and the red dot is the target position. As we can see, the drone can hover, and it can determine its own position down to 5mm accuracy by referencing to neighboring beacons and communicating with them, and also can hover within 3 centimeters of the set point using the localization information. This result is quite good considering MP3's complicated dynamics. We set out to explore the peer-to-peer communication and sensing capability. So in this experiment, the drone on the left is actively receiving message from the drone on the right and also determining the relative position of them in order to facilitate localization and control. In fact, if the right drone does not exist, the left drone won't even be able to hold its position because it will only be able to look at the leftmost two beacons and will not be able to obtain a good enough position estimate. So in this work, we proposed a peer-to-peer communication and sensing system applicable to nano UAVs and built a 20-gram drone based on the system. In the future, we plan to improve communication, sensing, and control so it can fly better, add environmental sensing capability to make it sense and interact with the external world, and develop swarm localization algorithms. Thank you. Please check out our posters.
Great work. Question at the front.
And another one in the back there.
Thank you. Great work. Very impressive. Really love it. Just a quick question. What do you think of maybe some application for this one? Maybe some very interesting application.
Yeah, that's a very good question. So we envision this as a way of creating the first swarm of robots that can actually physically interact with humans. So when you see drone shows, they're often high in the air, right? But we want to create a system that's more approachable to people. That's one goal. And also to explore different varieties of swarm algorithms on this platform.
Thank you. Hi, thank you for your talk. So I'm wondering, since you mentioned you are using the IR as the mechanism for sensing.
Yes.
So if the external environment, light source environment is complicated, so I wonder whether there will be any disturbance, or are you going to...
I see. Actually, this system is made to be very, very robust. It can work in a variety of IR conditions, and we never have a problem with the external interference, including but not limited to sunlight, flashing lights, or even IR controllers.
Thank you very much. Maybe we'll move to the next speaker.
Please check our robot during the poster session.
Yes. Our final presentation is Design and Control of Bipedal Robotic Character by Rupin.
I'm with Disney Research, and I'm excited to talk to you today about the expressive bipedal robotic characters that we built. And our goal here was to really create characters for entertainment and not some robot that goes and do some industrial tasks. And our robots are controlled by a remote puppeteering interface, which allows us to create interactive performances on the fly. We began this project by iterating between mechanical design and exploring animations. And the walking animations shown in the top left are produced by our custom gate generation tool, which uses some model-based control at the back to enforce physical constraints. But we also use some more free-form animations, as you can see in the top right. And we use these tools to study the movement of the character and estimate kinematic and dynamic requirements. The final robot has 5 actuators in each leg and has 4 actuators in the neck. But it also has a set of show functions shown in green. This contains speakers, actuated antennas, illuminated eyes, and a headlamp. And these show functions are controlled elements of the robot that don't really contribute to its dynamics, but they play a key role in expressing character. And finally, the onboard PC, battery, and other electronics allow this robot to freely roam for up to 1 hour. We use reinforcement learning to control our character. And from a high-level point of view, we train a policy to receive some high-level commands together with the state and directly output actuator commands. And in our case, we will actually train multiple of these policies and switch between them. And to train the policies, we create a simulation environment and augment the simulation with actuator models. Then we formulate a reward around tracking the animations that we created in the first phase. The commands are randomized over the entire range, and the policies are conditioned on the same commands. So over time, the policies learn to track the individual references that the animator created. And our reference animations fall into 3 categories. There are perpetual motions, which continue indefinitely, and here we parameterize the stance by the head and torso commands. And the periodic motions have a cyclic nature and are additionally parameterized by phase. And then finally, we have these episodic motions, which are one-off animations, which are simply parameterized by time. And then for each of these motions, we train a different RL policy. And here you see a visualization of the gait library, for example, we used for training the walk. And these trained policies can then be directly deployed on the hardware. So in the bottom left, you see the reference that was used during training, and the deployed policy tracks these incredibly well on the real system. And additionally, the hard switches are barely noticeable. And due to the domain randomization, the policies are also very robust, and they can walk over this challenging terrain while keeping their style. And with these stable control policies as a base, we can then introduce the online animation component of our system. Instead of requiring the user to provide manually all high-level commands, we use an animation engine. This animation engine internally has 3 layers. First, there's some background layer, which gives a general sense that the robot is alive. Afterwards, we have triggered animations, which can be triggered by just a button press. And finally, there are joystick-controlled layer, which provides an offset to the currently active animation. And this process results in the high-level commands we send to the policies, but also it coordinates all these show functions that I talked about before. And here you see that in action. On the left, you have just the background animation. In the middle, you have the triggered animations on top. And on the right, you see what happens when we overlay this with the joystick commands. And especially the combination between the joystick commands and the triggered animations makes interaction very easy. So you can look at a particular person and then trigger a yes, no, or confused type of animation. And the operator primarily controls the torso of the robot with the left joystick, and it controls the gaze of the head with the right joystick. But we also introduce some coupling on the joystick side. So if you look a little bit to the left, the robot will rotate only its head. If you turn all the way to the left, it will rotate its head and afterwards follow with its torso. And we found out that embedding this kind of fixed coupling into the control interface makes it really easy to do a performance that looks good in the end. And with the robot finished, we had the exciting opportunity to then take it into Star Wars Galaxy's Edge in Disneyland and see how people react. And we created a small show around them as them being explorer droids that go to this land for the first time. It was very interesting to see how people react. People of all ages were very positive, and they project so much emotion onto this character, even though it's just a remote-controlled machine. In the end, they truly see a character in front of them that is part of the Star Wars land. And with that, I want to give a shout out to the rest of the team that made this robot possible, and thank you all for your attention.
Thank you very much. And where's mine, please? I would like one of those. No, seriously though, do we have any questions? There's one over there.
Thank you for a very cool talk. So I wondered, do you find that the domain randomization is enough to deal with the sim-to-real gap, or do you have to do any more complicated, like system identification or something like this? Thank you.
Yeah, the actuator models that we added, they were obtained through system identification. So we spent quite a bit of time there to characterize friction and characterize the torque limits, as well as the torque limits varying over velocities. I think that's quite important.
I see. And do you use a learned model for those, or is it a more standard model?
Yeah, we use just an analytical model.
I see. Thank you.
Cool. We've got one more question at the back there.
That's very nice. Can you hear me? Ah, yes. Okay. Are you studying, like, in all the context of human-robot interaction, assistive robotics, all this technology acceptance? It seems to me very related to this, in the sense that it seems that when the robot is jerky and all these things, and it moves more, and it has all these interactions, and it moves the head and it moves the whole body, people accept it better. It might be more challenging for manipulation, but do you think this will be needed to add to our robots?
Yeah, certainly the response that we've gotten from non-roboticists, but also roboticists, seems that like making your robot cute really helps in getting it
but
accepted.
It's not just cute, it's the way it moves. Like,
right, and people like, you know, when you trigger a certain amount of animation, you can really communicate something just through the movement. So I think that's something we can also take into robots that maybe work in an industrial site, but next to humans. It's not something we've tried to quantify in this paper, but I think there are some lessons to be learned there.
Okay, thank you.
Okay, well, let's thank our speaker one more time. Thank you very much. Okay, so with that, we bring the session, come on, brain, session 13 to a close. So let's thank all of our speakers one more time, as we've been doing. And then, okay, so the next thing we have on our program is the Early Career Spotlight with Stefan Lotnegger, which is supposed to start at 11. So I think we will go straight into it now. Okay, cool. So yes, come on up.
Thank you very much. So thanks for doing such a great job of keeping us on time. I think we can make good use of the extra 10 minutes while everyone is here. We'll give Stefan a few minutes just to set up. Okay, so while he's doing that, I'll say a few words. So I have the privilege and the honor of introducing this next section, which is the session, the Early Spotlight Career. And it's a really important part of RSS. It's often my favorite part of the conference. It's where we recognize roboticists whose star is on the rise. And there's a process for this. What happens is that nominations are put forward to the Robotics Science and Systems Foundation, and then a committee is formed, and an evaluation is made, and a small number of outstanding people are then passed on to the program committee and the program chair, and the program chair then accommodates this as part of the program. And indeed, this year, our early spotlight is Stefan Lotnegger. So let me say just a few words about him. He is a tenure-track assistant professor at TU Munich. He also has a joint or a visiting appointment as a visiting reader at Imperial College London, where he was before. He has done several, I guess all of your degrees are from ETH Zurich. His PhD was on the topic of unmanned solar airplanes, and that was under the advisement of Professor Roland Sigwart at ETH Zurich. Today, he's going to talk to us a little bit about real-time and robust state estimation and 3D scene reconstruction and understanding from using vision as well as Lidar and other sensors as well. So I won't take any more of your time. Thank you, Stefan.
Thank you so much, Dylan.
It's great to be here. It's a real pleasure and a great honor to me to talk about my research here today, which is on spatial perception for real-world mobile robots, including drones. But before I dive right into the research, I think it might be helpful to just take a step back and look at the robots out there, mobile and otherwise, and kind of group them a little bit along the axis of, on the one hand, complexity of the task, and on the other hand, the environment as to how specific and controlled it is versus how much it is open-ended. And if we assess a little bit how well these things work, and this might be a little bit personal as well, but definitely we can see a trend that the stuff on the bottom left tends to work really well, and then the more you go right and the more you go up, the harder it gets. Also, the kind of very cool demos that we see here in the manipulation sessions, for instance, they work in our labs, right? But then perhaps if we want to take them outside of the labs, they work a little bit less well. They're not quite products yet. And similar things you can say perhaps even about autonomous driving, right? As soon as you want to really deploy it anywhere in the world at any time, I would argue that we are not quite there yet. And clearly this kind of vision of having humanoid robots anywhere that help us in our daily lives with anything we might want on the very much top right is really not quite there yet. So we have to make still some progress here, and I think if we keep this map in mind with the things that I'll say afterwards, it might be helpful. Of course, traditionally, we have tried to solve this problem of moving towards open-ended environments with mobile robots in a sort of modular kind of approach, where we have perception, we have estimation, we might build up a map on board a robot, we then have maybe some motion planning in the loop as well, some feedback control, the whole thing, of course, a real-time control loop. So this has taken us so far, so far. It also allows doing relatively natural interaction and introspection of what's going on as roboticists, because we use the same kind of signals on board such a robot that we also understand as humans. Sort of shared representations. At the same time, however, I would argue that there are really single points of failure that we have also introduced here. Things can go wrong, right? We compute stuff in a wrong way. We might also have inherent limitations on these representations, these handcrafted, engineered representations that we use. All of that might lead to, say, autonomous cars not quite always working, right? And also perhaps just a note on the natural introspection. The reality is perhaps also not always as glorious. We have always seen, or we have all seen these kind of demos of mobile robots where you would often find an army of PhD students that somehow try to make sense of what's going on. So the reality again is maybe not as glorious. So clearly it seems very appealing to go with a much more sort of black box approach and apply end-to-end training that we can directly map sensor inputs to outputs. So then we can now have self-emergent behaviors and representations that hopefully overcome these sort of bottlenecks. Again, perhaps we didn't make much progress in terms of introspection and interaction and understanding what's going on, but we gained something. And while some of the progress here has really been amazing, right? I'm really amazed by, for instance, having drone racing completely sort of end-to-end in this way from pixels to torque. But the tasks typically remain somewhat specific, right? Also the environments, again, looking back at the map that I've shown before, these tasks and environments remain somewhat specific. So if we want to move towards the more upper right corner, I think we simply have a training issue here due to the sheer combinatorial explosion of task complexity and real-world environments that we really struggle to make progress towards the top right with this approach. So therefore, of course, now we want Robot GPT to help us. It's not quite here yet. Either, but there's a lot of promise, it's very clear. We have seen the amazing potential to solve long horizon open world tasks, also support us in natural language interaction. At the same time, unfortunately, of course, we all know that there's not a direct interface, at least to the sort of off-the-shelf models with robot sensors, and there's also no clear interface with robot actions. They're too abstract, we can't directly translate them. And then, of course, there's a lot of questions around how to train these, how to perhaps run these on board with constrained resources if you don't have a high throughput data link. So still some questions here that remain. So again, now for the lack of better options, I think as a pragmaticist here, we should just embrace all of the stuff that's out there, from the classical modularized sort of robotics all the way to learning, to large language models, to vision language models. And what this brings us is certain advantages. For instance, we can now train, for instance, or we can use a pre-trained visual foundation model that can leverage all the huge amount of data that's already out there that is neither robot-specific nor task-specific, and we can, have this separately trained and plug it in. Similarly, maybe for the control policies. And also, just to say, it's not in principle impossible to still train such a system end-to-end, right? I'm not saying it's easy, but if we somehow make an effort and we can get such a system to be maybe in some way differentiable, then we can still benefit from all the opportunities in, for instance, fine-tuning with reinforcement learning. But you start with a system that already works. So I think this might be interesting directions to try out. And clearly my research sees the sort of spatial AI here in the center. I think these representations are enablers for robot action. They allow for grounding in the real world, and we can connect them now with all kinds of learned policies. For instance, you might have also some shortcuts here, and perhaps more importantly even, you might connect these to large language models on the one hand, that then can also interface with the motion planners, with the policies that are already out there, and also ultimately can interface with a human operator. So that's kind of how I view where things are going, and in the last few years of my career, we have tried to make progress towards such a system. Of course, what this means is it still requires quite a lot of good old-fashioned engineering, as some people maybe in here might call it. So maybe you think this is bad news, but I think engineering is quite fun. So for me, at least it's good news. And here's such a system that we have recently been testing. That is completely autonomous drone flying around in the forest. It's a sort of first shot at it. It's running onboard visual inertial SLAM. It's then using actually deep learned model here from the stereo camera that was fine-tuned also in the forest to do map integration into local submaps. And then it uses that for planning. And it follows ultimately with the model predictive controller. Okay, and so all of these can now be communicated to an operator, right? So if you were to use a sort of more end-to-end approach, then you would struggle at least at that point. So here it was important that you might have a forester here in the loop that actually sees what's going on in the forest, that can interact with the system, sees where the drone is, what areas it has already mapped. Also, the drone can make sure itself that it covers all the areas that it's supposed to. So you really can't quite get away without these sort of human understandable representations of space, in this case at least. Okay, so I think these sort of spatial AI representations continue to be important. And we have made some contributions along those lines, starting with relatively basic levels, just in visual inertial SLAM, that focuses really just on the motion of our robots, and then all the way up to dense mapping, to also semantic mapping, and all the way to object level and dynamic maps. But I will start with the sort of backbone of visual inertial SLAM, just very briefly. Still these days, you can get state-of-the-art performance with using the reprojection error, the classic reprojection error that you can minimize jointly with perhaps also other error terms like pre-integrated IMU errors in between camera frames, in between perhaps camera keyframes, as long as you weight them with the inverse covariance matrices of these probabilistic models. And we can actually still do some trickery about keeping the complexity of this thing bounded, and combine it even perhaps with GNSS errors when they are available, So we get this system that kind of gracefully transitions between high accuracy RTK, GNSS enabled in a visual inertial navigation to visual inertial SLAM, depending on availability. So that's the first building block. On top of that, we then need some form of mapping to do our planning and controlling. And here we have invested quite a bit of time into efficient representation of free space, using this notion of adaptive resolution occupancy mapping, where we have very big chunks of free space volumes here, so we quite coarsely represent the big amount of free space, and you still get the fine details around the surfaces where needed, or in narrow gaps, for instance, then you can do fast planning through all of this. So that was the second component. Now with that, you can still not quite get a scalable mobile robot or drone to fly around in completely unknown environments. What we also needed to make it work is this approach of submapping rather than one monolithic map that you anchor to the keyframes of the trajectory, because the trajectory might actually change quite substantially over time. You might have deformations of the trajectory, you might have loop closures and so on. And so you can still query the whole map in this kind of understanding of a superimposition of the individual submaps, so you don't really lose the notion of a global map. You just have to query several maps at a single position. So now that when actually loop closure happens, we just can move around these individual submaps, and we can keep doing what we're doing. We might also have to now deform actually the reference trajectory such that our control system doesn't suffer from it. What is also now quite well possible with this idea of having volumetric submaps is actually to formulate further error terms that we can add to the visual inertial SLAM system, for instance, from Lidar. So we might have quite accurate Lidar measurements. You might have a previous submap. So here I'm just showing a cross-section through a previously mapped area, previously created submap. So you see here these log-odds occupancy probabilities indicated here in color. And now when you have a live Lidar point, you simply can evaluate the occupancy value and the gradient, and we can directly formulate with that a sort of probabilistically weighted distance to the surface being the zero crossing here of this field. And this allows us to do it in a correspondence-free manner, right? So we don't have to do ICP-like correspondences, and we can actually include quite a lot of these error terms in addition, in a tightly coupled manner, in addition to the already existing visual inertial SLAM system. So just a quick visualization here. We are mapping one area here, right? And the drone moves on. By the way, it can be moving also quite fast. So we're doing motion undistortion of these points. You get some drift, and we can now evaluate these error terms here in the volume and add it to the full factor graph. Okay, so that was the kind of system that is flying around in the forest. But we want to do more, of course. We are also very, very interested and excited about vision language models. So what we're doing in more recent work is to use this same framework, but also fuse additional information. Here actually also color, but we now simply extended it to also fuse vision language features, could be clip features, could be anything else, that are volumetrically fused in real time as the robot explores the environment. So these are unknown environments again, right? And we can watch how the robot explores the environment and reconstructs the environment, and simultaneously fuse this sort of vision language embeddings volumetrically anywhere it maps. And then this allows us to do open vocabulary queries. So we can now go in and find objects that we might be interested in, for instance. And now, you know, I'm quite interested in leveraging these sorts of approaches as part of an open world type of language instructed navigation or manipulation. Right. Another approach I did a few more years back was actually using this idea of submaps for mapping individual objects. So here we would detect in 2D individual objects, but then map them separately. And this allows us also to keep track of their motion. So here using an RGBD camera actually. So you don't know anything about the environment in this case. You don't know anything about the camera motion, and you don't know anything about the object geometries either, so it's kind of trying to solve these hardest of possible problems. And in order to detect what's actually moving, we are using the photometric consistency and the ICP consistency on the depth map. And then once you find an inconsistency, you can start tracking with the same error terms. You can start tracking the individual objects that are actually in motion. But you could see it's not quite perfect. There are some artifacts. It's a hard problem. There's no additional sensors used here either. So we tried to address this problem and realizing that this photo consistency assumption is really fundamentally broken when you're applying it to moving objects, right? You're moving objects, even if they're perfectly Lambertian, they are going to change in appearance. So we were trying to instead learn features that are resilient towards these changes. So we can still formulate almost the same error term, just instead of evaluating the photometric, the color difference here, we just now use the difference, the feature difference. Okay, and we also actually learn a confidence map for every pixel that allows us to weight this error term into a probabilistic error term that can now be readily integrated with ICP or with inertial terms and so on. So that's an advantage here, and then actually testing this, kind of putting it through the machinery of rolled out Gauss-Newton optimization steps, all in an end-to-end trainable kind of unit type architecture. This gets us really quite high robustness, so it can very extremely kind of perturb now here a live frame, and we can still robustly register it to a previous keyframe in this way. Okay, so clearly learning has been instrumental to detecting, tracking objects, to also tracking the camera, forming data associations. But I would say also for geometry, it could be super useful. So we also investigated some work here. That when doing this sort of object level scene understanding systems, you will always start with incomplete geometrical constructions of previously unseen objects. So you have these kind of incomplete, for instance, TSTF fusion-based objects. And it would be very nice to have always as complete as possible an understanding of the world. So we're using here a kind of conditional convolutional neural network, 3D convolutional neural network architecture that will always give us a completed object, a completed chair in this case. But it is very important that it's actually consistent here in the area that we have already observed. I mean, this would be otherwise terrible, for instance, for a robotic manipulation task, right? You want to be sure that the things that you have already seen, that they're not going to be worse in the completed object. And that is also consistent in the transition. And now, as you're gathering more information, you're getting more and more complete objects, you should also get a better and better completed version of this chair. And ultimately, if you have seen it from all sides, it should perhaps ideally look the kind of same way in both cases, right? So this is now the advantage that when you can bring it into the whole kind of object level tracking understanding system, that, well, you always get the complete view of, in this case, this chair, but it actually also really helps in the tracking, because now we can track against previously unseen geometry. So you can do ICP, for instance, of the live frame with respect to self-occlusions or also occluded parts of the chair, in this case by a person. So this whole idea of having always as complete as possible a geometry really, really helps with tracking robustness. And perhaps not so surprisingly, you can also now put that into some sort of robotic manipulation tasks. So this is some more recent stuff that we did together with Sami Haddadin's group at TUM. And it really shows that having a completed version of these models in the loop of manipulation really improves success rates quite substantially. So this was about scene understanding all the way to dynamically moving objects. Now, one important aspect are people. We want to have robots amongst people. So more recently, we have also invested quite a bit of time in trying to understand what people are up to from the perspective of a mobile robot. So really trying to solve this joint problem of robot motion and then person, pose, posture, and motion over time as a joint estimation problem, and therefore calling this whole thing body slam. So you can see here how it operates. And So I'll just briefly stop it here. We are, of course, using years of computer vision research here to actually infer from the camera perspective where the people are, what their posture, their pose is relative to the camera, what the key points are, key points centered around things like the shoulders or knees and so on. We find them in the image, and then we actually combine that with a motion model that we also learn, but that's vision agnostic. So the motion model is now purely all about configurations. It just makes predictions of what is the most likely next pose change from the perspective of the person, as well as posture change. We can now combine that with the estimation of the whole structure as well. So using the classic term reprojection error from bundle adjustment, and the whole kind of factor graph structure looks something like this. So you have here in green the classic observations of the static landmarks, and now in blue we have the observations of the moving person. And so you see the gray boxes, the gray rounds here are the poses of the camera over time, and the red ones is the parameterization with a simple model of the human, including here also the body shape actually that we are estimating. So this would be a sort of baseline that just projects out from the moving camera perspective where the people are. But now the interesting bit is when we are combining this whole thing actually with this also learned motion model, because this gives us now a temporal constraint on the person. And if we're combining that now all together, we're solving the whole batch estimation problem. You can really see against the baseline, it's really quite jittery estimation, somewhat inaccurate also in estimate of the camera, of how it's moving. Whereas in the tightly coupled way now, using the motion model, you get very smooth motion. And what is actually an interesting side effect of all of this is that even though this is now purely monocular camera setup, and we actually get the scale resolved. So we can do scale-aware monocular SLAM, and it really only works because you're using both the human sort of spatial model as well as the temporal model. If you drop any of these two, then it wouldn't work anymore. But still, we can, of course, throw in all of the kind of multi-view or the stereo camera setup with also an inertial measurement unit and get this to work in real time as well, so that we can finally then integrate it into a robotic application. So you get higher robustness, of course, with all of the additional error terms. Now, our goal with that is, and this is very much ongoing work, just as a bit of a sneak peek, our goal is now to use these sort of estimates for safe interaction between a drone and a person or many people by not only knowing where people are, but also by anticipating what they might be doing next through the rollout of this model, so that you can actually try to make some conservative approximations on what people might do, but also be optimistic in the sense of what is most likely that they might do next. So that's just, as I said, a bit of a sneak peek. But let's further continue with how to use these spatial AI representations really onboard real-world drone deployments. So another one where it's very obvious that you need this sort of spatial understanding is in exploration. So we throw on all of this submap-based volumetric mapping system and visual inertial state estimation, and can put it into an exploration framework where the drone now plans paths towards frontiers between the unknown and the known space and executes them, but really without any external localization system. And the whole thing actually works for both Lidar-equipped drones as well as just using depth mapping, and it can completely autonomously explore any kind of environment that it's never seen before. So the whole thing also works in the forest without a change of a parameter, so that's quite nice to see. But we can go one step further and really also leverage the semantic understanding of the world. By having this whole object level spatial representation, we can now also ask a drone to find specific objects of interest and include that in the utility function of the exploration planner to make sure that it gets close enough to everything to really not miss an object, and also when it finds an object to make sure it's really completely as possible reconstructing this kind of object. So from a certain distance, from a close enough distance. And again, just to show that this doesn't work only in simulation, but we have also deployed that in the real world. Now, the drone demos I've shown so far, they use relatively simple control, linear model predictive control, where you treat the whole closed loop attitude controlled system as a linear dynamical system that you can identify as a sort of gray box system. And that gets you really quite far already. But if you want to be flying in a more aggressive manner, it might be more interesting to really look at the full nonlinear dynamics. So we also, a few years back, investigated that to now really use nonlinear model predictive control and the full physics-based model that we have identified. Of course, this could also be a learned model, right? But for the sort of simple drone dynamics, actually a physics-based one works surprisingly well. So just to show you that, here we are flying it in the drone arena, and we're just simply giving it a step input change in terms of orientation and position, and it then kind of figures out this maneuver completely by itself. So there's no training in here, right? It's just solving this sort of planning problem on board ad hoc as it's requested to do it, as requested to change the position and orientation. And you can see here how the onboard simulation really matches quite well with what's happening for real. And this allows us to also fly in kind of extreme manner. It also allows us to switch off motors. So the only thing you have to do to the controller in this case is to just change the system input limits to 0, basically, for that motor, and you can keep flying. Of course, this is only helpful if you can also identify what's going on. So we have also this kind of model-based health monitoring here. I'll just stop it for a second. That monitors the health of every individual rotor, so compares the model to what's actually happening from the estimator, and then we can actually track that, well, it's lost one motor, and you can react immediately and change the controller and save the drone. You don't have as much time to do this, so just to say, the drone crashes within, I think, 0.2 seconds in this case, so you have to be kind of fast to identify this. This kind of approach, this model-based approach, we also further extended with more mechanics. So we have added a delta arm here also to this robot. And then use the same control approach now, not just penalizing the drone state in the MPC objective function, but to actually now add additional terms for the end effector, because we wanted it to interact with in a whiteboard in this case. So in fact, we have a term for a penalization for the lateral position, and we have a penalization for the normal force. So there's also a force sensor that should apply a nominal force when in contact. So of course, we know when it should be in contact and when not, and then all the feedback forces back into the system are also modeled and sensed, and therefore we get this sort of behavior that we can actually get the drone to write something on the whiteboard. Okay. I guess you can see where this is going. I have a few more examples. Anyway, so we can also use this, however, for 3D printing instead. So this is some other work. This was actually work as part of a very big consortium. We did the control, navigation, and perception part of it. So we can do cementitious material 3D printing with this kind of idea. In some sense, the control is a bit easier because you don't have the interaction forces that are acting back on the system. But then other parts are harder. So for instance, when trying to build bigger structures, this is with sort of expanding foam, then it becomes harder. Because you can really not pre-plan what's going on. You really need to bring back into the loop sensing to see what you have actually printed in order to then decide how to improve it, how to fix the structure, and to not print in empty space or crash with a structure that is higher than you thought. So we had this additional drone here that is flying around after every layer that was printed, and it's called a scan drone, so it's using the whole kind of mapping machinery I told you about already, and quite in fine detail then maps what was going on and adapts the next layer that is printed. Okay, so with this, I should come to the conclusion. I've shown a few contributions to SLAM, all the way from SLAM to spatial AI, robot motion, dense geometry, semantics, objects, and also humans. I've shown, and hopefully didn't have to convince you anymore at this point, that learning is really super helpful for a lot of the steps in here, including data association, geometric completion beyond what's visible, and that still you can use these sort of modules in a modular architecture that make things work in open-ended environments, large-scale open-ended environments. I'm of course very interested in the novel developments. I'm really asking myself how to best use these LLMs. And perhaps the main question down here is how can we get to a sort of ChatGPT moment with robotics, given all the robot-specific data, the robot-specific tasks, the embodiment gaps. So I guess there's still a lot of work for us to do, and I'm excited to be part of that. And finally, of course, huge thanks to the team and also to the sponsors. And thanks a lot for listening.
So since we started a little early, we do have some time for some questions. Do we have any questions? Okay, so while we're looking for, there's a hand over there. While we're waiting for the microphone to go over there, I'll say, Stefan, one thing I appreciated about your talk, in contrast to how we get each of the 5-minute talks, is to see the flow of ideas that connect all the pieces. You know, for example, the very end where you're doing construction and you're saying, actually, it turns out this is the mapping algorithm I discussed from before. This is something which I think the longer format really helps us see, so thank you.
Thanks.
Go ahead.
Yep. Thanks, Stefan, for a great talk. I have 2 questions. First is the exploration. It is really hard to define what is the good, better exploration in terms of time or the accuracy of the reconstructed maps. So how do you think about it? And the second question is, I also really like the large language model, how that involved in the SLAM. Do you have any, you talk about that a little bit at the conclusion. Do you have any kind of future insight about how the language model could help in the SLAM?
Okay, so I'll start with the first one. Thanks a lot, Ayong, for the question. So for the exploration, what are the measures? So actually, we have some numeric results here somewhere. What I think is important is time. You have limited resources, limited time always to solve these kind of tasks in practice, and also the completion ultimately. So you want to explore the explorable volume to 100%, right? So these are the main metrics that we are using here for the evaluation, and these are actually also part of the utility function. And here we compared it to a state-of-the-art alternative, just to show that our approach, of course you have to show that, right? Our approach works quite well in that regard. So yeah, so these were the criteria that we were using here. And then about your second question, I wasn't quite sure I understood. Is it about how LLMs can help SLAM, or about how to use LLMs afterwards? About how they could help SLAM? Yeah, I think it's a good question. I think they might help us identify, for instance, more abstract spatial relationships, or also even more abstract relationships inside a scene graph between different objects or so. It's of course a long list. It might help us also perhaps interactions, affordances, but not necessarily right out of the box, right? So how to connect that to a SLAM representation is still, I think, some open questions there. Yeah, but happy to talk and brainstorm ideas. This is a big part of the research, of course.
Do we have another question? Oh, up there? Up on the top left, I think. Stefan? Stefan, it's top left there. Yeah. Oh, we need the blue microphone, I think.
Thanks for the great talk. I was interested in the body slam work, how you mentioned that modeling the human sort of dynamics over time really improved your results. And I'm curious how that varies from person to person, and if you think that that's something that is a challenge, or even thinking across like senior citizens who might move very differently or use mobility aids, or children, and I'm just curious if you can talk more about that.
Yes, that's a very valid point. So of course, in some sense, you're assuming a sort of prior of the size of people implicitly, and that's what allowed us to do it metrically. Now, the accuracy is dependent on the deviation from a sort of standard human size, right? So this is clearly a limitation, and it's only approximately metric in that sense. Now, I still think, though, that there would be more advanced models that can probably see that, right? We can, when we look at pictures, we can see, we have a better feeling of how tall people are, right? And can also deal with all kinds of, say, disabilities, or so that we can somehow properly assess that. So I think this is, to some extent, it's a matter of getting better vision models. That was not really our contribution here. So I think once these vision models are getting better, we will inherently, this whole system will also get better. And in some sense, this was a bit of a theoretical contribution as well. So once you're fusing it all with the additional sensors, stereo and inertial, then you anyways have very good scale observability, and you can resolve these ambiguities also through that, right? So it's just perhaps additional robustness that you get from that. And yeah, the next thing is that in principle, we can even only observe people, right? If you're navigating through a crowd, for instance, everything is moving. With this kind of approach, we wanted to see if we can still get a reasonable estimate of the motion, even if everything is moving. And it turns out, with this sort of approaches, we can make progress towards it. But that shouldn't mean that we forget about all the other sensing modalities and the multi-sensor fusion in the loop. So yeah, I think these are the two aspects of the answer.
Thanks.
Let's see if we can squeeze Luca's question in quickly.
Brilliant presentation, thank you so much. I have a question about map representations. Many of the contributions you were presenting were about using voxel-based or volumetric representations. So my first question is, what's your take on nerve-based representation or Gaussian splatting type of representations? And maybe the second question is about still representation. For the work in which you're fusing clip into the voxel-based map, do you see bottlenecks in terms of memory or runtime there?
Yes, so these are, of course, very important questions. Thanks a lot, Luca. So for the first one, of course, everything is about representations, right? That's my hypothesis from the start, that to select robotic action, we have to have the right representations. And I don't think I have the right answer, right? I mean, we invested quite a lot in the kind of volumetric occupancy-based ones because they quite directly support sort of free space navigation, and they still enable also estimating where contacts are and so on. But I'm not at all saying this is the only one for manipulation. The whole thing might be different. If you want very accurate renderings, then we are of course very excited about nerves and about Gaussian splatting. So I think at this point, it's just a choice, right? We have so many different representations that we can use. And we can try them out. It depends on the applications, if it has to be real time, if it has to be realistic looking and so on. So we just have to keep that in mind. I'm not even saying it has to be explicit representations always. You also asked about the state. I think an explicit state is helpful for communicating it to people, but I don't think we know the final answer of what is the right state. If it can also be some kind of quite abstract learned embedding, for many tasks, this might be absolutely the thing that you want. So yeah, I think we shouldn't be so extreme as a community. We should really embrace all the possibilities that there are and explore them and see what works for what task. Now, the second question was about the language embeddings and the fusing into the volume. So it's very true that this is an actual bottleneck at this point. We're wasting huge amounts of memory by fusing that stuff at, in an actually adaptive resolution way down to centimeter level voxels. And then query it afterwards. So there's certainly room for improvement, and maybe compression through something like a nerve or other approaches is absolutely something we should investigate.
Excellent, thank you so much.
Now we're going to move directly on to the control session, but before we do that, just help me thank Stefan one more time.
Thank you very much.
Sure. All right. Let's switch gears a little bit. So now we're going to start the control session. I'm Nadia Figueroa and Justin Carpentier. We're both going to share the session today. So Justin will start with introducing.
So the first paper is a policy, the RL, learning closed-loop robot control policies with probable satisfaction of hard constraints, presented by Jean-Baptiste Bouvier. So we are waiting for the video, please.
All right. Hi, everybody. My name is Jean-Baptiste, and today I'll present Police RL. And the goal is to learn closed-loop policies that verify constraints in RL. And I've done that with Kartik and Professor Nick Garmer at Berkeley. So in RL, to get safety, you need hard constraints that cannot be violated, and that's typically done with control barrier functions, or reachability analysis, or some kind of projection into a safe space. But all these methods typically require knowledge of the dynamics. On the other hand, in RL, where you don't have those white box dynamics, we've seen approaches like control barrier transformers or PPO barrier, where you try to learn a barrier function with a neural network. But because of this, you lose those safety guarantee because you would need to verify that those CBF equations are verified everywhere in the state space. Our approach is closed-loop constraint RL, where we have a black box system, some affine constraints that we want to satisfy at all time after training, and we're going to learn a deterministic policy to do this in closed loop with some reward signal that we try to maximize. So our insights towards this goal is, given your state space with some unsafe area that you do not want to cross, we'll design a buffer region right in front of it so that if a trajectory goes into the unsafe area, it first has to go through the buffer, and we'll try to make this impossible. So first, estimate how nonlinear is dynamics in the buffer, and then we'll use the police algorithm from Yann Lequin to make our policy affine in that buffer B. Everywhere else, we let the RL algorithm optimize the policy to maximize the reward. And then we can verify actually that our policy is repulsive everywhere in the buffer by only verify at a discrete number of points at the vertices of our buffer, and using convexity, we'll know that our policy is repulsive everywhere and guarantee safety. So that leads to our theorem with our buffer of some given radius, and then with our affine policy and an estimation of how nonlinear is dynamics with epsilon, we verify our repulsion condition on the vertices V, and we have that trajectory cannot reach our unsafe set. And we tried that on some simple example in 2D. You can see here, try to learn a policy to reach a target in blue without crossing constraints. It's just a regular RL algorithm, and it cannot figure out how to reach the constraint without at least some little violation of that constraint line. On the other hand, our police algorithm on the other side, because the policy is affine in that green affine buffer region, the arrows are all related to each other, and it's much easier to learn a policy that never crosses a constraint anywhere, and so it learns much faster to avoid the constraints. On a robotic task here, try to reach the green target without crossing the red constraint. Some regular reward shaping does not really work. CPO is a CMDP approach and gets very shy when we set the violation threshold at 0, whereas with our policed approach, you can see the buffer in blue that will push the arm away when it gets too close over the constraint, push it away, and then reach a target below. And that allows to verify the constraint at all times, contrary to the other approaches. And so here's the results. Just TD3's regular learning algorithm is not very good at constraint satisfaction. It just gets a penalty every time it crosses a constraint. CPO is better at satisfying the constraint, but never really good at reaching actually the target. And then there's PPO barrier, which is really good at reaching the target, but because it learns the barrier function, we don't have those actual safety guarantees, and the constraint satisfaction is not at 100%, which is what our algorithm, our theory provides. We have that 100% safety guarantee, and with a good completion rate. And so the takeaways of this approach is that with PolisRL, we can provably enforce an affine constraint. We only need a black box model of the environment, and safety verification is tractable because we only need to check at the buffer vertices and not like everywhere in the state space. So thank you for attending.
So do we have questions?
Look, maybe a stupid question. Is there an assumption about the obstacle being a convex set? Are there ways to extend beyond that?
Yeah, the buffer needs to be convex, so for now we need a affine constraint, yeah.
Do you have any ways to maybe have a collection of convex set instead?
Yeah, there's a way to extend it to several obstacles with several convex sets, but then you need to modify the police algorithm, which is quite tricky because modifying the weights of your network will modify every buffer at all the same time. So yeah, we found a few smart ways to do this.
Thanks.
Yeah. Was there a question?
For the talk, does your method assume a deterministic environment, or does it also extend to environments that have domain randomization or some noise injected?
So yeah, for now it's deterministic domain. We've looked at other approaches for if stochastic, but that will create a lot of problem, to get that exact safety guarantee. That would require some big modification, probably, yeah.
Okay, thank you very much. We can thank the speaker again. So the next talk is about demonstrating language-grounded motion controller by Ravi Tejwani.
Good morning, everyone. Hi, my name is Ravi, and I'm here from MIT representing the group for language-grounded robotics. So our agenda is going to be motivation, followed by I'm going to talk about the robotics language controller. So the motivation is we have seen robots which have performed physical assistance to the users. However, they miss always providing language guidance as they are working with a human. So how can we synchronize those together is what we are doing the research on. So for example, here you can see a physical therapist, which is, I think the audio is not playing here, but it gives a verbal assistance while it's also physically guiding the human. So the goal of the paper is how we can synchronize both together while it's physically guiding the human, not just taking an instruction and building a policy. So our objectives, what we learned at a high level was, you have 3 high-level policies, objectives, which is modulating the velocity based on the user cooperation and doing the execution. So we build a language controller, which you take force, and then you have a new velocity. And the idea is how can we have 2 different parameters, which is the audio pace as well as the physical pace, which changes based on the parameters. So in the physical pace, it acts like a speed knob where we modulate based on the new velocity that we have from the controller. And this should not be confused with end effector velocity because the physical pace changes not just virtually, but also physically as well. And the way we align is we compute the time of completion of the audio as well as the physical pace. And then we create like an optimization function, which you can see on the bottom left, where the time to completion for the audio as well as the physical pace is estimated. And the idea is how we can compute like a ideal pace, which is the A star and P star for both audio and physical, and then map that. Sorry, it's going pretty fast. The idea is you have a cooperation value, which is the user guidance, and then we map that into the virtual force. And you have a virtual velocity, and that maps the physical force. And the idea is you guide based on the K matrix, which is the X and X minus 1. And then that is based on the admittance matrix, which is the admittance variable we use here. Finally, we do the paraphrasing, where as you guide the user, so each words represent, and then we map them so you have a longer route or a shorter route based on that. And that also depends on the time to completion for the video. So we try to achieve these three objectives. And then we evaluate that on 12 users with using a UR5 robot. And the idea was see if we can have 3 control schemes, which is the admittance controller, just vanilla, language controller without paraphrasing, and our own controller with paraphrasing. We looked into 4 evaluation metrics: cooperation, alignment, and estimated alignment to see how far we go. And this is how we test on a real user. The audio is not playing here again, but you can see that how as the user's cooperation changes, the robot slows down, but also speaks slower as well in this one. You can see here at I think time 3, because the audio was not playing here, is the cooperation was dropped, so that's why end effector speed reduced as well. But also on the right here, as the cooperation dropped, end effector speed dropped, but also the audio pace as well matched the end effector speed. So that's what we're trying to align as optimization function. And our goal was to reduce the estimated alignment for those and increase the actual alignment. And then this shows the audio pace across 3 different baselines that we had. And then our experiment showed that we were able to show 3 different control objectives that we were able to map into these things. And finally, there were some limitations where it's not just employed on admittance control. We can also apply it on different controllers as well. Speech length can be varied, and we can also use generative model, which can generate it. So all in all, we had some compliant trajectory, which we wanted to project, and we want to show the experiments, which can work on different baselines, and future work will be exploring other areas as well. So that's it. Thank you.
So do we have questions from the audience? So I will start with one question. So you mentioned about extending your work using other type of control methods. So maybe can you just comment a bit on that?
Yeah. For now, we use only admittance control, but the idea is this can be generalized to like compliance control or other control methods as well. But our goal was to show a simple method of an optimization, which can do speech as well as physical-based alignment. But only we showed admittance, but this can be easily generalizable to all other controllers as well.
Okay, and so can we imagine to use, for instance, just optimal control or trajectory optimizations and
yes.
to tune the cost?
Yes, you can easily use that, absolutely.
Okay.
Hello.
Okay.
Thank you. So about the user study, I'm here.
Yes.
So this adaptive speech, according to these agreements with the human, were you measuring how the human was reacting to that? Was ending up being more user-friendly? Or were you actually measuring that part in the user study, or was just a general validation with humans?
Yeah, absolutely. So we had a force sensor, which was actually checking the amount of how much user was cooperating with the robot. So based on that, we were adapting our speech. But we could extrapolate that to more like using camera in future, which can see the vision parameters of like effective features like smile, or like are they feeling anxious, or are they feeling other different types, and then we can modulate the speech on that as well. For now, we focus more on their cooperation, which is the physical manifestation based on the force that they exert. Sometimes the hand would be stiff, sometimes would be fluid. So we would modulate the pace on that. So that was our main focus.
And do you think that the modulation of speech will make the user more comfortable during the experiments or doing the physiotherapy in the future? That was the...
Yeah, exactly. So one of the final reports that you see in our paper, we were able to ask users their subjective feedback, how they felt with 3 different baselines that we had compared to our method. And they had more positive response because they could see that the language was more aligned with when they stopped. So a lot of times, if they were stiff and the robot will slow down in the baselines, the robot would not change the way it will speak and kept on speaking. So they felt weird that it was still speaking. Versus with our own, it would modulate and slow down. So they had a more higher subjective score.
Thank you. Great.
Okay, so we can thank the speaker again.
Thank you.
So the next talk is about VLMPC, Vision Language Model Predictive Control for Robotic Manipulation. so presented by Wentao Zhao, I guess.
Hello, everyone. I'm Wentao, a master student from Shandong University, and I'm excited to present our work via MPC, a vision language model predictive control for robotic manipulation. First, what's our motivation? Imagine a situation that where a person wants to tidy up a table. To be more specific, he needs to place the ample onto the empty plate, and he will subconsciously identify the possible obstacles by envisaging this process. It successfully plans a path to avoid the collision with the mug and wine. And this process brings us to the question, do robots have the capability of envisaging this process, possible futures, like human beings before acting? In another word, look before you leap. And this ability, predicting the future states to select the best choice, have much similarity and relation to model predictive control, which includes model prediction and the optimization process. And in most of the common model predictive control framework in robotics, the model prediction contains often referred to some trained dynamic models or radio prediction models. And the cost function in the optimization process are often defined through some trained classification models or simply pixel distance. These models struggle to accurately predict in scenarios that involve objects that they have never previously encountered. Thus, we present VMPC, a framework that incorporates multimodal language models into the MPC, robot control loop, to guide the robotic manipulation with complicated path planning and interaction with seeing objects. It has three core components. First, we use LLMs to initialize the task and handle current observation, which generates a conditional action sampling distribution for further sampling actions. Then these action samples go through a lightweight radio prediction model to predict a set of future frames. Finally, we designed a hierarchical cost function composed of pixel level cost and knowledge level cost to make a comprehensive evaluation of these radio clips. We conducted experiments in both simulated environments and real-world environments. In the Web2 benchmark, the results demonstrate the good performance of VMPC. And we compared VMPC with 5 existing methods in the language table environment on the task of move to area. The success rates reached 70%. And here is the real-world demo with the visualization of the rollouts of the radio prediction models. It's noteworthy that VMPC takes as input either a goal image indicating the prospective states or a language instruction describing the required manipulation. As you can see in the radio, it first predicts a set of future frames and selects the best action sequence to execute. And a goal image initializes the 2 tasks to guide the robot finish tasks in complicated scenes, such as move the banana under a box to a pink ball, or pick the red tower from a pile of towers. And the task can also be initialized by a language instruction, such as turn on the lamp and clean the table. Our code has been publicly available, and please feel free to stop by our posters or see our paper for more details. Thanks for your time and attention.
So do we have questions?
So suppose here the VLM is completely pre-trained and you don't adapt it into your context at all?
No, we didn't fine-tune the VLMs. The only model that we need to train is the lightweight radio prediction models.
Okay, thanks.
Other questions by the audience? So maybe one from me. Do you encounter any kind of hallucination when you try to foresee the future?
Yeah, in the actually in the radio prediction model, it may not predict that well because we only need to predict the moving trends of the future. So we only collect a few data in a new things, but it's okay. If we predict the right trends, then we can make an evaluation.
I have one last question. So I noticed in your videos that they're sped up by 16 times speed.
Yeah.
I wonder where's the bottlenecks? I mean, normally MPC is used for kind of like near real-time control, so why is it so slow?
Yeah, that's a good question. To be honest, our framework is not that efficient because each step it goes through a VLM and a radio prediction model, so the speed is relatively slow. But what our MPC is trying to explore a new robot control loop that incorporates the VLMs into the low-level robot control loop. So in the future, we may explore some more efficient foundation models or investigate some advantaged motion planning methods to make it more fluent and smooth.
Okay, so maybe a last question here, please.
In the video looks relatively linear. So the prediction model of your network, does it handle like nonlinearity or like discontinue?
Yeah.
Do you want me to repeat the question?
I cannot get your question that well. So maybe we can handle it offline in the poster session.
Okay.
So we can thank the speaker again. So the next talk is about expressive whole body control for human robots by Xuxing Yang.
Hello everyone, I'm Yandong, and I'll present our work, Expressive Whole Body Control for Humanoid Robots. We have seen many sorry, can we restart the video? I think it's kind of, okay, I will present our work, Expressive Whole Body Control for Humanoid Robots.
Can we start?
Yes.
It's running.
We have seen many humanoid works doing walking, and their upper body is not controlled well. There are also ones doing upper body manipulation from Figure AI. If you look closely, the robot's lower body also moved a bit. It has some levels of whole body control, and that is what our work is focusing on, but doing complete and agile whole body control. We want to know whether a humanoid robot can have expressions using the entire body. Some previous fancy works in simulation have privileged information and also some other special assumptions. And these make the policy hard to transfer to the real world. Specifically, they use character models with far more Delfts than the real robot. And they have complete observations in the simulator, such as linear velocity, keypoint position, and robot height. Our policy is deployed on a 19 Delft real robot with only onboard sensors. Our method takes human motion from a mass dataset, generative model output, and also motions processed from YouTube and self-recorded videos. We train the policy with a mass dataset and then do evaluation across all these data sources. First, we retarget this human motion data set to robot morphology. Here we use a naive joint angle to joint angle mapping, and we simply drop those redundant dots to do this process. Our key idea is to track upper and lower body goals with separate rewards. The upper body expression goal is just joint position and key point position. The lower body root movement goal is base velocity and orientation. With these and the proprioception input, the policy outputs a motor commands, and then it learns to imitate the human trajectories with RL rewards. Besides some RL imitation objectives, the policy is also trained with some regularizing rewards, such as feet height and feet air time, and also there are some other smoothing items. The policy is trained with PPO in SXGene. To this end, our policy is trained with simulation and human motion data. We can do whole body control for both legs and arms using a single network. The policy can automatically avoid conflicts of its lower and upper body on a 19-Delft humanoid robot. In deployment, the policy takes the joystick commands as root movement goal and the retargeted motion as the expression goal. Using these methods, we developed the first learning-based humanoid system to robustly express itself with agile and random motions in the wild. Here is a video where it is dancing near the San Diego flight carrier. On the bottom left is the original YouTube video, and the robot is dancing on grass. We can see the robot can robustly dance with both challenging terrain and tracking agile motions. But why should we learn from the previous massive human data to get this result? Getting expression goal is one reason, but also because human motion data provides a good distribution for sampling locomotion commands. We can see that by sampling from the dataset, the policy's linear velocity represented in green dots can cover the entire red command velocity in the top row. But when using random sampling, the green area only covers a part of the red rectangular and command area. Quantitatively, if you look at column MELV, which is mean absolute linear velocity, the random sampling method results in a much smaller velocity tracking rewards. And besides the data and simulation, the policy actually kneels down at the start, which entirely fails on tracking the root movement goal. We also tested tracking full body trajectories instead of separately tracking root movement and expression goal. Their data points are comparable, but the robot keeps taking some small sub-steps, and this policy cannot deploy to the real world. We also blade training separate policies for legs and arms. We tested with the 3.5 meters per second backward velocity perturbation, and the separately trained policy fell down on the ground. We also blade adding an AMP reward for encouraging the policy's transitions to be similar to those in dataset. We found AMP policy gets straight legs and worse real-world performance. The code is released right now, and please refer to the website for more cases. And here is a quick video for the robot dancing with the band. With that, I conclude my presentation, and I'm open to taking questions.
So, yeah, go ahead. So, yeah, on the second line.
Thank you for the nice presentation. And in the video you showed kind of the robot was continuously stepping while the dancing video was maybe keeping the feet on the ground. Do you have some intuition why it tracks the arms so well, but not really the legs?
Yes, so in all the videos in this work, the legs are always moving. The reason why that happens is that we are using a technique called RSI, which is resetting the robot's initial position according to the human trajectory. And that is making the policy actually hard to stand. And the reason why we choose that is that, we don't want this robot to do some manipulation task, because at that time, there is no hand on that robot. So the goal of our project is that, express itself instead of making it stand well.
Thank you.
Questions? Okay.
So my question is like, you mentioned you separate upper body and lower body. So like there is a waist doff on the robot. So is this waist doff in the upper body or lower body?
Sorry, could you repeat your question?
Yeah, so there is a waist, a joint on the waist for this robot, right? So it is included in your upper body or lower body?
It is included in the upper body.
Okay, thank you.
Okay, so we can thank the speaker again.
All right. Next paper is from compliant to rigid contact simulation.
Hi everyone. So I'm Quentin Lidec, a PhD student at INRIA Paris, working on simulation, optimization, and learning. I'm going to present our work on entitled From Compliant to Rigid Contact Simulation, a unified and efficient approach. This work was done in collaboration with Louis Monteau here and Justin Carpentier just there. Is it running? Okay, simulation is ubiquitous today in robotics. Whether it is in online control or reinforcement learning, gathering simulation data in a limited amount of time is critical. Here is a quick reminder of how a physical simulator works. In the first phase, collision detection algorithms compute contact points and normals. Using first principles of physics, the second phase involves a solver that computes contact forces. Finally, these contact forces are applied and the state of the system is updated via integration. The second phase is critical and remains often limiting both computationally and in terms of physical accuracy. Our contribution in this paper lies on this phase of the simulation by proposing a unified and efficient approach to compute contact forces. These are some examples of what a simulator can do, by the way. When computing contact forces, 3 modes need to be considered. In the first mode, the contact point is braking, which induces a null contact force and a non-null normal velocity on the contact point. In the second mode, the contact point is ticking and has a null velocity. In the last case, the contact point is sliding, which means that its velocity is tangential and the contact force lies on the boundary of the cone. Intuitively, these 3 modes induces a combinatorial complexity as it is not possible to know in advance in which mode the system is. The resulting non-smooth dynamical system is highly challenging to simulate and control. These 3 modes emerge from fundamental physical hypotheses: the Coulomb's law of friction, the maximum dissipation principle, and the signal-unique condition. The resulting problem to solve can be written as a nonlinear complementarity problem. This class of problem is hard to solve in general, as it is non-smooth and non-convex, so many existing solvers proceed by relaxing some physical principles. Typically, they would convexify the problem by enforcing the compliant matrix R to be non-null and even in the case of rigid scenarios. This kind of relaxations come at the price of physical inconsistency, which may hinder the downstream applications. Our central contribution is a novel ADMM-like algorithm to solve the nonlinear complementarity problem by avoiding any relaxation. This algorithm is obtained by formulating the nonlinear complementarity problem as an equivalent optimization problem interleaved with an outer linear constraint. As depicted by the pseudocode here, the resulting algorithm is quite simple despite being both accurate and efficient, which is essential for applications in modern robotics. Our approach relies on 3 main ingredients. The first one is the use of proximal algorithm, which makes our approach robust with respect to ill-conditioned cases. For instance, here, oh no, sorry, I think it's the wrong slide. Yeah, in DrEureka, this is okay. The second one is a spectral adaptation of the proximal parameter, which makes our approach robust with respect to ill-conditioned cases. For instance, here, the red cube at the top of the stack weighs 1 ton against 1 gram for the blue ones. And the final ingredient is the use of advanced rigid body dynamics algorithm. These algorithms are particularly efficient when considering poly-articulated systems such as robots, as they finally exploit the sparsity of the problem. On various robotic systems, this leads to state-of-the-art simulation rates that are up to twice as fast well-known other simulators. Based on this work, we built a new simulator, which is called Simple. Simple will be available as open source on GitHub soon. And the simulator is built on top of Pinocchio library for efficient rigid body dynamics algorithm and on top of COL for fast collision detection. We hope this work will benefit the whole robotics community. Thanks.
Any questions?
Hi, thank you for the talk. Really interesting work. So I noticed that you were using ADMM to solve the underlying optimization problem. Could you comment on how sensitive your method is to the different ADMM parameters and how you do the step size scheduling? Thank you.
Yeah. Okay. So to update the proximal parameter, we use the spectral update rule, which is based on the evaluation of the highest and lowest eigenvalues of the problem, which is the conditioning, by the way, is set by what we call the Lasso matrix, which is the linear coupling between the contact forces and the contact point velocities. And so we are evaluating the eigenvalues of this matrix, which is quite cheap to do because we use the power iteration algorithm, so it's not more expensive than an ADMM classical step. And so once you have evaluated these eigenvalues, you can update efficiently the proximal parameters. It is set automatically during the optimization process.
Thank you.
Hi, thank you for your talk. My question is, so the original nonlinear complementary condition is very hard to solve, but when you change it to ADMM, so is there any intuition that why this kind of problem will be easier to solve?
Yeah, so the inner problem, so the optimization problem that we are solving with the ADMM algorithm is a convex optimization problem. So maybe this will give you an intuition of why it's an easier problem to solve. And so, by the way, so the inner problem, in the case where the contact point is not sliding, you are retrieving another formulation, which is called the Cohen complementarity problem, which is a convex formulation that is used in other simulators like Mujoko or DrEureka, for instance. So,
okay, thank you.
Yeah.
Any other question?
Hello, here on the right. Thank you for the very nice presentation. Would you be able to share some insights on what you plan to use these new techniques for, and what kind of robot applications do you see this unlocking that current simulators and current methods wouldn't be able to achieve? Thank you.
What I mean is a physics simulator, so it can be used for a range of applications. I think we would like to target most of them, like reinforcement learning, doing some control with it. Also, we're working on differentiating this simulator, so providing gradients, differentiable simulator. And so this would open the door to even more applications, MPC, doing contact invariant optimization, etc., etc. So yeah.
Okay, quick question.
Thanks for the talk. You mentioned that your NCP corresponds to a non-convex problem, which could have multiple problems. In the end, you solve a convex problem, which has one solution. How do you make sure that you map to the physically correct among all the possible ones?
I'm not sure to get the question, but we solve the NCP, not the CCP. What I wanted to say is that in the case where the contact point is not sliding, this is equivalent to the CCP problem, which is convex. But our problem is non-convex.
But how do you make sure that you solve the one that corresponds to physics? I mean, the solution, there could be many solutions. How do you know the one that you compute is the physically meaningful?
The thing is that in many cases you have sometimes infinite amount of solutions. And relaxing the problem makes the solution unique, but it also introduces some physical inconsistencies. And we find one solution.
Thanks.
Yep.
All right, let's thank the speakers. Let's move on to the next paper, MPC C++.
Hello? Hello? Okay, so hello, I'm Maria Krina, and today I'll be talking about model predictive contouring control for time-optimal flight with safety constraints. So this is joint work between Professor Zeilinger's group and Professor Scaramuzza's group. So drone racing is an extremely challenging task because we really need to push the physical platform to its limits. And it's also an extremely interesting case for us to really benchmark AI algorithms in robotics. And in fact, in 2022, for the first time, an AI won against a world-class human pilot. But these algorithms struggle to prevent gate collisions and often plant too close to the edges of the gates. So the question here is, can we do better? Can we fly fast and safe? Now, there are sort of two ways to solve this problem. So on one side, we have reinforcement learning, which does end-to-end learning, but it requires a lot of interactions with the environment. And then there's sort of the optimal control side. Here, we leverage a physical model of the system, and we can handle constraints, but we need to solve an optimization problem online. So in this work, we're going to focus on the optimal control side, and specifically, we're going to look into model predictive contouring control, which is an MPC algorithm tailored for the particular racing task. So MPCC continuously trades off between two conflicting objectives. We want to maximize progress along a predefined path, while at the same time trying to track this path accurately. Now you may be wondering, how can we actually make the drone fly to the gates? So one way of ensuring that the drone flies through the gates is to scale this contour weight in the proximity of the gate. This means that we don't really care about following path closely when far away from the gate, but really want to ensure to follow the reference path accurately when passing through the gate. Now the problem with this is that this does not systematically prevent collisions, because at the end, we don't have any constraints as such. So the question is, can we have some sort of constraint? Can we add a track constraint? But how do we define a track for the drone racing task? We can define a tunnel, which passes through the gates. Now this tunnel sort of expands in the gate-free regions and then shrinks when passing through the gate. So the idea behind is that we sort of really let the controller freely plan the fastest trajectory as long as it stays within the constraints of the tunnel. So here you see the approach on the standard approach on the left and the approach with the safety constraints on the right. Now you can see on the left that we sort of have to push the drone towards the gate center to follow accurately this reference path. Whereas on the right, because we have the safety constraints, we can nicely sort of take shortcuts through the gate corners. So we can fly safely, but what else do we need to fly fast? We need an accurate prediction of the dynamics throughout the MPC horizon. So we enhance the nominal dynamics with a residual term that we infer directly from real-world data. Now this term sort of encompasses all forces that we don't know. This means aerodynamic forces, propeller forces, and so on. And the nice thing here is that we can approximate these using very simple polynomial features. So we have accurate dynamics, we are able to include constraints, but how do we tune the controller parameters? We can use Bayesian optimization, and in particular, we use a scheme called Turbo, which stands for Trust Region Bayesian Optimization. So now we sort of combine all of our elements together, train it in simulation, and then finally deploy it in the real world. What do we get? So we can fly over and over again through the track without crashing into the gates. This is a really consistent trajectory, and the nice thing about this is that sort of the safety benefit comes without compromising performance, as our method achieves zap time similar to the best performing state-based reinforcement learning policies. And you can see it flies very consistently and has all of the nice properties of a model-based controller So it's very smooth, and we also have this physical interpretation. Now, one thing to mention here is we're using a motion capture system, so this is different to the work presented yesterday by my colleague. You can see we can just continue flying, and it flies over very consistently and very smoothly through the track. This we're at the end. Thanks a lot for listening.
Questions?
Thanks for the nice talk. I'm curious, what do you use to solve online the MPC problems, and do you have any feedback delay trouble at such high speeds? Thank you.
So the question is, how do we solve the MPC problem? Did I understand correctly? You can, yeah, keep them. Okay, so we use Sacados, and we use SQP RTI. The controller is running at 100 Hertz, and we just run one SQP iteration. It takes about 4 to 5 milliseconds usually to run one controller iteration.
The QP or everything together?
Everything together. Yeah.
Thanks.
Hello. So I have two questions. The first one is, the tunnel, it's wider out when you're far away from the gates, smaller close to the gates. But what is the advantage of having it wider when you are outside? Do you gain performance? So if you have the same width of the tunnel everywhere, according to how big are the gates, will it work the same, or it works better in this way?
Okay, so just to clarify your question, you're asking why don't we use the same tunnel width all throughout the tunnel? Okay. So yeah, the idea is basically you don't want to really have to constrain the trajectory. You want to find the closest to the time optimal trajectory, right? So you don't want to add an additional constraint in a place where you don't need it. And so the design choice here is you want to pick an outer tunnel width, so in sort of the gate-free regions, you pick a tunnel width such that the constraint is never active. Does this answer?
Okay, so you make it as big as possible.
Yeah.
The other question,
sort of make it as small as possible such that it's never active in a way. Like you could somehow make it bigger, but then you will have a very large transition from the inner gate width to the outer gate width, which is also not so nice for the solver. Yeah, so you sort of make it as large as possible such that it's never active. Yeah.
And about the modeling, I know that Professor Zeringer likes Gaussian process to model the residual dynamics. So I wonder if you can say something about why the polynomial approach that doesn't measure uncertainty is better than this, or a Gaussian process will do the same job?
Yes, you could also use a Gaussian process. And in fact, the beginning, or we have another version where we're using sparse spectrum Gaussian processes, which is sort of a low-dimensional version of a Gaussian process. And yeah, you could use either of the two. The thing here is we leverage actually the physics of the system, and sort of we know that these unknown forces are dependent on X quantities, and it's actually much cheaper in terms of evaluation if you have this knowledge of the system that you could actually leverage and directly come with some polynomial features. But if you have a black box and you don't know how to model your residuals, you can use either like a full GP or a sparse spectrum GP approximation.
Thank you.
We have one question here up front.
Hello, thank you for impressive presentation. I know that your system is tailored to track racing, but I was just wondering whether is there any more applications in more complex real-world scenarios, and what do you expect? How do you expect your drone to perform in those cases? Thank you.
Yeah. So, I mean, if you think about MPCC on itself, it's an algorithm tailored to racing. So it's tailored to car racing, road racing, finding time optimal, or close to time optimal trajectories, let's say. And I think here the key takeaway is that we maybe need to think of the MPC sort of moving a bit away from the standard tracking MPC into something where we really just have a cost function that is somehow flexible, and we can sort of just solve an optimization problem. So I think that's more maybe the way to think about it. Particular, if you think about MPCC, then yes, I would say it's tailored to anything where you want to find nearly time optimal trajectories. But it could also be something beyond drone racing, where you say you're some retail store or something and you want to find the closest or the fastest path between X points or X waypoints.
Thanks.
All right. Any further questions in the poster session? Thank you very much. Let's thank the speaker again. Our next paper is linear time differential inverse kinematics, presented by Bruce.
Do I just go automatically start? Okay. Hello, I'm Bruce Wingo. I'm with Ingrid Paris and Georgia Tech. This is a presentation about differential inverse kinematic solver. So differential IK is fundamental to robot planning and control, and making it fast is important. Doing so will enable differential IK to be deployed on low-powered hardware, such as microcontrollers, as is commonly found on resource-constrained robots. Differential inverse kinematics problems often needs to be solved hundreds, if not thousands of times as inner problems for other downstream applications, such as global IK and sampling-based motion planning. For a complex system such as a humanoid, having a fast and efficient IK solver will certainly free up precious onboard computing resources for other tasks, such as motion and language processing. QP-based formulation has become the go-to approach for formulating differential IK problems. Specifically, the joint space formulation is the most common, employed by many state-of-the-art solutions. Motion constraints and velocity bounds can naturally be expressed as equality and inequality constraints. However, with the joint space formulation, the kinematic tree-induced sparsity is abstracted away. Therefore, we opted to formulate the differential IK problem in the so-called maximal coordinates. In this formulation, both spatial velocities and generalized joint velocities are decision variables, and inequality constraints can be concisely expressed with a composite constraint set. To solve these constraint QPs, we opted to use augmented Lagrangian style methods, specifically ADMM. And to facilitate the application of ADMM, we can introduce these slack variables for the inequality constraints. So with ADMM, the original problem is transformed into an equivalent primal dual saddle point problem over a so-called augmented Lagrangian function, which is constructed by adding appropriate penalty terms to the ordinary Lagrangian function. And the resulting primal dual saddle point problem can be solved efficiently using ADMM iterates. So we first solve the equality constraint subproblem, then we perform constraint projection, and lastly, we update the dual variables. The most computationally expensive component of the ADMM iterates is solving the equality constraint subproblem. Even with state-of-the-art QP solvers, the worst-case computational complexity is still cubic. However, if we exploit the tree structure sparsity in the problem, we can obtain substantial speedup over off-the-shelf QP solvers. So structured sparsity in robots' kinematic trees has been successfully exploited for rigid body dynamics algorithms. More specifically, Ricardi-like recursion procedures have been deployed on robots' kinematic trees, often producing linear complexity algorithms. The same recursion principle can also be applied to solve differential IK problems, as we seek to exploit the same exact tree structure sparsity. So if we take a closer look at the ADMM equality constraint subproblem, we realize that it takes on the same form as a discrete time LQR problem. This can then be solved, again, with Ricardi recursion, and this allowed us to derive a 3-pass linear complexity algorithm, which we call LOIC, for solving differential inverse kinematics problems. The performance of our solver is evaluated against existing differential IK solvers with state-of-the-art QP backends, specifically OSQP and ProxQP. So we designed a benchmark for trajectory tracking tasks specified as differential inverse kinematics problems. The benchmark is collected over a variety of robots, ranging from fixed-base robotic arms to high degrees of freedom humanoids. As we have discovered that LOIC is on average 2 to 3 times faster than state-of-the-art QP solvers at solving differential IK problems. So here are some video footage of LOIC running on a diverse set of robots performing differential IK tracking tasks. At each time instance, a differential IK problem is specified for each robot as tracking some desired spatial velocities while subjecting to robots' kinematic constraints and velocity bound constraints. So an open source and efficient implementation of our solver LOIC is available on our website. It's written fully in C++ and it's compatible with the latest release of the Pinocchio API. Thank you for your attention, and if you are intrigued by our work, please come see us at the poster session.
Any questions? Okay, I'll start. I have one question. So I noticed when you define the inequality and equality constraints, the inequality constraints are kind of like bounds. So I wonder if, or at least how you formulated them in the slide, which is fine for like velocity limit, like kinematic limits, joint limits, velocity limits. But what about more like affine inequality constraints like self-collisions and collisions with external obstacles, or even preferred null space configurations? Like, can this formulation handle these type of constraints?
Because we isolate the problem into different subproblems, so technically, as long as you have the correct projection function for how to project your solution onto these inequality, because if you remember, we formulated inequality constraint as just basically belonging to some composite constraint set. So as long as it's a set we know how to project to, you can handle it with ADMM.
Okay, and what about more like global constraints, like balancing? Like with a humanoid, normally you have these like task constraints, which are how you want to move the end effectors, but you would also want to keep balance, right? Like the center of mass of the humanoid. So can you handle those type of constraints where it seems like it's constraints on all of the links, not just kind of like separately on each link?
So for instance, for balancing, you could specify it as a tracking, more like a tracking target, right? That would be, you can put that in your cost. And for stuff like that, a lot of it are equality constraints, task space constraints, so that we can definitely handle for sure.
Okay. Any other questions?
Hi, thank you for the talk. What are the QP solvers that you compare to? There's a lot of variation between them, in my experience. So.
Yes, because our formulation is very similar to OSQP, which is also using an ADMM style procedure. So we figured OSQP is the most reasonable thing to compare to. So we will be releasing our benchmark code as well, and in there you have support to stuff like QP Oasis, and just there's a lot of support for other QPs. I don't have the slides up, but we also compared to DrEureka's inverse kinematic solver, which, I mean, again, you can use any QP you want. But for us, OSQP and ProxQP are probably the best performing, so that's what we compared against.
All right, let's thank the speaker again. Now the last presentation of the session, a trajectory tracking algorithm for the LSMS family of cable-driven cranes.
Hi, my name is Javier, and I'm presenting a trajectory tracking algorithm for the LSMS family of cranes. This work is out of NASA Langley Research Center. The project is called Lando. So let's watch an intro video. I don't think there's sound, so I'll be narrating over. So to build infrastructure on the surface of the moon and Mars, we're gonna need autonomous cranes and excavators. And to do so, we need to develop new algorithms that can handle these type of systems. We need them to be lightweight and compact to save on cargo volume and fuel costs, and one of them is the LSMS, that stands for Lightweight Surface Manipulation System, that you can see here. It's very slim. It deploys when it arrives on the moon. As you can see, it folds up for space travel. And the smallest version is the LSMS Mini. It can lift 35 kilograms on the surface of the moon, and the biggest version can lift 1,000 kilograms on the surface of the moon. As you can see, they're cable actuated, which is an added challenge, And a team at NASA Langley Research Center is working on this specific one. It has 3 degrees of freedom with 3 joints, the waist, the shoulder, and the elbow. And it's actuated with cables, as you can see. So to operate it like a robot, we had to design a protocol that can track complex trajectories. These trajectories define the desired joint angles and rates. The trajectory tracking algorithm takes in this information along with the encoder information, and it's supposed to create angular speed commands. This was a difficult problem due to the dynamics of the crane. The cable that controls the elbow is routed through the arm, and this creates a coupling between the shoulder and elbow dynamics, the nonlinear nature of all this geometry that you can see up here, and the spreaders that introduce switches when they touch the cable, so 6 different configurations. So to solve this problem, we broke it down in 2 steps. First, we analyzed the geometry of cable A. Here you can see that as the shoulder lowers, spreader D becomes in contact with its cable. And in the video, you can see that there are no sensors on the LSMS that we can use to determine whether and when the switches happen. Similarly, we analyzed the geometry of cable B. In this case, as the elbow lowers, spreaders H and I became into contact with the cable. This video highlights the coupling between the dynamics. The LSMS is lifting the arm while keeping the elbow angle constant, and this is only possible if you move the motor, the shoulder and elbow motors that you can see on the right, in synchrony. So this geometric analysis led to the model of the LSMS, and then we started taking some assumptions to simplify our life a little bit. So the first one is that cables A and B operate under tension, otherwise we lose controllability over the shoulder and elbow angles. Here you can see that if you keep lowering the elbow, you may lose tension on the cable. The second one is that the protocol knows the geometry of the LSMS. We later relaxed that assumption, so the protocol knows the geometry within some tolerance. And the last assumption is that the underlying motor controllers track the speed commands precisely. And then we later relaxed that assumption to consider bounded errors on those motors. So with that, we were able to prove that under ideal assumption, the trajectory tracking algorithm is uniformly exponentially bounded, and under relaxed assumptions, the algorithm is uniformly ultimately bounded. And this is a video of the test that we performed at NASA Langley Research Center. On the top left, you can see the desired trajectory along with the actual angles, and then on the bottom graph, you can see the errors. We achieved pretty good tracking, and these trajectories were designed to go through all 6 spreader configurations, switching from all the spreaders that you can see here on the right. So if you want to know a little more about the LSMS or the Lando project, you can talk to us at the poster session, go to nasa.gov, or reach out. Thank you.
Thank you. Any questions?
Thank you for your nice talk. I'd like to know what is the requirement of your crane system, something like the payload or something.
Yep, so there are many requirements, depends on the crane within the family. There's 3 different cranes, but the biggest requirement for the smallest crane, the most important requirement for the smallest crane is a 35 kilogram lift capacity on the surface of the moon. That's sort of the most important one.
Oh, thank you. Is there any requirement of the speed of the hoisting the object?
There is not a strong requirement on the speed to lift the object, but more important requirements are power consumption, compute power, things like that.
Thank you so much.
Any other question?
Right, thanks for the talk.
I was just wondering, so if I understand correctly, you control the system by knowing, let's say, when the various switches are happening.
We don't know it.
All right, so can you, yeah, okay, so how do you estimate that? Can you just repeat that part?
Yeah, so we estimated, but we estimated with incomplete knowledge. So we know the geometry of the crane within some tolerance. So that means that when you estimate whether a switch is going to happen, it may not exactly happen at that time. And one of the things that was important in the proofs is proof that the algorithm was still stable, even if the algorithm believed it was in a configuration, spreader configuration, that it wasn't really in.
Right. Yeah, so let's say that was because I expect that essentially you can handle uncertainties like unexpected slippage and things like that that could happen because of, I don't know, dust, or I imagine the application is not too easy overall, so yeah.
Yeah. It was important for us to handle uncertainties like that, and even like manufacturing errors and other uncertainties that these systems are subject to.
All right, let's thank the speaker once again.
Thank you.
So this ends the control session. Thank you all for staying. Oh, okay. We still have one thing next, the upcoming Lely industry talk. Right.
Nice. Yeah. He's introducing us, I think, but they're letting people walk first. And then, oh.
Test.
Test.
Can you hear me?
No.
Test.
Yeah.
No, not from here. Test. I cannot hear myself. Ah.
Yes.
Okay, so, well, if you can please take back to the chair, so we will continue with the program. Well, now we have an industry talk, a lunch industry talk from our main sponsor, so that's Lely. And they will show some very cool videos of real robots in real places. But yeah, I will not tell more about it yet. So we have two speakers. We have Kasper Haag and Alexis Siakris Lekos. Both are embedded software engineers at Lely, and they will tell us a bit more about how is one day at Lely. So the floor is yours.
Thank you. So, like mentioned, we're engineers, so this will be a bit of HR, but not too much. We'll also be a bit talking about our work, and I think it's good to show what we do. So let's get started. So first, I also would like to start with the vision of Lely. So why do we do what we do? Our vision is to have a sustainable, profitable, and enjoyable future in farming. So that means not only for our farmers, but also we need to be as sustainable as we can be to bring our robots to the field. So before we get started with our talk, let's first do a video on what Lely is doing currently. I'm not sure that there's no sound. Sound's working, but
a future that continues to center around the cow, as it all starts with her. When she's hungry, our solutions provide her with food automatically. Whether it's a freshly mixed batch of feed or fresh grass right from the farmer's pasture. When she wants to be milked, our milking robot is at her service. At her own pace, 24 hours a day, 7 days a week. Her milk can be processed and bottled at the farm, resulting in fresh milk in your glass within 48 hours from the dairy farm just around the corner. Her home is a clean barn, as our solutions take care of manure. Waste is captured and processed to reuse as fertilizer, reducing ammonia emission by 70%. All our solutions are integrated and deliver valuable data, brought together in an easy-to-use farm management platform. Data that helps farmers make the right decisions for optimum productivity and cow health. Working with our integrated solutions, dairy farmers can rely on the dedicated support of our global network of Lely centers. Together, we support dairy farmers to feed the world in a sustainable manner while caring for their cows and the planet, now and in the future.
Yes, so that's us. Don't have to clap. Sure if it works. I think, yes. Okay, so who are we? We're Lely. We're based in Maasluis. Currently we have over 2,500 employees. Most of them are in Maasluis, but also we have a facility in America where we build our machines. We also build machines here in Holland. And I think it's good to mention that a lot of our investments go towards R&D. So we do a lot of research, also why we're involved in conferences, this one, but also a lot of others. And I think that's good to mention here. We're in a lot of markets, over 50. This is the places where our robots are. So we haven't conquered the whole world, but we're almost there. So let's continue on that. And these are robots. You saw a few in the video. I will go over a few of them now. Left top is the astronaut milking machine. So basically a cow goes in, it gets milked automatically, and it can go out again. So all on our own terms. You have the graceway on the left, where the cow basically can go outside of the barn. It's scanned, and basically the farmer can manage, are they allowed to go out, yes or no, based on like grassy lawns, are they wet, can they get stuck, and then that's done automatically. On the bottom you see some hoof cleaner, so also automatically cleaning the hoofs, so the hoofs don't get any diseases. And on the right you see an automatic feeding machine, so it goes to the kitchen and gets some food for the cows and then scans, okay, where is the food, is there enough food, and then distributes it along the cows. And two of the robots that are in the middle we're going to talk about a bit more because we're engineering those, so that's Alex is going to talk a bit more about that. So who are we? I'm Casper. I've worked for 4.5 years at Lely. I'm a software engineer. I did my master's here in Delft, system and control. And as hobbies, I like to play hockey. I could do cooking a lot. I travel. Recently visited South Africa and want to visit a lot more. And I like movie and games. And my current biggest passion project is my daughter. She's recently born 10 months ago. So that's where most of my time goes currently. So Alexis?
Great, thanks. I'm Alexis. I am working a bit more than 3 years at Lely. Also a software engineer like Casper. Also did the same master, systems and control. Only thing is that I did it in the rival university in Eindhoven. In my free time, I like to play ping pong. We also play a lot in the Maasluis campus. I like to go to the cinema. Doesn't matter if it's a 100 years old movie. I like it. Really enjoy going to concerts, and especially during my vacation, I like to do hiking. I might not have a kid as Casper here, so what I have for now is our robots. These are the two robots we are working on. On the left, you can see the collector, which is the manure cleaning robot. Basically, it makes sure that the floor of the barn is clean for the cows. On the right, you can see the Uno. It's the feed pushing robot. It makes sure that the cows always have feed within the reeds. But then you might ask, okay, what did the farmers do before our robots came to market? These are the manual solutions, basically. On the left, you can see the manual manure cleaning tool. On the right, you can see the manual feed pushing tool. Well, the nice thing about our robots is that they take away the manual labor from the farmer, and also they do the same kind of work 24/7. So I think that's better. Yes, so actually yesterday we were at the farm. We were actually doing some tests. So we were in one of our test farms, and we thought, okay, let's make some videos for today. Let's show a bit how do these robots work in their environment. Sounds a bit loud, but basically you see the collector here. It's on the dirty side of the map, of the barn. It cleans, so wherever it passes, it leaves a clean path behind it. It's a bit hard to see, but it sprays water on the front to make the manure a bit softer, so it's easier to collect. It sucks the manure inside with a vacuum pump. And when the tank is full, the manure tank is full, or when the route is finished, it goes to the dumping station. Usually the dumping station is combined with a water station and a charger. So basically the robot goes back, dumps the manure inside, fills up with water, and then charges for the next route. And this is our Uno, the feed pushing robot. Here we see the feeding fence. So this is where the cows eat. You can see the cow head sticking out. Of course, the cows are very eager, so while they're eating, they spread the feed around the place. Then comes the Uno, detects the feeding fence, uses this nice skirt that you see that it's rotating to push the food back close to the cows. When the route is done, it goes back to the charger as the collector charges for the next route. Now I want to talk a bit about why do we enjoy working on these robots. So the collector is a robot that has quite some limited sensing. So it has odometry, it has IMU, it has ultrasonic sensors. So it's partially blind. It's a bit, we see it a bit like a bat. So it doesn't really see, but it uses ultrasound waves to localize. So that's really a challenge for us to work and make this a robust machine. Another challenge is the dirty environment. As you saw, the robot is full of manure. So you have to deal with challenges like, I have manure on my side and my ultrasonic sensor is dirty. I'm detecting nothing. What do I do about it? And of course, it also needs to account for moving objects. It's really in the place where the cows live, sleep, and eat. So, there are many cows around. It has to take care of that. Sometimes the farmer may step inside. We step inside sometimes to do some tests. So you have some variety in moving objects over there. And the Uno. The Uno may not have such a challenging environment as the collector, but it's still a very dusty environment. A bit like the R2-D2 in Tatooine. And the extra challenge there that it also goes outside of the barn, so it has a bit more diverse in surroundings in the environment. There are a lot of moving objects, even more than the collector, so you can have cows, but you can also have people, you can have dogs, you can have machines. Maybe the farmer parks the machine in the route of the Uno needs to take care of that, go around it. And we also have the farmer over there, and what we want to show, you see a nice farmer with one of his cows. We want to show that we also work on user interaction. So these machines, they need to interact with the user in a reliable and intuitive way. So this is something we are also working on. It's quite challenging, but also very interesting for us. And very important is also that, as Kasper showed earlier, we have robots in many different countries around the world. That means that we have more than 1,000 machines out there. And they need to be robust. They need to work, they need to do the job well, and they need to do it 24/7. So robustness is also a very important aspect in our job. I want to go a bit more technical to maybe inspire you a bit. So as we said, we both studied systems of control. And the nice thing is that we actually get to apply what we studied in our everyday job. So for instance, we are working on movement controllers. The collector is using a wall follow controller to make sure that it touches the wall and scrapes every last bit of manure from all the sides of the barn. The Uno uses a feed push controller to make sure that it pushes on the feed with minimal error and minimal oscillations. And we also touch on other topics, other robotics topics like localization and path planning. So as we said, we have a couple of sensors like odometry, IMU. We fuse them together with the sensor fusion, and we try to estimate where we are within our environment. And after that, of course, we need to plan our way towards the next reference point. Let's say we want to go at the end of the cubicle. So we touch upon this kind of topics, which we like a lot. Very interesting also is that this is a real-time embedded system. So it has to work real-time, very important. It has to be fast. And the nice thing is that it's not just software, it's not just hardware, it's not UI, UX, electronics, it's all come together. So let's say someone from hardware says, okay, I want to design a new charging station. We need all to come together, make sure that every last bit of the collector works fine with these chains. And this is very interesting because we get to work with multidisciplinary teams. We come together, we learn from each other, we look at the same problem from different perspectives. In the end, we have a robust and nice machine. And on the right, you can see our application. This is how we communicate with the robot. And what we want to say is that we don't just do low-level stuff, back-end development. We also actually work on the front end, and we really like that because we see the full cycle of development. Last thing I want to mention before I pass it back to Casper is that we have all these machines on the field, so that means that, of course, we need to maintain them, right? So we get issues from the field that we have to solve. We get new feature requests from our stakeholders. So that means we do a lot of continuous development. But we don't do only that. As we said, we have robots with very limited sensing. So that means that we have to be creative. So we actually put a lot of time and effort in innovation and research. And that can be, for instance, that we're looking at better algorithms, how we can take more advantage of this limited sensing, but we also look in newer technologies or other types of sensor, how can we integrate them and make sure that we have a better robot.
Yes, so how does our day-to-day work then look like? So the thousands of robots in the field that we have, we take the data basically, we make a model, we engineer something that works for all the robots. We can use everything that a lot of you guys also using, so that's nice. And then basically after that is finished, we have a model, we use the control part, then we do something like the continuous development where we write the code, we unit test it, we system test it, which is less nice, but it's still nice that you can do a lot of stuff altogether. And then, of course, it's testing. We have a workshop in the company where we can test our robots, but also we have the test farms. There's 10 in Holland where we can go. And we get to talk to the farmer, we get to see the robots in action, and we actually see what we're doing. And I think that's really valuable in your job. Also, we're not sitting right at the desk 24/7. So that's a great part about the job, I think. Besides that, why is it nice to work at Lely? You have some nice things like a foosball table, ping pong table, a barista where you can get nice coffee. Also, of course, get your cappuccino with the own produced milk, so that's always good to see. And besides that, we have our own gym. We can work out, and some nice team outings, like Alexis said. We're really a large team, so also that involves a lot of nice outings. And besides training your calves in the gym, there's also calves being born in the farm. So I think that's one nice part of the job. So thank you for listening, and that's Lely's eShort.
Is there any question for the speakers?
No? Okay. So what's the break-even time of these machines in terms of like, given the upfront investment of the farmer, how long does it take for them to actually generate profit with this? Do you know more or less?
So for one of our machines, you mean?
Yeah.
It depends a bit on the machine. Like a milking machine is quite expensive, so that's I think 5 to 10 years, something like that.
Mm-hmm.
The Juno and the collector are a bit less expensive, so that takes a bit less time, of course. But it depends a bit on what robot you have and what you're gonna do with it. Sometimes like you can get a collector for like 60 cows or something, up to 60 cows. Some use it for 40 cows. So that's a bit of how much cows you have, and yeah. It's not really a one-way answer that you can.
And what's the lifetime expectancy of the machine, more or less?
I think at least for union collector is about 10 years.
Yes. So mainly we produce them for 10 years, and that's all parts should.
Yeah. Sorry, one last question. So you mentioned that you are internationally quite active and you export a lot. Do you use external suppliers, or is it Lely itself?
Yes. So also in the picture we have, or also in the video you saw, like a Lely Center thing. It's sort of a franchise which basically sells the robots in their own country, in their own language. I think for farmers that's really important, because basically they're really into their own circle. They talk to their neighbors, and they find it more important what they think than what the rest of the world thinks. So I think it's really important that you have like these guys there that sell the robot, and we try to do our best to basically involve them in that process.
I see. Okay, thank you.
Hello. Thank you for the nice presentation. I'm curious about what you learned when you started on this. Like, what were maybe some of the surprises about what products are important or could be valuable to the farmer compared to what you thought initially when you got started?
What is most interesting? What was most
nicest I have one anecdote I'd like to tell. Basically, the moment I came into Lely, I was like, okay, let's design some nice controllers, let's design some popular things. The thing I learned is that cows are really how do you call it in English?
Curious animals.
They're really curious animals, but also they're really packed animals. So they really see the robot as one of their pack. So if you for instance, say, okay, I want to stop now for a cow, they eventually know that you're stopping for a cow. So what happens is that they basically push the robot into a corner, and then they keep the robot there. So you learn a lot of those things, that cows are really packed animals. You need to take those things into account into your robot design, otherwise you're gonna fail, basically. Those are nice learnings, I think.
Thanks.
Yeah.
Very interesting. I have like a follow-up question. So I saw, and as you said, your robots get very dirty, the cows are pushing them around. So how, I mean, robustness must really be like super essential. And if you work in a lab and do your research, right, like you constantly have to repair your robots because it's constantly breaking. So I'm wondering, how exactly do you ensure this robustness? What are kind of your strategies there?
So there's two types. Maybe you could take this.
Yeah. So indeed, I was going to say there are two kinds that you can do. Of course, we have a lot of filtering, so we try our software to be robust towards it. Sometimes we might have some hardware solution to clean up, for instance, the ultrasonic sensors. And then we also, there is some time that we actually require the farmer to take some action. So we try to identify if there is a problem. For instance, we say, okay, the ultrasonic sensor seems to be dirty. Please clean it. Or the charging pad of the collector seems to be having so much manure that while charging, the charging is suboptimal. Please scrape it. So it's a bit of combination of coping on our own and also identifying the problem and asking the farmer to take some action.
And hardware-wise, you do endurance tests to make sure that those components actually survive 10 years in those conditions. So you mimic something in the office to get those conditions there.
Thank you. I think I'm next in line.
So we will take one last question.
I'm down the other side here. Do you guys collaborate with academia, or do you prefer to do it all in-house? And if yes to collaborating, then like how does a person get in touch?
We actually work quite a lot with academia. We work with a lot of students here from Delft. We have many nice ideas for new internships, new algorithms, maybe searching how a new sensor could be integrated in this harsh environment. And yeah, we don't always have the time, so we usually use some interns to do some proof of concept. If the outcome is good, we bring it into our production and we further develop it.
Besides that, we also have some projects with some universities, PhD projects. So I think with Eindhoven now and Twente. So we're always open to those things for more research because basically we need it, otherwise we cannot survive.
Well, maybe we can take the question down there. You have been waiting, I think.
Localization and navigation on the farm. Do you like pre-map the whole farm, or you instrument the farm with some beacons, or all of the above, maybe?
Yeah. So right now, there is a map for the collector at least, but we are also we always do extra research to try to see if we can make it even more autonomous.
So now someone manually pre-maps the environment. I think most of the research now goes into indeed automating those things. So that's a large part of our work currently, that we're automating those kind of things.
Thank you.
Okay. So, well, Casper and Alexis will still be here. So they have a booth outside, as you probably have seen it. So you can go and ask them all the remaining questions. They also have a visit. So one of the visits tomorrow afternoon is a visit to the farm. So that you can go and see the robots. If you're interested, you can still sign up. And with that, I would like to thank them again for the talk and the sponsorship of the conference. So thank you very much.
Thank you.
Let me try again. So welcome everyone to the RSS 2024 Test of Time Award session. This is an RSS tradition and a special session designed to recognize papers published at RSS at least 10 years ago that have had a substantial impact on the community and beyond. So I'm Luca Carlone, I'm going to be the moderator for this session, and it's my great pleasure to announce that the Test of Time Award this year goes to the paper LLM, Lidar Odometry and Mapping in Real Time by Ji Zheng and Sanjeev Singh, which was presented at RSS 2014. Let's start with that. So let me start reading out the format citation. It says, LLM is recognized for making important advancements with relevance directly to the core robotics capability of mapping. In the years since, Loam has been successfully employed for different types of vehicles and across diverse environments, and has spurred related activities by multiple other research groups. So in the RSS tradition, the authors, Ji and Sanjeev, who are joining us online today, will give a lecture about Loam today. And after that, we have a presentation by our expert panelist, Ayun Kim, who will talk about developments in the field after Loam. But maybe before we start with the keynote by Ji and Sanjeev, let me say a couple of words about the impact of Loam, and maybe let me start with a little bit of history. So starting from a couple of decades ago, the robotics community put substantial research effort on 3D Lidar odometry and mapping, partially triggered by the DARPA Urban Challenge. So one key issue is that the 3D Lidar might be relatively slow scanning a scene, and this is particularly the case for lidars involving 2D, 3D lidars involving 2D spinning lidars. And in particular, if the robot moves quite fast comparing to the scan time, the resulting point cloud might have some distortion, which is causing inaccurate odometry and mapping results. So early work just got around the problem by just keeping the robot stationary during scanning, or by assuming that the scan is much faster than the motion of the robot, in which case you can use standard tools, for example, the iterative closest point or ICP. Then a new wave of papers started explicitly modeling and correcting the motion-induced distortion of the LiDAR, but these are either offline methods or relied on specific type of LiDAR sensors. Finally, in 2014, Loam was introduced and provided an effective solution for motion and distortion while working on any LiDAR and in real time. So the impact of Loam has been extraordinary. At the time of publication, Loam was placed first in the KITI benchmark, and something that really blew my mind, I checked this yesterday, is still in third position on the KITI benchmark after 10 years, which is pretty impressive. Loam triggered many follow-ups, including SA-Loam, E-Loam, F-Loam, L-Loam, P3-Loam, R-Loam, S-Loam, T-Loam. And I will stop there. You can keep reading the list if you want. I think at some point people just finish the letters of the alphabet and had to come up with a little bit more complicated acronyms. The paper has collected lots of attention, more than 3,500 citations, including the journal version, and has impacted companies and startups, ranging from application, from mining to inspection, and we're going to hear more about this in the keynote, I think. So with this introduction, it's a true pleasure for me to pass it to Ji and Sanjeev, who again are joining us remotely today for their keynote about Loam. So let's welcome them.
Sanjeev, please go ahead. Yeah, okay, great. Thank you, Luca. Thank you for that great introduction, and thank you for this great recognition. I will try to give you some thoughts about how things got started and some insights about this and some applications since then. I wanted to say early on that as an advisor, it's sometimes humbling to learn that something you asked your graduate student to do, not to do, it made it big and then made it really big. So G was working with me around 2011 onwards for a few years, and he wanted to work on SLAM, and I said to him, G, SLAM's done. I mean, what is there to do? It's already all done. There's nothing left to do here. And he said, no, I think we can do something in this area. And well, so he had another project and he would work on SLAM in the background. And that's how this thing got. I'm very happy he didn't listen to me. What happened was that the exact moment was that we were working on agricultural robotics and having a vehicle that G will show steer itself through some orchards and vineyards. And when the world was very flat, very even, very flat, there were simple methods that could keep the vehicle going fully autonomously. But when the world started to become a little bit more three-dimensional, when it was sloped or it was rutted or something, then it was just really hard to be able to do this. So what G came up with what was the state of the art at that time was a Hokuyo laser scanner, and he started rotating it. He built it himself, and then developed a method that would effectively be the precursor to what became Loam. Couple of steps there, so we got something that was more like guidance still going on there. It wasn't really mapping until we looked and saw that the maps that were being produced were actually pretty good. That was sort of unexpected. And so then G started taking this device here and walking around Newell Simon Hall in this kind of complicated area. And one day he came back and I said, okay, well, yeah, this looks good. But what method did you use for loop closure? And he said, I didn't use any loop closure. I said, what? That's just not possible. This is a part of that, the second floor of Newell Simon Hall. We were puzzling over this, like, why did we not, this is no loop closure. Why was it doing such a good job? So I said to him, next door they're building in the Gates building, they have this really interesting thing. It has a spiral walkway, okay? And in the middle of this building, no edges, just like gently sloping spiral walkway that's going all the way through the middle of the building. I said, yeah, by the time you finish your thesis, you should go and try to do a map there. Try to do a SLAM there, because this is meant to really confound people working on SLAM. This is exactly the kind of thing that, if somebody wanted to make life difficult for SLAM people, this would be it. So next week he came back with a thing that was already, he had built a map with this. So we were still trying to figure this out. I was trying to make things a little bit harder for G because he was just racing ahead. And so I said, okay, now what we're going to do is how about we put this on a flying vehicle? And then, we do this on a drone. Well, there were no drones that could carry anything at that time. And no, the computing wasn't quite there. And the Velodyne puck was just about to be released. We actually got one of the first Velodyne pucks, and it happened to be so heavy that the drone couldn't carry it. That's the genesis. It was a combination of computing and IMU and Lidar just hitting a particular spot, and then having an iconoclast like G, who was not willing to listen to anybody's idea about what problem had been solved or not been solved, to sort of like keep plugging away. And what you're going to see here in G's presentation is just some remarkable things that progressed to a point that at the end, I almost ran out of challenges for him. And I said to him, I've seen this Star Wars movie in which they fly through a forest here. How about if you have a drone that flies through a forest? And that you can do right before you graduate. In my mind, I'm thinking that's never going to happen. But I needed to give him something. So you'll see, okay, where he got to there. And then I'm going to let him talk. I'll step in at the end and talk about one application that has been picked up commercially. There's been many companies that have taken this forward, but something a little non-intuitive that we might be able to think you. We have people walking around in buildings and drones flying through forests and all sorts of things. But how does this solve a real problem? And I'll talk about one such case. G, take it away.
Okay, thanks. I'll talk about the early work. So after that, Sanjeev and I will talk about application. We also invited Ayang to talk about the extensions and improvements. I kept saying this to Ayang, this award is really for the family. Over the 10 years, we have a family. Loam is just a dump tray front end. It's just a front piece. But over the 10 years, there is really a family, and we have full-scale SLAM. And Ayang will overview the approaches. And we didn't really do anything for the family, and we think everybody in the family, every family member has credit. Okay, so I'll very quickly go through the early work, and these are all the stuff. The work started from here. This is the very first result right out of my office. My office was right here. So I walked out of my office and mapped the whole way. So I took that 3D scanner, And we built the spinning mechanism. We took a Hokuyu line scanner, we built the spinning mechanism so that we made a 3D scanner, actually. It's right here. And they can only rotate back and forth. You see the wire. They cannot spin continuously. Okay, it's a cheap design. But I took it and I tried something in parallel to the agricultural project. I first implemented this step, okay, which does motion distortion removal, and it sort of work. It can give you motion estimation, or state estimation, but it just strips so much. So I tried something more. I added another step. I didn't have another choice, so I added the mapping step. There was no magic here. I did the first one, then I thought, okay, what can I do? So I added the second one. This is the original processing pipeline. So the geometry step here, it runs at high frequency, 10 Hertz with that sensor package. The mapping step takes longer time. It runs at 1 Hertz, and it does careful processing and careful mapping to ensure the accuracy. In transform integration here, it takes the output, the post output out of the tool, and integrates them so that it gets the best out of the tools. So the final post output is at higher frequency, 10 Hertz, which is a dominant frequency, and it's the mapping's accuracy. Okay, so that's the original pipeline in the RSS paper 10 years ago. The original implementation used geometrical features. It used edge points and planar points. So this is again using that custom built 3D scanner. And the Hokuyu scanner, it worked quite well indoors in a perfect environment like this. This is the end of the hallway. The walls are perfectly flat. The edges are perfectly sharp. And you see the features are well extracted. The yellow ones are the edge points, and the red ones are the planar points. Later on, we started to try the Velodyne 16-line scanner. That one came out later, probably a year later. So we started to try that one, and we started to see more noises. But this is the original implementation. So here is an early video of mapping the staircase right out of my office. So my office is on the 2nd floor. It's a little slow. Okay, so I carry a sensor and I walk down the staircases. Okay. 10 years ago, when you watch a video like this, it wasn't as boring as today. Okay, I'll stop it there. So that's almost the end. Okay, so we actually tried putting the scanner on drone. We had a bridge inspection project. So we use the drone to fly around bridges to collect data, and we use this technology to build a map. To assess bridge inspection. Okay. Okay, some more early maps made by Long. This one is right off my office. My office was right here. And this one is the lobby of our view. More trail, orchard. I remember I showed this to Sanjay. I showed an extended version of this map. This is the very first one that I made off of my office. But if you walk through this hallway, it goes through the other side of the view. So Sanjay's office was somewhere here. There was another loop. So I mapped this loop. I walked all the way to the other side of the building and back to the other loop. And I showed the map to Sanjay. So that's the first map that I showed him. And he asked, you were working with Michael Case, right? This is his loop closer. He thought I was using his loop closer. Michael just came in. couple of months ago. It was almost the same period. So, okay, we're a good friend. So that's how the conversation started. Then later on, we tried some more improvements. We used IMU, and we also made some improvements in the scan processing as well. So this is me carrying the sensor and jumping over that vehicle. So at that time, the 32-line Velodyne scanner came out, and we got one. And we made some improvements. We tried to reduce the computational load. There was a processing computer in the backpack that processes the data in real time. And we also tried to keep the map clean. We figured that if we let the map get blurred for just a little bit, it hurts the scan magic in the next frame. And when the scan magic gets worse, and when you register the scan onto the map gets even more blurred. So it gets worse, scan by scan, but very quickly, in a few seconds, it starts to drift, and it could even fail. So keeping the map clean is one of the keys. That's a take from the early days. So in the next,
Can I say something there? Can you just go back to that one slide? Just add a small thing. So this was a sort of precursor to trying to fly it on a drone. The drones weren't quite there yet, you know, and so we were trying to scratch our heads about how are we going to make the case that something that dynamic could be done, right? So somehow or the other, somebody suggested, hey, how about doing parkour with you know, the sensor strapped to a person? This would have about the right kind of, you know, speed, dynamics, the kind of accelerations that you might see on an aircraft. And, you know, before you knew it, G had turned himself into a samurai roboticist. And that was his name, with the Lidar strapped to his head, to mimic to sort of start the whole thought about how to do this on a drone.
In the next couple of years, we extend the pipeline. This is the final pipeline. I'll talk about a high level. It has three smaller problems. We're not solving the full-blown optimization, like the standard Stackelberg optimization. We dump all the constraints in one big optimization problem. We're solving three smaller problems. Each problem does whatever it can, and it gives the result to the next step. The next step refines it. And we figured this is a format that works really well, because our take, according to the full-blown optimization, is that when you have multiple sensor modalities, we have so many constraints, and they all have the noises for each constraint, and you dump them into one optimization, and when the convergence close to the bottom, it could get very slow. So that part, it takes a long time to convert, and it may not convert very well. So we're solving smaller problems one after the other. So it's a reconfiguration. It's another version of spectrograph optimization problem. We're just not solving the full-blown problem in one shot. Okay. Compared to the Karman filter implementation, the filter-based method, they process the data in a sequence. This is just a high-level illustration. The data comes in, and you process the data one by one. Of course, there are variations, but that's the concept. And the full-blown optimization, you dump all the constraints into one problem, and they solve the problem. It could take a long time. And I would say that our pipeline is a variation of the full-blown optimization. It does it in smaller and multiple steps. So this is the full pipeline working. We have the 16-line Velodyne scanner at that time already. There's a camera, IMU inside, and there's the eyesight processing computer inside. So it does everything in real time. And at that time, we also had the localization feature implemented. So I first walked around the building. This is our Robotics Institute building. Then I put it on a drone and flew it manually. And the second run was the localization mode. So it loaded the map from the first run and it kept extending that map. And in the end, we will see the final contour. It covers the surroundings of the building and the roof. And the mapping of the roof, it was the localization. So by that time, we have the building, but the roof is empty. So this is the end of the walking part, first step. Second step, I put it on the drone, flew it manually for just a couple of minutes. The first step took almost 20 minutes, 15 to 20 minutes. Then you just, that little bit of flying on top of the roof so that you can cover everything. This one right now is running in low climate. Okay, so the green part is from flying, and then it was mapping in low climate. That's the whole map of the area. Very three. Okay. The subterranean challenge started. We tried to do the technology. We went through this mine. It's a huge mine in Louisville. And we had the kickoff meeting there. We made an appointment. So we were allowed to drive through the mine. It took us 1 hour to drive through the mine. We mounted the sensor payload on the car. And we drove through it. And we mapped the whole mine. So that was around the start of the DARPA Subterranean Challenge. That's 2008, 2018, and 2009. It took about 1 kilometer by 1.2 kilometer by 0.7. So we also looked at the robustness. We integrated the 3 sensor Lidar, camera, IMU. After we integrate the 3 sensors, we got the accuracy improved for just a little bit. It's a little more accurate, okay? It is what it is, but we thought about it. What's more to get out of the 3 sensors? We think it's the robustness, because when you have the multiple sensing modalities, one sensor can be degraded. So when you are in an environment like in the bottom, and when you look at the constraint, for state estimation, the constraints can be parallel in some direction in some directions in the state space. So which means you just cannot solve the problem in that direction because there's not enough data. If you use just one sensor and every once in a while it goes into an environment that's degraded, you cannot do much with that sensor alone. But when you have multiple sensors, they can compensate each other, like to make a full set of healthy and well-constrained problem, like the one on the top. Of course, this is a healthy case, but when you have multiple sensors, you can make it happen in that way so that the whole problem is healthy and you can solve it well. So we think the robustness is the point, the real point out of multiple sensing modalities. And this is what we try. Again, this applied to our 3 small step processing pipelines. So each step takes care of itself. And the way that we tried it was to actively detect the degradation. We call that degeneracy. So analyze the eigenvalues and eigenvectors. It actively detects the degeneracy, and when the degeneracy happens, we only use the prediction in the degenerate directions in the state space. Okay, so in the state space, we detect the degeneracy, and we also compute the degenerate directions. And in those directions, we don't try to solve the problem. Like in the standard way, we try to solve the problem in all directions, but in the degenerate directions, it's not solvable because it's affected by the noise. The solution can slide in that direction because of the noise. You can get anything out of it. So in that direction, we actively detect it, and we use the prediction, the initial guess from there. We only solve the problem in the well-conditioned directions, and we parse the result to the next step. The next step refines it. So each step takes care of itself, and it does whatever it can, and it gives the result to the next step. The next step tries to make it better. Okay. Sorry. This is a quick result mapping a traffic tunnel, a smooth tunnel, and if we don't do active degeneracy detection and handling, we got the tunnel mapped like that. It's squares. It's clearly wrong. But when we handle the degeneracy correctly, it maps the tunnel from one end to the other end. Okay. So this is to the end of the slide deck. So this is the time that we started to try commercializing the technologies, and we also started to try using the SLAM solution to support autonomy. So this video, it has our SLAM module there at the bottom. And at that time, we started to develop clear avoidance and planning. This is our drill. The clear avoidance module, it runs very fast. It gets you the path within 0.2 to 0.3 milliseconds. But that's beyond SLAM. The SLAM module is there, and it's very stable, integrating the 3 sensors, Lidar, camera, IMU. It's a building block of the system. And from there, we actually developed the local planner for clear avoidance. And later on, we also had exploration and global route planning. So this is the start that we stepped out of SLAM and into autonomy. This is the map view through that flight. It was processed in real time on the onboard computer. While it flew through the forest, it dumped the various laser points into a pump cloud. So we got this pump cloud map on the computer right after the flight. This is the last slide. We tried to commercialize the technology. The startup tried many things. And so that's the end of the slide deck. So at this point, I would invite Sandy to talk about one application. And after that, we will give it to Ion. And Ion will talk about the extension and the improvement. Like I said, the award is really for the family. Every family member has credit, and Ion will talk about it. Okay, so Sandy?
Yeah, G, let's see if I can share. I think you have to stop sharing. Okay. Let's see here, share. 1 second here. Okay, give me a second. I'll try to share. Here it is. So one of the sort of non-intuitive applications, and there are many applications I just want to share, is using this to inspect large aircraft. So just a little bit about that. Aircraft are often in hangars where there's absolutely no chance of GPS and there's no chance to install any kind of infrastructure. Yet you want some way of inspecting these very high surfaces because, every so often they have to be tested for or checked for failure, et cetera. So the problem is really about putting a camera, and it could be any kind of camera or any kind of testing device, at a very specific place and very specific pose, whether the aircraft is in one hangar or another, or it's in a different position in the hangar. So this is a problem that was presented to us, and we looked at it and thought about how we could possibly use the method that we developed. And I just want to show you one thing here. There's an image here that I'm just going to bring up here. Let me see. I'm going to stop it and start it over again. So this is a C-130. It's a fairly large aircraft used for large transport. Of course, there's been a number of others much larger than this that have been tested with the method, but I thought I liked this one. So I'm not sure exactly who did this, was G or somebody else. It was possible to just walk around the aircraft and build this kind of a model. Now, you know, in some cases now we can do better with structure for motion cameras, but the idea here is within an hour, you have a very, very good point cloud of this thing. Maybe you edited out a little bit of the stray noise points, but once you have this kind of a 3D representation, then just like what G showed with when he walked around Old Simon Hall and then was able to map the roof of it and all the buildings around it. Once we have this, a drone can take off anywhere around the vehicle, and it locks onto the 3D model that was created before. In this case, it's not a partial model, but here's a 3D model, and then what it can do is it can position its camera relative to the aircraft coordinates. So we care about inspecting some points like maybe the props or the tail or the horizontal stabilizers at a very specific place, not a specific location in GPS coordinates or in hangar coordinates. And so this is now this method and some improvements on the loam technique are sort of like in use every day. I can tell you that the US Air Force, for example, just one is very interested in this and is now using this to inspect aircraft all around the world, actually. And it routinely uses it for inspections. And, you know, there's a lot of steps from the time you develop some technology to the time somebody asks if you can make a connection, to the time you make a prototype, to the time you have a engineer along within a deployment, to a time when you actually have the end user doing this yourself. But one way to think about the lasting impact of this is that in this application anyway has made it all the way through a place where a lightly trained user can in fact deploy the system. So I'm going to stop there. There are many such applications, and G gave some ideas of them, but I like this one because it's very visual, very easy to understand what the impact is. And here it is, it's being used all these years later.
Hiya, please.
G. Sanjeev, great, excellent keynote. Thank you so much, and congrats again on this amazing achievement. Please stick around. We are going to try to take a few questions at the very end of the session. But before then, we are going to transition and I will pass it to Ayun Kim, who is our expert panelist today, and he's going to tell us a few bits about the evolution of LiDAR-based odometry and SLAM after LOM. So Ayun is an associate professor at Seoul National University, and of course she's here because she's an expert on SLAM, localization, mapping, with LiDAR, as well as other sensors. So it's a pleasure to have you here. Ayun, take it away.
Thank you very much. Thank you, Luca, for introduction. And I really appreciate Ji and Sanjeev. Congratulations to your award. And at the same time, it's a really great pleasure and honor to participate in this talk so that I can summarize 10 years within 15 minutes. It's very challenging, but I'll try my best so that we can have a nice transition to the Q&A session later. So my name is Ayong. I am at Seoul National University. I've been working on many LiDAR, SLAM, place recognition works, and I'm kind of catching up from what Ji told us and what happened beyond the LOM, and quickly summarize things. So this work, the LLM, defined the edge features and planar features. It's like you can think of it as a feature-based LLM. So nice feature, what should we use for the Lidar LLM? And ever since that, like many algorithms came out, and one of them is Lego LLM. And Lego LLM, they define the ground, using ground plane is really important, and so that you can use noise removal and making it a lightweight, running in a real time on an embedded system. And then many try different ways. For example, Suma came out, and then it was RSS 2018 paper, and using a surf file for the map representation. And later on, they developed further to Suma++. They can incorporate the semantic labels and then making a semantic SLAM. And then we come to have an inertial odometry, Lidar inertial odometry, or LEO. And I think Ji briefly mentioned about like solving one big optimization, and LEO-SEM is in that way, like it's solving many factors and then it's combining factors in a tightly coupled manner. So IMU is helping the LiDAR as an initialization, but at the same time, LiDAR odometry helps to estimate like IMU biases in a coupled manner. So we start to use the IMU more actively, and then we have a fast LEO came out. As the name says, fast, how fast it is 100 hertz. LiDAR usually runs at 10 to 20 hertz, but they kind of kicks that up toward 100 hertz and are making really fast. How they made this possible is they define a new Kalman gain so that they alleviate a lot of computational effort. And then they have a fast LEO too, and they start to change perspective a little bit, like going back to the traditional ICP-like manner, looking at the point level, just like what happened for the visual SLAM. Visual SLAM, we had a feature-based SLAM, and then later on they have a direct method. They try to look at the images as a holistic way. So same thing for the LiDAR. So we start to look at the point, and later on in their work, point LEO, they are looking at a more direct point-wise registration. That's not all. Like in a KISS ICP from the University of Bonn and their group kind of did amazing work. They also looking at the point-to-point ICP, and their argument is if you do it correctly, you don't need many parameters. So here, they only have a number of parameters, and they said handful of parameters. One thing that most of the SLAM researchers are experiencing is we have a lot of parameter, and when you move from drone to UGV to the leg robot, you have to tune the parameter a little bit. But their work, they handle this one very well, and they require no tuning, which is amazing. So one parameter set can work for many different environments. So that's I try to encapsulate. I already said that I can only encapsulate small number of algorithms, but there are so many. From the Lego Room to Suma and LEO-SEM to Fast LEO to, and I kind of deviating from it just to indicate that these are the direct method more like, and then some algorithms started using the IMU. So by the point now we are incorporating not only the vision, not only the IMU, but the LiDAR SLAM together with the manufacturers and completing it. But they are SLAM in the sense that they handles loop closures. But how do they do that is, so how to propose a loop closure in their algorithm is by having a kind of search bound, or based upon their current estimate, look at the nearby point, or they do that for entire thing, but using the fast tree search kind of scheme. But we probably want something more topological or appearance-only place recognition, just like a visual place recognition. We call that as a LiDAR PR. And so that we can have a kind of one single point cloud, and looking at it as a holistic way, and can we determine, have I seen this one before, and can we solve the kidnapped robot problem? So in that way, having those place recognition module running, you can complete the SLAM more robustly, and in the line of that research, we have SegMatch by the ETH group, and their idea was to have all those object segmentation and labels in a matching in a local level. So this is car, there's car gain, and you can do that. And they have another RSS paper on that. And there's another approach coming from the visual perspective. Like there's a computer vision society, they were looking at how to encapsulate the point using like point net. And they were also looking at the flood or net flood for the visual place recognition. So easy, straightforward solution would be combining those two together, having a point net flood, and using that to encode a point cloud into one nice descriptor and matching that globally. So that kind of worked out well. And later on, this is our algorithm, the scan context. So I think most of the work in this area, they try to use the deep learning, but ours, we try to avoid it so that we can have a very lightweight. So our idea is looking the point cloud in more global manner or macro manner, looking at from the bird eye view, from the top-down view, and stacking this measurement column by column. What you are looking at is the height of the building. So you can think of this scan context as an unwrapped version of the skyline of the building. So this one kind of works nicely. So we can use this scan context image to describe a single place from the LiDAR point, and you can use this one for the matching. But the problem is you can only do that in urban environment, 3D environment works perfect, but there's a limitation in indoor, how you're gonna define a highest building indoor. So people kind of tackle this issue. But the nice thing about the scan context is because from this x-axis from 0 to 300 degree, so when you are coming back on the reverse route, you can estimate what you're gonna see as a scan context because you can take half of it and then putting it the other way. So ours is able to detect the place recognition even in the reversed route. There's a more paper came out in this PR, like another RSS paper 2020 by the University of Bonn, and they look at this problem. And one idea is if two places are from the same place, they should have enough overlap. So they, from this idea, they develop an overlap net and then solve this place recognition problem. And more recently, we have an InstaLog RSS last year. And they are, I think, they are looking to the indoor problem because so far we've been looking at the outdoor problem or urban environment, and their idea is to looking the semantic labels and matching indoor scene. Indoor scene is much more harder, but they made it work, and then they made it work in the real time on a single GPU. So yeah, the indoor and tackling the learning, and then ours was not the non-deep, but there are more. I kind of had to miss the Mink log or log 3D or the ring, another handcrafted feature. But these are kind of overview of what happened in the last 10 years. So now we have odometry and we have place recognition or loop closure detector, and now we combine it to have many nice SLAM papers. I tried to encapsulate, but if you want to know more, there are one survey paper on odometry and the place recognition, go for it, and then you should be able to find more there. But ever since those algorithms came out, there are many more, like PinSlam by Bone or XICP and Wildcat by Zyro, and Teaser by MIT Lucas Group, and Litamin or BOM is the bundle adjustment for the LiDAR mapping. So many works. So I think G said the SLAM is done, but he kind of started the LOAM, and he opened up a new era of this LiDAR SLAM, and so many application follows. So I want to kind of go to the open problems in the LiDAR SLAM. If you think of LiDAR, there are so many LiDARs and so many new LiDARs came out. Solid state LiDAR and spinning LiDAR and small field of view. So many different LiDARs, and their types are so different, and what they are providing as a sensor measurements are so different. So if you are using two different LiDARs, it's almost like working in two different, totally different sensors. And LiDARs start to provide a new information, not only the range, but also measurement of the velocity or ambient channel. So there are so many variety that you can use with the new LiDARs. And now we have a better capability of mapping. The key benefit of having a LiDAR is there is a very little scale drift. If you measure 100 meters, it's 100 meters. That's a kind of big advantage over the visual SLAM. But now you have a better map, but there is another challenges coming from this mapping perspective. How are we gonna deal with the multi-session? There are many, many maps are coming in. How are you gonna deal with that large size memory, and how are you gonna incorporate that into one nice map, merging many different maps at this different time? And the map, the environment itself is changing, and nothing stands there forever. So how are we gonna incorporate the changes into the map is another challenges. Evaluation, we should think about the evaluation in a different way than the visual place recognition does. And we definitely need a lightweight system, especially when the Lidar produces a so large memory size and computational cost. So that's one of the challenge. And the deep learning always is a good tool, and we have witnessed so many nice learning-based methods. For example, our previous work on the deep Lidar odometry, we try to learn end-to-end manner, and this is what the learned odometry looks like here. Or a more recent paper by the University of Bonn, they have a neural representation of the Lidar point cloud and use it for the mapping and the odometry also. Look at the size of the map. The raw point cloud was more than 100 gigabytes, but now you have very, very well encoded map representation from the neural representation. So yeah, many more chances will be there. I tried to cover many things in a short period of time, but like Ji and Sanjeev said, there are many applications like construction site monitoring or change detection in the mapping. And later on, if we were to have a drone delivery for the Tokyo, New York, we probably need a 3D, really well-made 3D map, and we have to maintain that map for a long period of time. So I think there are more applications coming up. I will conclude my talk here, and thank you very much.
10 years in 15 minutes. I loved it. Thank you so much. Thank you so much. So I think we have a little bit of time for the Q&A. I think if you can stick around with us, we can involve you in that as well. And I believe, Ji and Sanjay will be still online. While we collect questions from the audience, maybe I will break the ice with one question on my side. So we started looking at the prehistory, pre-LOM history, and telling that, iterative closest point and ICP was the method, the go-to approach, before then. Then LOM was starting to use feature-based method, and feature-based method were used for several years. And now we see KISS ICP and ICP methods, again, which are not doing feature extraction, they're dense methods. So my question is, between feature-based methods and dense methods, what are the considerations? What is the trade-off? Is one better than the other? Do you see, these two trends, they will keep going? And I will open up for Ji and Sanjeev if they can hear us.
Do you want to take that one? I have some thoughts, but why don't you go?
Okay, sparse features versus dense mapping. I guess it's my personal take. I think it makes more difference in the visual SLAM. In Lidar SLAM, because you're looking for the closest point in the 3D space, in the end, the difference is mostly about the density of the point cloud. When you have the computational power to make use of more points, and you should definitely use it. And so I'm referring to the robustness. Sometimes you go to degenerate environment, it does not have enough features. But if you use dense data, you can make use of just that little bit of geometrical features. Something like everything is flat, flat environment, but you have a few posts here and there, and you can make use of them. If you use sparse features, it may be overwhelmed by the noise from the ground, and it could fail.
Very cool.
Sanjeev?
Yeah, in some sense, when you look at what LOM is doing, it's doing something like an ICP. Not exactly an ICP, right? But it's just being smart about it, and then not only incorporating it, but just using those updates in the dimensions in which there's information and not in the others. ICP has a big initialization problem. So, the thing that happened, what G did was he starts with almost registered point cloud between the local and then the one that was done either 2 weeks ago or 30 seconds ago. So there's this idea here is, yeah, if you have complete, very dense model, in some cases it might actually work. I think the place where it might be more useful is that in the cases of very smooth surfaces or tubular kind of things, where you really actually need to take a larger part of the map and match it to the prior map. I think that may be a more useful kind if you have an environment such as that. Otherwise, in natural kinds of environments where there's structure, even very natural, like walking through farms or orchards or vineyards, strangely enough, there's enough structure there. It looks kind of random at the close end, but it's enough to be able to match there. You don't really need that full-blown ICP.
All right, thanks. So let's jump maybe into the questions from the audience. We have a few minutes to go, so let's see if anybody wants to ask questions here. There's one from Shudang here.
I think Aaron already pointed out how to evaluate the quality of the map. So in many of the data sets we have ground truths for poses, but we really don't have the ground truths of maps. So I want to hear your opinion. What's a good way to evaluate the maps? Thank you.
I don't know if you guys were able to catch the question. It was about evaluation of the quality of the map instead of just the odometry or the trajectory.
Okay, let me take a shot at it, G. See if you can add some thoughts. So, the people who are doing construction monitoring care about this, right? I mean, they want to get this right. One of the things they want to do is to want to make sure that the thing is being built properly. So during the construction, if there's any kind of deviation, then they want to be able to correct it rather than wait till the construction is completed. So they care about this, and the way they've gone about this is, of course, they have these survey points that they can make sure that, these are points that are surveyed, and you can see how that's a localization issue, okay? So first, you test it. Simple way to test it is to make sure that the control points are properly registered. You have at a site, you have maybe half a dozen or a dozen such points, and you can check those and say, okay, we know what they are. What did the method estimate? The other idea is that if you have a CAD model, or if you have a model that's been built by a stationary sensor, that's sort of like the gold standard. So you can get survey grade sensors that'll give you millimeter evaluation. So you let them sit in one place, and it takes a couple of minutes. It creates a very accurate point cloud. You move it to another place, it does that. It's sort of the opposite of what loam type methods do, which is on the fly and quick. But you can get one of these maps, and then you can sort of the evaluation is that you can actually compare the maps that are being generated from a method like this. Now, there's two things going on. One, it's iterative, online, real time, that kind of thing. The other thing is that the kind of Lidar map, the Lidars that are used are not really survey grade. So a flat wall will appear a little fuzzy because the point cloud is created from hits from all sorts of angles. But you want to make sure that thing is sort of centered around the ground truth, so to speak. So that's been a method that the people who really care about mapping have used. Any other thoughts, G, about this?
No, I'm good.
All right, thanks. I think I've seen in maybe one of the last few slides that you have a paper on the survey and also a paper about benchmarking. Do you have extra thoughts about that?
But I think Sanjay covered all three completely, using survey station and using a part and checking the consistency. So I think I can add no more.
Very good. Yeah. Okay. All right. Anybody else? Yep.
G and Sanjeev, well deserved. Knowing everything you know about these algorithms now, if you were to design a LiDAR from scratch, what would you have it be?
Okay, so talking about a perfect LiDAR or better LiDAR for autonomy, because we are, okay, so there are multiple ways to look at the question. If you just want to map well, that's one standard. But if you want to use SLAM to support autonomy system, the vehicle has to drive autonomously or fly autonomously. You need to think about the collision avoidance and planning. So the density and field of view are two important factors. Many of the LiDAR that we try, when you put it on an autonomous vehicle, the field of view does not cover the bottom part. Or sometimes you pick one that does cover the bottom part, but the top part is empty. So you end up with a blind area behind, right below the sensor in front of the vehicle. So if you step into the front of the vehicle, it can go over you because it does not know. That area is blind. So there are considerations like this. If you just want to use LiDAR for SLAM, something like you carry the sensors and walk around, you want it to cover the environment well, but if you want to use it for autonomy system, there are more considerations.
Maybe let me follow up on Tim's question. Like, I think in Loam you guys are not using the intensity of the LiDAR at all. In hindsight, do you think that's a useful information to leverage?
So let me take that. In Loam, there was very sparse data at the very start with the Hokuyu pulsing at 40 kilohertz and one line that had to be rotated. With the Velodyne, we've got 16 lines, but they're still quite spread apart. You really couldn't use that much. They weren't really too close together to be able to find features in the reflection space. But now, with some of the newer LiDARs like the Ouster, you get as many as 128 lines. And when you look at like a scan put together, at least when it's stationary, it almost looks like an image, right? Because it's so highly dense. And I think that gives an opportunity to sort of like find the visual features like we do right now in VLOAM, where the camera itself does some sort of finding some visual features when you don't have enough shape features. So that's a possibility. Note that, of course, everything is moving. But when you put this together, it certainly looks like an image when the LiDAR is pretty much static, but it would be skewed when it's moving. So it's a little bit harder to do that, but now we actually have enough resolution and dynamic range to be able to do that. I don't know who asked that question, and just say a little bit about the perfect LiDAR. The colorful analogy that I know is that when you're making beer, you get Vegemite, right? And so the question is, do you want Vegemite or you want beer, right? If you would, if you really want Vegemite, beer is just a stepping stone to get that. And if you're a beer lover, then Vegemite is just a byproduct there. So localization and mapping are like that, a little bit like that, to bring it back to our world here. And so for autonomy, what you want is range, and you want density, like G was mentioning. But if you want mapping, then you want the key thing that we need with the LiDAR is much higher accuracy. The small sensors are really safety sensors, so you get something like plus or minus an inch in sort of like in the best case, but in the worst case, of course, you have a glancing angle. It could be worse than that. So I think that the best LiDAR from a mapping perspective would be different than the best LiDAR for autonomy, the control perspective, to support autonomy. And of course, I think the requirements or desirements would be different.
Excellent. So I know we're out of time, and I know I'm staying in the way, like, to your coffee break, but I still want to give the audience one last chance maybe to ask a question. Otherwise, we can wrap up. But, let's see if there is anybody else. 1, 2, 3. If not, guys, I have to say I have plenty of questions on my side. Probably will not take more time out of the coffee break, but I still want to thank G and Sanjeev, just for showing up, giving the keynote, and just congratulating them for this amazing achievement. And thank again, Yun for the overview on the present, and future of Lidar Slam. So let's thank our speakers again, and congrats for the award.
Thank you very much. Thank you.
Thank you.
Then we're heading into the coffee break, and we are going to restart, I think, with a planning session at 3:30.
All right, welcome back, everyone. We'll start this last session today on planning, and we'll start with first paper, Auto GPT plus P, presented by Timo Beer.
Hello, I'm Timo. In our paper, we tackled the problem of generating robot plans from natural language instructions. So if the user asks, can you bring me a glass? The robot should generate and execute a plan to solve the user-specified task. If not all required objects are available in the scene, the robot should explore the scene to find the missing objects or suggest possible alternatives. This capability of robots to be instructed in natural language in such a way and react dynamically to unexpected situations is a crucial aspect in intuitive human-robot interaction. The recent advances in large language models provide an enormous leap in natural language processing, which makes them especially interesting for our problem. We can categorize the recent literature for task planning with large language models into two paradigms. For the LLM as planner paradigm, the LLM generates a plan directly from the user command in natural language. On the other hand, the LLM with planner paradigm combines LLMs with classical planning. In classical planning, we typically have an initial state and a goal state, and a domain, which contains logical rules and actions. A classical planner searches the state space to find the shortest sequence of actions to get from the initial state to the goal state. In LLM with planner, the LLM generates the goal state directly from the user command in natural language, which is then solved by the planner. As classical planners plan under the closed word assumptions, that means all objects needed for a task need to be available. However, the paradigm has the inherent advantage that plans are always logically correct in optimal lengths, especially for long horizon tasks, where the LLM as planner paradigm struggles. This is the reason why we created Auto GPT plus P, a hybrid approach that aims to combine the best of both worlds. We combine both paradigms by using the LLM with planner paradigm inside a feedback loop where the LLM is used directly as the planner. First, let's take a look at our contributions towards the LLM with planner paradigm. Here you can see a schematic of LLM plus P, the state of the art in that paradigm. Given a task and scene description in natural language, the LLM generates an initial state and a goal state, which is then solved by the planner. We improve on this by deriving both the initial state and the domain not from language, but from our newly created affordance-based scene representation, based on visual perception. Affordances can be used to model the action possibilities that an agent has with the environment, that they are ideal for task planning, and reasoning about possible object substitutions. Our symbolic scene representations consist of object affordance pairs like Kapur or table support. It is achieved by combining object detection with object affordance mapping, which maps an object class to the predicted affordances of that class. It is derived by querying an LLM. Our second contribution is automatic error correction. In LLM plus P, the LLM would sometimes hallucinate impossible goal states, like that the same apple should be in the human's hand and on the table at the same time. We eliminate these errors by predefining semantic constraints and evaluating them on the generated goal state using Prolog. We can then feed back the detected errors to the LLM to let it correct the goal state, making planning overall much more robust. The problem that still remains is the limited flexibility of closed-word planning, so the previously shown approach is only part of a bigger feedback loop where the LLM is used directly as the planner. Here, the LLM incrementally updates the robot's memory by exploring the scene or suggesting possible alternatives to missing objects until all objects are present. So here's a quick example of the entire process on ARMA.de. In this example, the user wants a glass, but as the robot does not see a glass, it explores the table. As it only sees a plastic cup, it reasons about its affordances and suggests to replace the glass with a cup, as both of them have the liquid contained affordance. In the end, it generates a plan using the method that you've just seen and executes the plan, first grasping the cup, then moving to the human, and finally handing the cup over. Finally, we quantitatively evaluated both our improved closed-word planning as well as our entire system in simulation. Our improved LLM with planner approach achieved a success rate of 98% on the second set of instructions, where we can clearly see that the error correction has a significant impact on the success rate of our method. For further details on the evaluation, please take a look at our paper or our poster. Thank you, and I'm now ready for your questions.
Any questions?
Hi, great talk. Can you comment a little on what's taking up most of your planning time? Is it the large language model inference, or is it the discrete planning process?
So it kind of depends on the complexity of the scene and the complexity of the plan length. So the LLM time or the inference time of the LLM is always the same, independent of the complexity of the scene, or it's always about the same. However, if we have really complex scenes and really complex tasks like plans that take more than 20 steps to solve, the classical planner really has problems doing that in a reasonable time. So that scales basically exponentially. However, for tasks that are like under 12 steps or under 15 steps, the time is reasonable, and most of the inference time is attributed to the LLM.
Thank you very much.
Any other questions? Okay, so if there is, maybe I will ask one quick question. So for the auto corrections, how do you detect the errors or the failure modes?
I basically define the logical conditions in predicate logic. So, for example, for an object that is in the hand, there can't be another object of the same type on any other object. So, I define a predicate logic formula, translate that into a prolog statement, and then check that on the go state. So the go state is basically a Boolean combination of predicates, and by checking this, or by transforming the go state into a disjunctive normal form of the go state, we can then check each substate of this disjunctive normal form for correctness with all those semantic constraints that we defined. So, but we have to hand define them.
Okay.
Constraints.
Thank you very much. Thank you. All right. So let's thank him again.
Thank you.
Right. So next talk is implicit graph search for planning on graphs of convex sets.
Hi everyone, my name is Ram. I'll be presenting our paper titled Implicit Graph Search for Planning on Convex Sets. GCS, or Graphs of Convex Sets, is a recent framework for smooth kinodynamic planning that removes the expensive collision checking by pre-processing planning space. Because it uses convex sets and convex constraints, the framework is very optimization friendly and the representation is sparse. If you consider this slide as a 2D environment with these black polygons as obstacles, then the free space can be decomposed into a set of convex sets shown in orange. The adjacency relationship between these convex sets can be represented using a graph shown below. So then planning on the graph of convex sets boils down to finding the sequence of convex sets and the trajectory via that sequence. So this joint optimization problem can be formulated as a mixed integer convex program that is shown on the left. GCS opt is a previous method that solves this mixed integer convex program by proposing a very tight relaxation, and it does a rounding after the fact to find a bounded suboptimal trajectory. Our hypothesis is that GCS opt underutilizes the power of GCS. So GCS is a powerful representation, but because of the choice of the solution strategy, it solves the same sized optimization over the entire graph for every query. It also cannot take advantage of the graph search techniques, although the GCS is a graph. It also cannot enforce a bounded suboptimality factor, and it only calculates it after the fact. And because it doesn't let the convex sets to be revisited, it sacrifices completeness in certain cases. For this maze planning example, you can see that GCS optimization optimizes over 1.25 million constraints for every query. So in this paper, we propose an implicit search technique called InSAT-X GCS that addresses all the limitations that I just mentioned, and it is inspired by a previous method called InSAT. So InSAT is a hybrid search optimization algorithm that combines the benefits of graph search in the low-dimensional space with trajectory optimization in the full-dimensional space. So the graph search decides what optimizations to run with what seeds, and then the optimization drives the graph search in the correct direction by finding feasible trajectories. These two operations are interleaved until a trajectory solution is found. So in GCS opt, the mixed integer part of the optimization finds the sequence of convex sets, and the convex program finds the trajectory via that sequence. So these two operations are done as a concurrent joint optimization, and that's the MICP in GCS opt. To apply InSAT as a solver for GCS, we can use the graph search to find the sequence of convex sets, and that takes up the mixed integer part of the optimization. And then the optimization in the full dimensional space can find the trajectory via those sequence. And these two operations can be interleaved until a trajectory in that GCS is found. To guarantee optimality in our implicit interleaved search method, we need to allow the subsequence of path to the convex sets to be suboptimal, and also we need to allow the paths to revisit the same convex set multiple times. So this requirement basically translates into allowing state re-expansions, and we propose a set of lower and upper bounds to efficiently prune these expansions. And the lower bound is computed by a surrogate graph that is pre-computed and using a simple search on the surrogate graph. For the theoretical properties, the InSAT over GCS or IXG is complete under the assumption that all the constraints along any path on GCS can be satisfied. The optimal versions IXG star and weighted IXG star are complete and optimal without that assumption, and they can also be trivially parallelized without sacrificing any of these theoretical properties. We compared with GCS opt in planning for this 2D maze and found that our method is like around 4 times faster, with being 12 times more efficient in terms of the edges optimized, and with only a small increase in the cost. We also compared did the same comparison for UAV and found that there was a massive improvement in terms of planning time, and with being 58 times more efficient. We were also able to deploy our planner for planning for a multi-arm motion planning problem with these 18 degrees of freedom, 3 arms, whereas the GCS opt was unable to load this problem into memory. In terms of the savings that we obtained because of the incremental nature of the IXG star, even the largest optimization that was invoked is only a fraction of the size of what GCS opt solves. So in terms of the takeaways, we show that how an incremental search algorithm like InSAT can be applied on GCS with 3 different variants with different fidelities of theoretical properties. And we see that the efficiency gains, and it also opens up opportunities for applying other graph search techniques. Thank you.
Thank you.
Hi, I realize this was not the point of your talk. I'm just curious. You start with the convex decomposition. Could you just hint about how that is achieved?
Yeah, so there is a decomposition technique called IRIS that came out of MIT. So this is it's a pre-processing. You pre-process the planning space similar to constructing a PRM, but whereas here you decompose the planning space into a set of convex sets by randomly sampling different configurations in the planning space and growing these convex regions. And once you grow these regions, the relationship can be represented using a graph.
Hi, thank you for a very interesting talk. So I wonder, can your method model as many problems as the graph of convex sets the original method can model, or can you comment on kind of the discrepancies there?
Model the contact planning problem?
Oh, no, not that one. I was meaning like the original GCS paper. Are you like limited in terms of what problems you can model, or can you solve all of those problems as well?
As long as the representation is a GCS, the solver is agnostic to what the, I mean, you can use the same solver for any GCS representation, right? Yeah, there is nothing, I mean, in terms of the assumptions, the one that I listed in the theoretical properties, so for IXG, you need to have that along any path on the GCS graph, the constraints can be satisfied. But for the optimal versions, there is nothing like that, like it can run on any GCS.
I see, that's very cool, thank you.
All right. Okay, if there is no question, let's thank the speaker again.
Thank you.
Next talk is real-time anomaly detection and reactive planning with LLMs by Rohan Sinha.
Oh, we already started? Well, the motivation for this work is that while learning has enabled tremendous advances in autonomy, eventually, the robot will encounter out-of-distribution inputs like these real-world edge cases of self-driving cars in the wild. Right? These semantic-level edge cases, like stopping for a stop sign of a billboard, are hard to handle traditionally, and our insight has been to leverage large language models to handle these cases. How can we practically increase closed-loop robot trustworthiness with LLMs? Doing this requires solving two key challenges. The first is to mitigate the computational costs of LLMs to enable real-time reactivity. And the second is that we also need to integrate the LLM-based reasoners into the control of dynamic and agile robots. We propose a two-stage decision-making framework to address these challenges. We first take a data set of prior experiences of the robot and use a foundation model to generate a database of semantic embedding vectors. Then, at runtime, we take the current observations of the robot and compare its similarity to the previous experiences in the database. We continue with the decisions made by the autonomy stack if those observations are similar, and if they are not similar, we query a large model to carefully reason about the safety-preserving intervention to take. The LLM chooses a fallback from a number of recovery sets, each corresponding to high-level safety interventions. Like for a drone, we could say landing on a field or on a rooftop, and so forth. We use these recovery sets within an MPC that maintains a tree of fallback trajectories associated with the nominal goal and a set of safety interventions. We compute embeddings of the observations in parallel so that we can detect anomalies, and we show that this can be done in real time. We then provide the current fallback options to the LLM reasoner, and as shown in orange, we constrain the fallback trajectories to overlap for an upper bound on the time it takes the LLM to return a decision. This ensures that the fallback options that we provide to the LLM are still dynamically feasible once it returns a decision. This allows the MPC to safely enact the LLM's choice. This controller design allows us to prove that our controller reaches the recovery set chosen by the LLM. As a case study, let's re-examine the stop sign on a billboard example. A base autonomy stack detects the stop sign on the billboard and slams on the brakes. Not very safe. If we look at our approach, we see that the vehicle first drives normally, but fires off a query to the LLM, encoding the current observation once an anomaly gets detected. We want to note that an embedding-based similarity query only requires a single forward pass through a transformer, and therefore it's real-time feasible. We can run this approach at 20 Hertz on an NVIDIA Jetson and actually outperform much larger models like GPT-4 at anomaly detection. The planner then slows the car down while waiting for the LLM to output, and when the LLM decides to keep driving, we ignore the billboard without ever stopping the car. While we can detect anomalies quickly with small models, it is necessary to reason about downstream consequences with larger models. We also apply our reasoners on quadrotor hardware, where the nominal goal of the quadrotor is to land on the red box in the presence of a clutter of inconsequential objects, and the drone can fall back onto the blue box or go to a holding zone. We see that if we place a bunch of quadrotors on the boxes, the drone correctly detects this and goes to the holding zone instead. What's interesting about this case is that the quad rotors were seen in the nominal data on the ground, but when we put them on the boxes, they are detected as anomalies. Similarly, if we place a previously unseen object on the ground, in the top video here you can see a keyboard, the anomaly detector flags this, and the drone slows down while waiting for the LLM to return an output. Whereas in the bottom video, you can see that the drone immediately backs out of landing when it detects the other quad rotor on the red box. In the top case of the keyboard, the drone confidently proceeds to land on the box, and the other drone on the red box, on the bottom video, forces the LLM to output landing on the blue box instead, and the drone safely recovers there. Throughout our evaluations, the following takeaways consistently hold. The first is that grounding an anomaly detector in prior experiences via embeddings outperforms zero-shot generative reasoning, that smaller models can do just as well as larger models at anomaly detection, that embedding-based anomaly detectors really detect differences with respect to prior experiences, whereas zero-shot chain-of-thought reasoning with large models is necessary to reason about the safety criticality of out-of-distribution scenarios. In this sense, our fast and slow reasoners are both necessary. The fast reasoner is what enables reactivity. Our pipeline runs 360 times faster than querying GPT-4, whereas the slow reasoner is really necessary for zero-shot OOD reasoning and decision-making about edge cases. I would like to thank all my collaborators for their amazing work on this project, and I'm happy to take any questions.
Hi, really interesting work. Can you explain a little bit more about how the anomaly detection system works? Are we simply looking for semantic situations which are not matching our training data, or is there something
So
stronger going on?
basically assume we have a database of prior experiences of the robot, right? These can be maybe the data sets used to train the system that the nominal-based autonomy stack runs, or they could be, the large amount of mundane nominals driving or flying data that any relatively mature autonomous system is bound to collect, right? We embed all of those observations to have a database of semantic embeddings, capturing the semantics of all of those scenes and settings that the robot is known to be able to handle, right? Then if you see at runtime that semantically what your observations are now are really different from things that you've seen before, that is anomalous, right? And we just basically calibrate thresholds to detect that as an anomaly, right? Just because something is anomalous doesn't mean it's dangerous, right? It just means that it's different from anything that you've seen before, right? And that is what motivates using the language model reasoners to reason about whether that anomaly is really safety critical and what needs to be done in response to it, or whether it's not actually dangerous and the car's or the robot's nominal decision is acceptable and we should go, continue about our day.
Okay, I see. Thank you.
Sorry, thank you. Interesting. So am I right in assuming that the ability to ask the LLM these questions requires that you can first accurately perceive that there is a stop sign on a billboard? And to what extent is that part of your focus as well? And I suppose related to that, like, what if there's a stop sign in front of a billboard? Might you wrongly conclude that that's a stop sign on a billboard and ignore it and crash into something?
Yeah, so that's a really good question, and maybe I've intentionally not specified too much about this in this presentation, because in the paper we tried multiple things. One of the things that we tried is you could directly use a VLM to sort of understand the scene and reason about what to do, right? Something like GPT-4V and so forth. The other thing that we tried is we tried using open vocabulary object detectors, which basically detect bounding boxes of all types of obstacles in a scene and return open vocabulary captions of said obstacles, right? Which means that those models generate free-form text describing specific parts of an observation, right? And then we use those detections to parse them into a language prompt, which we then provide to text-based reasoners. And so we compare against the two of them. I think there's promising results in both areas, but there are some small nuances in how they differ. I would love to talk further with that at the poster session, because I think those can be quite insightful also.
All right, thank you very much.
So hello everyone, I'm here to present our work, iHero, Interactive Human-Oriented Exploration and Supervision under Scarce Communication. So, the problem of multi-robot exploration has been studied for years. To obtain a complete map of an environment, an operator deploys a group of robots equipped with sensors to navigate automatically in the workspace. Most previous works assume that all robots can exchange information via wireless communication instantly at all times. In this case, all the robots and the operator can share the same global map, so it is easy to monitor exploration progress and interact with the fleet. However, this assumption is impractical in many real-world scenarios, where the communication facilities are unavailable or severely degraded. In this case, the robots can only exchange information when they are close to each other via ad hoc networks. This poses great challenges to the coordination between the robots. Moreover, the operator can no longer supervise the exploration progress or interact with the fleet if no robot returns for data propagation. Lastly, it is common that the operator may want to move inside the explored area, in which case, to maintain the interactions through movement is quite challenging without global communication. Therefore, we consider three kinds of online requests. First, the local map of each robot should be known to the operator within the latency bound of TH. It provides the operator with a timely update of fleet status and map data. Second, a region specified by operator should be prioritized to explore. And third, the operator requests to move to a new position within the map. And the objective is to minimize the time that the operator receives the whole map. To overcome the challenge of limited communication, there are three kinds of basic strategies. The independent strategy requires each robot to explore and return independently without active communication, and thus lacks coordination between robots. Another strategy requires the fleet and operator to maintain a connected communication network at all times. Though it ensures a real-time data flow, the connectivity requirement severely restricted the robot's movement and the exploration efficiency. Therefore, we applied an intermittent communication protocol which can balance exploration, communication, and data propagation. Specifically, the local plan of each robot is in the form of meet, explore, meet, return, and so on. And their communication follows a predefined communication topology, which means their communication order is predetermined from the beginning and will not change thereafter. On the other hand, a dynamic connection between the operator and fleet is allowed, and the choice of return robot is optimized online according to exploration progress. During each meeting event, the two robots first optimize their local plans by filling between confirmed meeting events with newly generated frontiers. Then, they check whether a return event is needed before they meet next time. If not, they will determine the time and place of their next meeting event subject to the latency constraint. Otherwise, a return event will be appended to the local plan of the corresponding robot before they determine their next meeting. As for the other two human requests, the operator-specified region is prioritized by giving more weight to the nearby frontiers. And the movement of operator is restricted in the feasible region, such that the latency constraint can still be satisfied if the operator moves in the environment. And this is the overall framework of our system. The inter-robot communication module maximizes exploration efficiency and ensures timely update to operator. And when the robot returns, the operator updates his data and sends requests to the return robot. The return robot then responds to the request by providing guidance for human movement and incorporating these requests into future coordination with other robots. To validate the proposed method, we tested 3 different requests separately with different parameters in the office and cave environments. And the bottom right video presents the entire process of an operator using 4 robots to explore a cave environment, showcasing all aspects relevant to the considered problem. And the results show that iHero ensures a timely status update to operator and efficiently fulfills all the human requests. Moreover, our system works fine even for 15 robots, and is robust to human robot failures. We also tested a large and complex environment with a fleet of heterogeneous robots. Finally, hardware experiment is conducted with 4 robots in an office environment. The operator is equipped with a pad for visualization and interaction. During exploration, operator specifies prioritized region and chooses his next position within the map. And the feasible region is denoted by the red area. Then he leaves his original place and heads for the new position. Finally, the whole map is obtained and the mission is accomplished. So thank you for listening, and if you are interested, please check our paper and come to us in the poster session.
Thank you.
Hi, great presentation. I was wondering, the robots only communicate their maps to the human operator, or is there any way for the robots to like tell another robot like, hey, I'm gonna keep exploring, here's my map, you go tell the human operator both of our maps or something like that?
Oh yes, actually, when the robot returns, he will bring the plans of the other robots, so the operator can choose his interesting region according to the plans of the robots.
And so only one robot needs to meet the human operator at each return instead of the whole fleet?
Yes. So this kind of intermittent communication protocol ensures that because the robots, they communicate very often in this kind of environments, so there's no need for all the robots to return. So we dynamically optimize the return robot. So usually there's only one robot to return to the operator.
Thank you.
Any other question? Okay, so perhaps I will ask one question. So sometimes there are some communication issues that happen because maybe of obstacles or some locations that are not modeled. How do you deal with that?
Actually, the communication event between two robots is we give it a determined location and the time. And they will try to get to that position. And if they are close enough, they will just communicate with each other. And if one robot fails during his path to the meeting point, then the corresponding robot will wait. And if he waits for a maximum time of a predefined limit, then he will think this robot has already been failed. So he will continue to go to his next meeting point so that the other robots can still communicate and explore. And our system can still works in this kind of robot failure.
Okay, thank you. Let's thank the speaker again.
Okay, our next presentation will be Who Plays First? Optimizing the order of play in Stackelberg games with many robots. And the presenter is Haimin Yu.
Do you remember the last time you were stuck at a stop sign, but not sure who should go first? Turn out, robots find it awkward as well. Let's see how our work, Who Plays First, can resolve this issue properly. We are entering a future where many transportation systems are gradually become autonomous, both on the ground and in the air. However, coordinating those robotic systems at scale can be challenging. This is mainly due to the need to ensure their safety and fairness. In our paper, we target as multi-agent trajectory planning problem with two types of stakeholders, a regulator and a group of interacting agents. We are assuming that agents are self-interested, and they're driven by their individual utilities, such as avoiding idle times and catching up with schedules. And on the other hand, the regulator, such as a traffic light or air traffic controller, oversees all agents to ensure their safety and collective efficiency. So there's a clear trade-off between optimizing the individual and social performance. How can the regulator balance this trade-off? We formulate this multi-agent decision problem as a hierarchical Stackelberg games. First, we will let the regulator determine the order of play for each agent, and then the agent will compute a Stackelberg equilibrium according to the assigned orders. In order to solve this game for any fixed order of play, we use a distributed algorithm called sequential trajectory planning, or STP, in which a lower priority agent has a responsibility to avoid higher priority ones. But the issue is, how should the regulator decide this order of play, such that it will optimize the aggregate social performance? One way is to use a brute force approach that enumerates all possible subgames. First, we can just record the social cost of all subgames and pick up the best ones. However, the issue of this approach is that its complexity blows up factorially and can take days or weeks to compute the optimal ordering for 10 robots or more. So how can we find the socially optimal order of play at scale? We propose an algorithm called branch and play, which implicitly enumerates the order of play on a search tree to speed up the computation process. And then the optimal ordering is given to a low-level game solver, which is STP in our case, that plans the agent's trajectory individually. Now let's take a look at how branch and play works. Our algorithm relies on two fundamental operations. First, we can assign a partial permutation to players. Those unassigned agents will play along and ignore everyone else. Second, we require the social cost of a partial permutation to be admissible in the sense of never ever estimate the social cost of a complete child permutation, just like A star. Now we can use those partial permutations to construct our search trees and use their game value to prune the trees. Now we consider this full UAV collision avoidance example with a root node where nobody is assigned to any order. We first extend the tree by assigning the order position to additional players. Since we know those underperforming non-leaf nodes can no longer improve due to admissibilities, we can just use the social cost of complete permutation to prune the trees. And finally, we arrive at the optimal order of play. Our main theory states that branch and play returns a socially optimal permutation. Although the worst case complexity will still be factorial, we find that in practice, this upper bound is rarely hit. In the experiment, we first apply branch and play to simulate air traffic control examples involving 8 airplanes flying on a collision courses. In terms of solution quality, we achieve a 35% improvement in the travel time efficiency compared to a first-come, first-served baseline. In terms of computation times, we empirically observe that branch and play usually converge within only a fraction of time required by the brute force approach. In the second experiment, we also test our algorithm on a hardware experiment with a fleet of autonomous delivery trucks. The trucks need to obey the rule of road and, of course, avoid accidents. As you can see, coordinated by branch and play, the trucks are able to yield to each other and efficiently complete their individual routes. So to summarize my talk, our branch and play algorithm is guaranteed to find socially optimal order of play to coordinate trajectory of multiple robots and scale gracefully with number of robots grow up. It's general and modularized enough so that you can use any low-level game solver as long as their partial solution is admissible. Finally, we have demonstrated in both simulation and hardware experiment that branch and play can safely coordinate multi-robot interaction in real time. Thank you, and please check out our poster in the next session.
Thank you very much. I'm not entirely clear. So is this a top-down, one controller making the decision for all the agents? And if that is the case, then how do you see it being applied to things like self-driving cars, where presumably they're independent agents?
Thank you for your great question. So first, yes. So we are considering a centralized system that is coordinating multiple robots. And secondly, I think, first of all, application, it will be, for example, air traffic controls, you have a regulator that controls many individual, individual robots or individual airplanes. And beyond the air traffic controls, for example, we have warehouse robots where, you need a centralized system in order to coordinate many systems to avoid congestions. And potentially, I think, in terms of autonomous drivings, we have technology like V2X that potentially, can do the communication. And then you do need some centralized system in order to coordinate their plannings. And I also want to emphasize is that, compared to many traditional centralized methods, when you scale up to many robots, you cannot solve it, easily with a very large state space. But in our case, we are able to decompose this as, ordering problems, and then to solve the Stackelberg equilibriums to resolve this in real times.
Okay, for the sake of time, we have to move on to the next talk, but let's thank our speaker again. So the next presentation will be goal-reaching trajectory design near danger with piecewise affine reach-avoid computation. And the presenter is Long Q Chung.
Hi, my name is Long Q Chung, or you can call me Edgar. Under extreme dynamics such as drifting, how do we guarantee that the agent both reaches the goal and avoids the obstacle that are placed near the goal? This is known as the reach-avoid problem for near-danger scenario. In this presentation, we'll talk about a formal way to efficiently compute the BRAS, or backward reach-avoid set, such that if the agent starts in anywhere within the states of the BRAS, it is guaranteed to reach and avoid. We propose a method for PARC, or piecewise affine reach-avoid computation, which can efficiently compute the BRAS for a PWA, or piecewise affine system with low conservativeness. Our method proceeds as follows. Given a planning model defined for some state parameter bound, we convert it to a PWA system by tessellating the bound, afinizing it using Taylor expansion, and then account for the mismatch between the planning model and the actual checking ability of the agent by sampling trajectories, rolling out, and then computing a tracking error bound. Online, we obtain information about the goal set, the obstacle, and the initial position. We assume we have access to a goal-reaching plan that connects the initial position to the goal set in the planning model. Notice that this coarse goal-reaching plan does not have to avoid the obstacle. We can then extract the mode sequence of this goal-reaching plan, string the goal set with the tracking error bound, and compute the BRS, or backward reachable set, with respect to this mode sequence. Any plans generated from within this BRS guarantees goal reaching when followed. To account for the obstacle, we similarly buffer the obstacle with the checking error bound, takes its one-step BRS with respect to the mode sequence, take the convex hole, take the intersection, and then backpropagate it through the mode sequence as a subset of the BRS. This computed BAS, or backwards avoid set, over approximates the set of all plans that, when followed, collide with the obstacle. Therefore, by taking the set difference between the BRS and the BAS, we obtain the BRAS, which for all plans generated within, guarantees goal reaching and collision avoidance when followed. Of course, there exist many methods in the literature that deals with this reach avoid problem. However, it is very hard to compare them because each of them has a different advantage. For a variety of experiments, we notice a unifying challenge for all of these methods lies in the near-danger goal-reaching scenario, which is why we propose a PARC method to address this gap in the literature. We believe PARC has three things it has that the other method doesn't, that enables it to do near-danger goal-reaching. Planar checker cooperation, low numerical approximation error, and time-varying uncertainty model. We'll demonstrate the importance of each of these with three experiments. For the first experiments, consider a learning-based method. It doesn't have any formal guarantees, which is why it can sometimes collide with the obstacle before going to the goal. In the opposite, a method that considers an adversarial planar tracker may be too conservative to even get through the gap. PARC considers the planar tracker as cooperative, which is why it successfully gets to the goal while the other two methods fails. Even if the planar tracker is cooperative, for the second experiment, we found out that if the method uses a set representation such as sonotope, which has more conservativeness than the polytopic set representation that PARC is using, it will fail to get to the goal while PARC could. For the third experiment, consider a sampling-based motion planning method with a constant error checking error bound. If the gap is wide, of course, it could just get to the goal. However, if the gap is small, it would just fail to find any safe plans that get to the goal. PARC can handle a time-varying checking error, which is why we succeeded to get to the goal while the other method failed. Also, because PWA has such a representation power, we can extend PARC to handle extreme dynamics such as drift parallel parking. We adopted drifting dynamics from existing literature, fit a PWA function through it. In the figure, we can see that the small BRAS indicates this is indeed a very challenging problem. However, as I said, any trajectories generated from within this BRAS guarantees drift parallel parking reach avoid when followed. In conclusion, we believe Park is the key step to guaranteeing reach avoid for near danger scenario by being safe but not too overly conservative. As a future work, we'll focus on speeding up the Park algorithm as well as stress test Park on more hardware examples. Thank you.
Can you comment on how sensitive your approach is to the dimensionality of the problem?
Yes, that's a great question. The question is how does my method scale to the dimension? So what we're dealing with is a planar tracker framework. So the actual robot can be very high dimensional. As long as we design the planar carefully, the mathematical method in the polytopic sense, it does scale with the dimension. However, the planar's dimension is a user choice. So the maximum kind of dimension that we can handle is like a 6-dimensional planning model. However, if we're careful, for example, in one of the experiments, we have a 12-dimensional planning model that we decompose into 3 4-dimensional models, and we can handle that. So it depends on the user choice on what dimension that you choose.
We have another question up there.
So it seems that when you find some reachable set that intersects the unsafe set, then you do backward reachable set computation to your initial set. So is there some limitation in the intervals or the dynamics that limits you how far back you can go, essentially?
Yes. So if I understand your question correctly, you're saying what is the number of time steps that we roll back? Yes. Okay. So in this example, we are assuming a fixed time problem, meaning that we obtain the number of time steps that it takes for the robot to reach from the initial position to the goal by using that goal reaching plan that we initialize with. So the number of time steps is determined by the goal reaching plan. However, if we're careful about the formulation, we can also turn this from a fixed time problem to any time problem. It's just we did not show it here for simplicity.
Okay, then let's thank our speaker again. And we are moving on to our next talk on partially observable task and motion planning with uncertainty and risk awareness. And the presenter is Aidan Curtis.
Hello, my name is Aidan Curtis, and today I'm going to be discussing our paper on partially observable TAMP with uncertainty and risk awareness. There are many forms of uncertainty that are important to reason about in robotics. Just to name a few, we have object pose uncertainty due to noisy sensors, action outcome uncertainty like grasp success, position uncertainty for mobile robots, ambiguity in human interaction, detection classification uncertainty, and larger map uncertainty that comes from extreme partial observability. In this paper, we desire to build a long horizon planner that's capable of handling all of these different forms of uncertainty. Just to give a bit of context, here's some of our recent work on long horizon manipulation via task and motion planning. Given a set of low-level skills such as picking, placing, pushing, pouring, etc., our planner can take in RGBD images along with natural language goals and convert it to a logical goal. As long as the goal is achievable, given a set of skills, it can sequence those skills to achieve the goal in a zero-shot manner. While this is a fairly capable system, it assumes full observability and outcome determinism. This means that it thinks it knows everything about the world from a single image, and that its actions will always succeed, so it never has a reason to gather information or consider potentially disastrous effects of risky actions. To deal with partial observability, we need to move from planning in state space to planning in belief space. A belief is simply a probability distribution over the state space. The belief representation could be arbitrarily complex and encompass many aspects of uncertainty, such as pose, shape, class, universe, map, or physical uncertainty. The initial belief can be derived from an image and updated with new observations via a combination of structured estimation modules and a particle-based belief updater. As in standard TAMP setting, we require a set of predicates and operators. Predicates are classifiers that are a function of the belief, and operators define both the preconditions under which we expect our skills to succeed and some effects that we expect our skills will have on the world. These abstractions make planning tractable in large spaces. In our approach, we use belief space predicates and belief space operators. In addition, we expand the standard Bipedal semantics to include uncertain effects that we are unsure will hold after the skill is executed. We call our approach TAMP, with uncertainty and risk awareness, or TAMPERA. Our method starts with a cost-weighted deterministic planning step with initially uniform cost weights. The determinized plans are evaluated under simulations to determine if their actual effects on the belief. These effects update the cost weights, which are then fed back to the determinized planner for more informed determinized plans. This model learning step is a probabilistic generalization of the sampling step that's common in many fully observable TAMP algorithms. Lastly, we pass our learned model to a probabilistic planner such as Lau star, and we find a risk-aware belief space policy. We experiment with a number of simulated domains involving classification uncertainty, pose uncertainty, partial observability, physical parameter uncertainty, and localization uncertainty in a mobile robot context. We find that our risk-aware method can outperform determinized belief-based TAMP methods, and also can outperform some non-TAMP planning and reinforcement learning baselines. Here we show our planner working to find an object in a partially observable scene. The blue dots on the right indicate the robot's belief about where the object could be. The robot acts efficiently by looking behind larger objects first, and only looking under objects when all of the other options have been ruled out. In this setting, we're using a probabilistic pose estimation model that uses an inverse rendering-based strategy to return a full posterior over possible locations of the non-visible object. Because of this, when the robot knows the shape of the object it's looking for, such as a banana in this case, it can ignore parts of the scene that are non-visible but incapable of containing that target object. Lastly, the system is risk-aware, making it capable of safely avoiding humans in the workspace. We model human-robot collision with a decaying 3D occupancy grid. Here we see the robot online replanning at the task level to avoid human in the workspace. It can complete parts of the task that avoid human collision and wait for the human to move if no progress is possible elsewhere. Sorry, these QR codes don't really work, but if you come to the poster, those ones work. But yeah, thanks for listening.
Hey, very nice work. So could you comment on the computational time of the approach with respect to the number of tasks? So that video, I suppose, was real time, but could you comment on this?
Sorry, could you repeat the question?
So yeah, so the video that you saw, I suppose that one is real time. Could you comment on the computational time of the approach with respect to the number of tasks and also potential limitations of the method? I'm also interested.
Yeah, so I guess the question was about computational time. In our experiments, it seems the computational time is equally split between symbolic solving and sampling. And so faster samplers or symbolic solvers would speed up the process.
But could you give an indication with respect to the number of tasks? Or how long does it take?
Oh, the number of samples, yeah. So again, it depends on how long it takes to simulate out each sample. But yeah, it's on the order of like 10 seconds per step. And we do rerun the model learning after each step. So, yeah.
Okay, thanks.
We have one more question over there.
Hi, thank you for the really interesting talk. I was wondering how the robot decides when it is confident enough to act or maybe to correct an action. For example, for the banana example, that it's actually found a banana.
Yeah, so we equip our operators with belief space preconditions, and these often come with some thresholds in belief space. So it can continue to act in a certain way until it passes one of these thresholds. And then there's also, effects that we are estimating the likelihood of. So it's possible that you can discretize in such a way that you are able to select the threshold for which you expect a certain outcome to happen more likely than not.
And those thresholds are tunable?
Yeah, and you can have multiple thresholds within a single problem. So it's possible that, for a threshold of 0.75, you get success like 90% of the time, but for a threshold of 0.8, you get it 95% of the time. So the system can pick the 0.8 if it requires fewer samples.
Cool, thank you.
Okay, let's thank our speaker again. And we are at our last talk of the session and of today, and that will be logic skill programming, an optimization-based approach to sequential skill planning. And the presenter is Teng Ju.
So hello everyone, I will present our work about logic skill programming. It is an optimization-based approach to sequence manipulation skills. So let's first think about this problem. Given the initial configuration of the object, we want to find the shortest path to manipulate it to reach the target configuration. So here the shortest path means a path with minimum control cost or maximum cumulative reward under the constraints. So how can we solve this problem? It is actually a contact-rich manipulation task with multiple different contact modes, like contact breaking and making, and sticking and sliding. Moreover, because of the long horizon process, there will be multiple different manipulation primitives. So all of this will result the solution space to be a piecewise smooth manifolds. Then our task is to find the shortest path on these manifolds between the initial and target configurations. So to handle this hybrid contact dynamics issue, multiple methods about mixed interior programming have been proposed, like MPCC, graphical convexites, and logic geometric programming. But I would say all of these methods can be seen as planning methods. They are hard to handle the context uncertainty in the real world. Therefore, the sampling-based skill planning methods, sequential skill planning methods have been proposed. The basic idea is to use a high-level symbolic planner to find the symbolic skill skeleton, and then rely on sampling-based methods to find the feasible paths. But as I mentioned at the beginning, we want to find the shortest path without the symbolic goal. Therefore, an optimization-based approach is required to sequence the manipulation skills. So to the best of our knowledge, our proposed method in this work is the first work in this line. So we propose logic skill programming. It's a first-order extension of a mathematical program. So here we introduce the symbols to describe the manifolds. And because we have no idea about which manifold the target configuration will be located in the end, so it means there's no symbolic goal. Then we introduce another evaluation function to check the performance of the final configuration. Therefore, the whole objective of this program is to maximize the sum of value functions and also the evaluation of the final configuration, subjected to multiple different constraints, like the symbolic transition conditions, path constraints, and also mode switching constraints. So the first step is to learn the skill policies and also approximate the value functions. So here we employed a method called generalized policy iteration using tensor train. It is an approximate dynamic programming method over the full state space. So based on this method, we can build the task-agnostic skill library with multiple different skill operators, value functions, and also the corresponding policies. We then propose to solve logic skill programming by alternating between the symbolic search and also the skill value optimization. So resulted skill skeleton and optimal subgoal sequence are then used to actuate the robots in the real world. So we first compare the value functions obtained from TTPI with another two state-of-the-art reinforcement learning methods. We can find from this table that the value functions in tensor train formats has higher accuracy, and the training time is really much lower. And then we compare our proposed method with a sampling-based approach called STEP. We can find the quantitative results are shown in the paper. From that result, we can find our proposed method does not rely on the explicit symbolic goal, and can achieve a much higher cumulative reward compared with STEP on these three different manipulation tasks. We then validate our approach in the real world. So given an evaluation function or the final configuration without any symbolic goal, our method can find the optimal full logic geometric path. And it can also cope well with the contact uncertainty and external disturbance in the real world. So in the future, we plan to explore more about low-rank structure for full path optimization using tensor approximation. And then we want to imply this method to solve much more complicated tasks without symbolic goals. For example, building a tower as high as possible with multiple objects. And these objects can be non-graspable, partly graspable, or graspable. So that's all. Thanks for your attention, and feel free to ask questions.
Thanks, very interesting. The set of skills here, are they fixed in the beginning and parameterized, and you search over this fixed set of parameterized skills?
So we build this skill library offline. So you have multiple skills, and then in the planning part, we use the symbolic search to find, okay, what's the correct skill skeleton.
Okay. And can I ask about the real experiment? I presume you're also running perception where here you assume you can detect the object and...
This method is state-based, not image-based.
And you're, okay.
Yeah.
Sure, thanks.
Any other questions? Yep.
Thank you, this is very cool. I like the hardware. I would like to know more about the computation time, if you had not spoken about that, and then how you handle the pre and post conditions for these skills. Like, just out of curiosity.
So I didn't get the question. Can you repeat it a bit?
I think the important part is just like the pre and post conditions for the skill library that you build. Like, I think that's the core idea, right? Like how you link them together. But I just wanted a little more detail. No. Okay, we can talk offline. Sorry.
Okay.
Sorry.
Well, on the poster session. Yeah.
Okay.
Okay, if there's no more questions, then we end almost right on time. Let's thank our speakers again.
Okay, thank you.
All right, thanks everyone. So we will now go to our poster session, and then at 5 o'clock, we will have our town hall. So in the town hall, if you are interested to learn a bit more about the review process and how RSS gets organized, and especially if you have feedback or ideas how we can make things better, please join us back here at 5 o'clock for the town hall. And let's thank the speakers for this final session.